You solve problems. A lot of them. Maybe 100. Maybe 300. Maybe more. And then a new interview question shows up. And your brain goes blank. That is the trap of random grinding. You remember answers, but you do not recognize patterns fast enough under pressure. This video is different. This is PatternMastery 100, 100 interview questions, organized around the patterns Phong companies keep reusing. And every solution follows one system. Basics. Breakdown. Assess. Structure. Implement. Check. All solutions will be implemented using Python. So do not watch this like entertainment. Watch it like training. Pause. Think first. Find the pattern. Then compare your thinking. By the end of this session, you should not just know more problems. You should see problems differently. Clone graph. If you want to ace technical interviews at Phong and beyond, clone graph is a classic you must master. This PatternMastery 100 essential tests whether you truly understand recursion, graph traversal, and deep copying data structures. Did you know that a significant portion of candidates lose points here by shallow copying nodes, missing cycles, or failing to preserve graph structure? By getting this one right, you'll stand out in any interview and be ready for a whole family of graph problems. Here's the breakdown. You're given a node from a connected undirected graph, where each node contains a value and a list of neighbors. Your job? Return a deep clone of the graph, a new set of nodes, with the same structure and connections as the original, but no shared nodes. You can't just return the same nodes or rewire incorrectly. Cycles and shared neighbors make this tricky, so you need to carefully manage which nodes you've already cloned. Let's assess the challenges. Graphs can have cycles, so a naive recursive or iterative copy may loop forever. Nodes might be shared among neighbors. If you clone each node multiple times, the structure gets corrupted. We need a way to remember which nodes we've already cloned, so we can reuse the correct references. Use a hash map, dictionary, to track each original node and its corresponding clone. Traverse the graph, BFS or DFS. For each node, if it hasn't been cloned, make a new node and put it in the map. Then, recursively/iteratively clone all its neighbors. Here's our plan. Edge case. If the input node is none, return none. Create a map, old to new equals, to track original to clone nodes. Define a helper, DFS or BFS. If a node is already in the map, return its clone. Otherwise, clone the node, add it to the map, and recursively clone all neighbors. Return the clone for the input node. This is solution 1, DFS recursion. Time complexity, O(n plus m). We start by defining a class named solution, which simply organizes our method. This defines our function cloneGraph, which takes a starting graph node and returns a deep copy of the entire graph. We check whether the input node is none. If there's no graph to clone, there's nothing to do. So in the case of an empty graph, we simply return none. We create a dictionary called cloned. It will map original node clone node. This ensures we never clone the same node twice and also prevents infinite loops in cyclic graphs. We define our helper function DFS, which performs a depth-first search to clone nodes one by one. If we've already created a clone of the current node, we return it immediately. This avoids duplicate nodes and handles cycles safely. So if the node has already been cloned, we just return the saved copy. If the node has not been cloned yet, we create a new node with the same value as the original. Right now it has no neighbors. Those will be added next. We store this new clone in our dictionary so we can reuse it later. We loop through all the neighbors of the current node. Each neighbor is another connected node in the graph. For each neighbor, we recursively clone it using DFS_NA and then append that clone neighbor to the new node's neighbor list. This is how we rebuild the structure of the graph. After cloning the node and all of its neighbors, we return the completed clone. Finally, we start the DFS cloning process at the input node and return the fully cloned graph. Final wrap-up. And that's how this algorithm works. It first creates a mapping to track clone nodes, then uses DFS recursion to clone each node and its neighbors exactly once, gracefully handling cycles and shared references. Efficient, simple, and elegant. Test case check. Clone graph using DFS. Let's test our function using this input. 2, 4, 1, 3. 2, 4, 1, 3. These lists represent the neighbors of each node in the graph. For example, node 1 connects to nodes 2 and 4, node 2 connects to nodes 1 and 3, and so on. Here's why the solution works. We perform a DFS traversal of the graph. Whenever we encounter a node, we create a copy of it and store the mapping in a dictionary. Then we recursively clone each of its neighbors. If we revisit a node we've already cloned, we simply return the existing copy, preventing infinite loops in cyclic graphs. And that's exactly what our program outputs: 2, 4, 1, 3. 2, 4, 1, 3. It perfectly matches the expected clone structure, confirming that the graph has been duplicated accurately. Wrap up. So, our implementation is correct. The algorithm successfully creates a full deep copy of the graph using DFS and a hash map, efficient, accurate, and reliable. Solution 2. BFS iterative. Time complexity. O(n plus m). We import dec, a fast double-ended queue that lets us pop from the front efficiently, perfect for BFS. We define a class called solution to store our cloning method. This defines our function cloneGraph, which returns a deep copy of the graph using BFS instead of recursion. We check if the input node is none. If the graph is empty, there's nothing to clone. So we return none in that case. We create a dictionary cloned, starting with a clone of the input node itself. This maps original node clone node, and ensures we never clone a node twice. We create a BFS queue and begin with the starting node. This queue will help us explore the graph level by level. We begin our BFS loop. This will run until we've processed all nodes reachable from the start node. The BFS traversal touches every node, n, and every edge, m, giving us O(n plus m) time. We take a node from the front of the queue. This is the node we're currently cloning neighbors for. We loop through each neighbor of the current node. Every edge in the graph gets checked exactly once. If the neighbor hasn't been cloned yet, we need to create its copy now. We create a clone for the neighbor and store it in our dictionary. Since this neighbor hasn't been processed before, we add it to the BFS queue so its neighbors can be cloned later. Regardless of whether the neighbor was newly cloned or already known, we connect the cloned current node to the cloned neighbor. This recreates the correct graph structure. Finally, we return the cloned version of the starting node, which is now the head of a fully copied graph. Final wrap-up. And that's how this algorithm works. It first creates a queue and a mapping of original nodes to clones, then performs BFS to clone each node and link all neighbors, ensuring the entire graph is rebuilt iteratively. Efficient, simple, and elegant. Test case check. Clone graph using BFS. Let's test our function using this input. This represents a graph with just one node, and that node has no neighbors. In other words, it's a single isolated node with an empty adjacency list. Here's why the solution works. We start by cloning the initial node and placing it in a BFS queue. Then we process the queue level by level. For each node, we look at all its neighbors. If a neighbor hasn't been cloned yet, we create it and push it into the queue. Then we connect the cloned node to its cloned neighbors. And that's exactly what our program outputs. This confirms that the BFS cloning logic works correctly even for the smallest possible graph. Wrap up. So, our implementation is correct. The algorithm successfully clones the graph, even in minimal cases, using a clean BFS traversal and a mapping of original to cloned nodes. Efficient, accurate, and reliable. Clone graph. Let's do a recap. So, we just tackled one of the trickiest graph problems in interviews, clone graph. It's a true test of your understanding of recursion, traversal, and deep copying complex structures. Once you master this, you'll be ready for an entire class of graph and network-related problems that interviewers love to ask. Breakdown recap. At its core, this problem asks us to create a deep copy of a connected graph, meaning we build entirely new nodes that mirror the original connections perfectly. The catch? Graphs can contain cycles, so careless recursion can loop forever or duplicate nodes. Assess recap. We compared possible approaches. Brute force copying fails because of repeated nodes, while using recursion with memory tracking works beautifully. The key insight was to use a hash map to store already cloned nodes, so every original node maps to exactly one copy. This ensures no duplication and handles cycles cleanly. Structure recap. Our plan was simple yet powerful. Handle the base case when the graph is empty. Use DFS to explore and clone each node. Store each clone in the map, then recursively connect its neighbors. That's it. A clean, recursive structure that mirrors the graph one layer at a time. Implement recap. We implemented the DFS-based solution, ran it through LeetCode, and it executed flawlessly. No infinite loops, no shallow copies, and no structural mismatches. The cloned graph preserved every connection while remaining fully independent of the original. Check recap. After running multiple test cases, the cloned adjacency lists matched perfectly. All cycles, neighbor relationships, and node values aligned as expected. All test cases passed with optimal performance. Closing insight. The big takeaway? Clone Graph is all about thinking recursively, breaking complex structures into smaller, familiar problems. Once you grasp how to track references and prevent duplication, you unlock the mindset needed for tackling any advanced graph or tree problem in technical interviews.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Can you spot cycles before they wreck a project? Course Schedule is a PatternMastery 100 classic. Frequently asked at Google, Amazon, and Meta for its blend of graph, topological sort, and cycle detection. Over 40% of candidates either miss edge cases or get tangled in the graph logic. If you master this, you'll ace any dependency or order check problem in interviews. Let's break down Course Schedule with the basic method, a stepwise approach that builds deep understanding for any cycle or topological ordering question. Let's break down the problem. You're given num courses, number of courses, and a list of prerequisite pairs. Can you finish all courses? Each pair, A, B, means, to take course A, you must first finish course B. The courses form a directed graph. Your task is to check if there's any cycle, which would make it impossible to finish all courses. Integer num courses list of prerequisite pairs. Boolean. True if all courses can be finished, false otherwise. Think of project tasks or college courses, where some steps must happen before others. Interviewers might ask, how would you check for circular dependencies in a build system or workflow manager? What's tricky? You need to detect cycles in a directed graph, classic topological sort. Multiple valid orderings may exist. Must efficiently track visited nodes and recursion stack. Build an adjacency list to represent course dependencies. Use DFS to detect cycles. Mark each node as not visited, 0 visiting, 1 visited, 2 for each node. If already fully visited, skip. If visiting, and you re-enter it, you found a cycle. Recursively DFS all neighbors. If any cycle is found, return false. Otherwise, return true. Let's clarify. The recursion stack, visiting, is key. It tracks the current path. Alternatively, BFS, Kahn's algorithm, within degrees works as well, but DFS is easier to explain in interviews. Edge cases. No prerequisites. Always return true. Disconnected graph, some courses with no dependencies. Multiple cycles. Build adjacency list from prerequisites. Initialize state array for all nodes. For each node, DFS. If node is visiting, return false, cycle. If node is visited, skip. Mark as visiting. DFS all neighbors. After neighbors, mark as visited. If no cycles, return true. Let's try to implement it using solution 1. This line just starts a new blueprint called solution. Think of it like naming a folder that will contain our function for checking if you can finish all the courses. Here we define a function called canFinish. It takes in num courses, how many total courses there are, like 0 to num courses 1. Prerequisites, a list of pairs that say to take this course, you must do that course first. This function will return true if it's possible to complete all courses, or false if there's a cycle, like a loop in prerequisites that makes it impossible. This line builds a graph using a dictionary. Graph is like a map where each course number, I, is a key. Each key starts with an empty list, which will hold the courses that depend on it. So we're saying, for every course from 0 to num courses, 1, create an entry in graph with an empty list. From a time complexity perspective, this takes O num courses because we loop once over all courses. Now we loop through each pair in prerequisites. Each pair is like, course, prereq, meaning, you must take prereq before course. We're going to use these pairs to fill in our graph. The number of these pairs is usually called E for edges, so this loop runs in OE time. For each prerequisite pair, we go to graph prereq and append course. In plain language, from this prerequisite course, you can go to this next course. We're building edges in our graph from prereq course. This lets us later walk forward and see which courses depend on which. Overall prerequisites, this line contributes to OE time. Here we create a list called visited with one entry per course, all starting as 0. We'll use this like a status flag. 0 equals not visited yet 1 equals currently visiting in the recursion stack. 2 equals fully processed, done visiting all its neighbors. This helps us detect cycles. If we ever see a course marked 1 again while exploring, it means we've gone in a loop. Creating this list is ONUM courses. Now we define an inner function called DFS, short for depth first search. This function will try to explore from a given course to all the courses that depend on it, walking forward in the graph. It will help us detect if there's a cycle. First check, if visited course is 1, it means we are currently exploring this course and somehow came back to it again. That's a sign of a cycle. So if we detect that we hit a course that's already being explored, 1, we immediately return false from this DFS call. Next check, if visited course is 2, it means we have already fully processed this course before, and we know it's safe, no cycle down that path. In that case, we simply return true. We're saying, from this course onward, we already confirmed that there's no cycle. Now, we mark the current course as 1, meaning, we are currently visiting this course. Now we loop over all the next courses that depend on this course. Graph course is the list of courses that you can only take after finishing this one. For each NXT, next course, we call DFS NXT to explore it. If DFS NXT returns false, it means starting from that next course, we detected a cycle. So not DFS NXT will be true in that case, and we'll react to it. So DFS course being true means this path is safe. Outside the DFS function, we now loop over every course I from 0 to NUM courses, 1. We do this because the graph might not be fully connected. There could be separate groups of courses. We want to make sure we check all of them, not just one starting point. This loop runs ONUM courses times, but remember, thanks to the visited list, each course's DFS work is effectively done once overall. For each course I, we call DFSI. If DFSI returns false, it means we detected a cycle in the component that contains course I. Not DFSI will then be true, and we know it's impossible to finish all courses. In that case, we immediately return false from the canFinish function. This is the final answer. No, you cannot complete all courses, because there's at least one cycle in the prerequisite graph. If we finish the entire loop without ever seeing DFSI return false, then it means no cycles were found anywhere in the graph. So we return true, meaning, yes, it is possible to finish all the courses given these prerequisites. Overall, the time complexity of this algorithm is OV plus E. V equals NUM courses, E equals number of prerequisite pairs. We visit each course and each prerequisite at most once in the DFS process. And that's how this algorithm works. It first builds a graph and a visited status list to represent all the courses and their dependencies, then uses depth first search to detect any cycles in the graph. Efficient, simple, and elegant. Alright, let's walk through this test case and make sure our solution behaves exactly the way we expect. We're given 2 courses, that means course 0 and course 1. And the prerequisites array, 1, 0, tells us one simple rule. To take course 1, you must first complete course 0. That's a clean, straightforward dependency chain. And importantly, there's no cycle here. Throughout this entire check, we never revisit a course that's already in the visiting state, which means, no cycles. And the program prints true, which matches the expected result. Perfect. So yes, our implementation is correct. The algorithm detects that there are no cycles in the prerequisite chain, meaning all courses can be completed. Simple input, clean execution, accurate result. Now let's try another implement approach using solution 2. This line begins our class solution, which simply wraps everything together neatly. Think of it as the container for our more optimal approach. Here we're defining the function canFinish again, but this time we'll use a topological sorting approach. This method is often faster and cleaner for detecting cycles. We start by building a graph, same idea as before. For every course from 0 to NUM courses, 1, we create an empty list. That list will store courses that depend on the current course. Here we create an in-degree list. In-degree I will tell us how many prerequisites course I has, basically how many doors are blocking it before you're allowed to enter. Now we loop through every pair in the prerequisites list. Each pair tells us, to take course, you must first complete prereq. This loop will take OE time. This line says, starting from the prerequisite, you can move forward to the dependent course. This is the heart of the topological sort approach, tracking how many prerequisites each course has left. This line gathers all courses that have 0 prerequisites, in degree equals 0, and places them into a queue. We initialize count to 0. This will track how many courses we've successfully completed in our topological process. Now we begin a loop that continues as long as our queue isn't empty. This loop is the core of topological sorting. Each time a course becomes available with no remaining prerequisites, we process it. We remove a course from the left of the queue. This is now the next course we can take. no prerequisites blocking it anymore. We increment count to mark that we have now completed this course. It's like checking off one box in our course completion list. Next, we look at all courses, NXT, that depend on the current course. For each dependent course, we reduce its in degree by 1 because one of its prerequisites has just been satisfied. If you imagine these as doors, this line is effectively unlocking one of the locks for NXT. Here we check, has the dependent course now reached 0 prerequisites? If so, it means all its requirements are completed, it's ready to be taken. And if it is ready, we add it to the queue so it can be processed next. This is like moving it into the "You are free to take this course now" list. Finally, after processing everything we can, we check if the number of completed courses equals the total number of courses. If count equals num courses, it means we were able to complete every single course, no cycles existed. If not, it means some courses stayed locked forever, which only happens when there's a cycle blocking progress. So the entire method runs in OV plus E, time, very efficient. And that's how this algorithm works. It first builds a graph and counts each course's prerequisites, then repeatedly removes courses with 0 remaining prerequisites using a topological sort. Efficient, simple, and elegant. Let's test our function using this input. 1, 0, 0, 1. These pairs represent course dependencies. Each, A, B, means you must take course B before taking course A. Now here's the interesting part. The pair, 1, 0, says 0, 1, and the pair, 0, 1, says 1, 0. So as soon as we build the graph, we can already see a loop forming. Running the algorithm, our in-degree array shows that each course has a prerequisite, so nothing starts with in-degree 0. That means our queue begins empty, and no courses can be processed, a clear sign of a cycle. And that's exactly what our program outputs, false. We expected false, and the result matches perfectly. So, our implementation is correct. The algorithm successfully identifies the cycle in the prerequisites and confirms that the student cannot finish all courses, efficient, accurate, and reliable. Let's have a quick recap. We're given a number of courses and prerequisite pairs. Each pair means take A only after B conceptually. That's a directed graph. The question is simple. Does a cycle exist? If yes, you can't finish. If no, you can. To decide, we compared two classic approaches. DFS with state marking versus BFS using Kahn's algorithm, in degree. DFS is interview-friendly and direct for cycle detection. Kahn's is an equally valid alternative. Key pitfalls: remembering multiple valid orders can exist, handling disconnected nodes, and not missing edge cases like no prerequisites. Plan of attack: build an adjacency list from prerequisites. Track each node's state: unvisited, visiting, visited. For every course, run DFS. If we ever re-enter a visiting node, that's a cycle. After exploring neighbors, mark the node visited. If no cycle is found anywhere, all courses are doable. We set up the graph and the state tracking, walked each node with DFS, and short-circuited as soon as a cycle appeared. The code ran on LeetCode cleanly, no errors. We verified the logic by running through simple passes, like a single chain, and clear failures, a two-node cycle, plus edge cases such as empty prerequisites and disconnected components. The solution behaved as expected and passed the LeetCode tests. The takeaway: cycle detection is the heart of dependency problems. If you can model constraints as a graph and reason with visiting versus visited, or in degreed appeal layers, you can reliably untangle any ordering question under interview pressure.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Ready to test your multi-source graph skills? Pacific Atlantic Waterflow is a PatternMastery 100 standout, and a frequent challenge at Google and Amazon for grid DFS/BFS mastery. More than 30% of candidates stumble on multi-source propagation or state tracking. Master this and you'll be ready for any two-way reachability problem in grids or graphs. Let's solve Pacific Atlantic Waterflow using the basic approach, a robust method for systematic, interview-ready solutions. Given an MXN grid of heights, return all coordinates where water can flow to both the Pacific and Atlantic Oceans. Water can flow from a cell to neighboring cells with equal or lower heights. The Pacific touches the left and top edges. The Atlantic touches the right and bottom edges. 2D grid of integers, heights list of coordinate pairs, row, col, where water can flow to both oceans. Think about rainwater flow on a terrain map. Where could water reach both rivers? Interviewers might ask, how would you find all meeting points in a network from multiple start sources? What's tricky? Water flows uphill in this reverse sense. We can visit a cell if it's equal/higher than the previous, simulating water flowing down from it. Need to find cells that can reach both oceans, not just one. Must avoid redundant searches, propagate from oceans inward, not from each cell out. For each ocean, mark all cells that can flow into it. Pacific, start from all top and left edge cells. Atlantic, start from all bottom and right edge cells. From each ocean border, use DFS, or BFS, to move to neighboring cells of equal or higher height, reverse water flow. Collect cells reachable by both DFS runs. The intersection is the answer. Let's clarify. 2 visited sets, one for Pacific, one for Atlantic. Each DFS only goes uphill, to equal or higher height. Final answer is the intersection of the 2 sets. Edge cases. Empty grid. Return. Single row/column. All cells touch both oceans. Flat terrain. All cells can reach both. Initialize 2 visited sets for Pacific and Atlantic. For all Pacific border cells, top row, left call, DFS/BFS and mark all reachable. For all Atlantic border cells, bottom row, right call, DFS/BFS and mark all reachable. Result equals intersection of both visited sets. Let's try to implement it using solution 1. This line starts our solution class. It's like creating a container to group our method that will solve the Pacific-Atlantic water flow problem. Here we define a function called Pacific-Atlantic that takes one input, heights. Heights is a 2D grid where each cell represents the height of the land at that position. We want to find all positions where water can flow to both the Pacific and the Atlantic Oceans. This line figures out the size of the grid. M is the number of rows. N is the number of columns. We'll use M and N a lot when we move around the grid so we don't go out of bounds. This is a simple constant time operation, O1. Here we create a 2D grid called pack with the same size as heights. Every cell starts as false, meaning, we don't yet know if water from this cell can reach the Pacific Ocean. Over time, we'll mark some of these as true. Building this grid takes OMN, time because we touch every cell once. And this line does the same thing, but for the Atlantic Ocean. ATLIJ will be true if water from cell I, J, can reach the Atlantic. Again, this creation is OMN. So our setup so far is linear in the size of the grid. Now we define a helper function called DFS, short for depth first search. It will start from a cell, I, J, and mark all cells that can flow to a particular ocean, PAC or ATL, by moving uphill or flat from the ocean edges inward. First thing the DFS does, it marks the current cell, I, J, as true in the ocean grid. That means, yes, this cell can reach this ocean. This loop is our way of exploring the 4 possible directions from the current cell. Down, 1, 0, up, -1, 0, right, 0, 1, left, 0, -1. We'll use these offsets to compute neighboring positions. Here we calculate the neighbor's coordinates. Ni is the neighbor's row, NJ is the neighbor's column. This if line is doing several checks at once to decide if we should continue the DFS into that neighbor. 0 less than equals Ni less than M and 0 less than equals NJ less than N. This makes sure the neighbor is inside the grid, not outside the map. Not ocean Ni NJ. This ensures we only visit the neighbor if we haven't already marked it as reachable. That prevents repeated work and infinite loops. Heights Ni NJ, greater than equals heights IJ. This is the key water flow rule. We only move from lower or equal height to greater or equal height. We're simulating the reverse direction. Instead of water flowing down to the ocean, we start from the ocean and move uphill or flat. If we can move from the ocean inward to a cell, it means water from that cell can flow back out to the ocean. If the neighbor passes all those checks, we call DFS on that neighbor. Now we start from the Pacific Ocean's edges. This loop goes over all columns J in the top row. For every cell, 0, J, in the top row, we call DFS with the pack grid. This simulates water reaching the Pacific from the top edge and then flowing inward to all cells that can flow back to it. Next, we handle the left edge, which is also touching the Pacific. We call DFS for each cell, I, 0, in the leftmost column. This again spreads inward from the Pacific side. Now we switch to the Atlantic Ocean side. This loop goes over all columns J in the bottom row. For each cell, M, 1, J, in the bottom row, we call DFS with the ATL grid, spreading inward from the Atlantic edge. This marks all cells that can reach the Atlantic via paths going downhill to this border, in the normal water direction, or uphill when we reverse it like we're doing. And now we cover the right edge, which also borders the Atlantic. We call DFS for each cell, I, N, 1, in the rightmost column, again marking all cells that can eventually flow to the Atlantic. So to recap, top and left edges feed the Pacific DFS, bottom and right edges feed the Atlantic DFS. Across both Pacific and Atlantic DFS phases together, the total time is still OMN, because each cell is visited at most twice, once per ocean. Now we create an empty list called result. We loop over every row I in the grid. And for every row, we loop over every column J. So together, these two loops scan every cell, I, J, in the grid. This scan is OMN. Here's the key check. We look at cell, I, J, and see if pack IJ is true. It can reach the Pacific. ATL IJ is true. It can reach the Atlantic. If both are true, then water from this cell can flow to both oceans. That's exactly what the problem is asking for. If the condition passes, we add I, J to the result list. Finally, we return the result list, a list of all coordinates that satisfy the Pacific and Atlantic condition. Overall, our time complexity is DFS for Pacific, OMN, DFS for Atlantic, OMN, final scan to collect results, OMN. So the total time complexity is OMN, linear in the number of cells in the grid, which is very efficient for this type of problem. And that's how this algorithm works. It first sets up two grids to track reachability to each ocean, then uses DFS from the ocean borders to mark all cells that can flow to each side, and finally collects the cells that can reach both. Efficient, simple, and elegant. Let's test our function using this height matrix. Each number represents the elevation of land at that grid cell. Higher numbers mean higher ground, lower numbers mean lower ground. Our goal is to figure out which cells can send water to both oceans. The Pacific touches the top and left borders. The Atlantic touches the bottom and right borders. Water can flow from a cell downward or sideways, as long as the next cell's height is less than or equal. But remember, since we ran DFS from the oceans inward, our rule flips. We only move from the ocean to a neighbor if the neighbor is higher or equal, meaning water could flow downhill back to the ocean. Now, here's what happens in this test. The Pacific DFS explores from the top and left edges, marking all cells reachable uphill or flat. The Atlantic DFS explores from the bottom and right edges, doing the same. Finally, we intersect both sets of reachable cells. Any position marked true in both grids means water from this cell can flow to both oceans. And the program outputs exactly these coordinates, perfectly matching the expected result. Each of these cells sits on a path where water can go downhill toward both the Pacific and the Atlantic. For example, 0, 4 is at the top edge and can flow right toward taller cells that eventually descend to the Atlantic. 3, 0 and 4, 0 are tall on the left Pacific edge and can climb up towards cells that drain to the Atlantic side. 2, 2 is on high ground, able to spill in both directions. Everything checks out beautifully. So, our implementation is correct. The algorithm effectively finds all cells with dual ocean reachability using two DFS sweeps, efficient and accurate. Now let's try another implement approach using solution 2. This line starts our solution class, the outer container holding our optimized Pacific-Atlantic function. Here we define Pacific-Atlantic, which takes heights, a 2D grid of land heights. Our job: find all coordinates where water can flow to both the Pacific and Atlantic Oceans. This gets the grid dimensions, m equals rows, n equals columns. We use these to navigate safely. This is a constant time O1 step. We create the pack matrix, same size as heights. Every cell starts false. We haven't confirmed this cell can reach the Pacific. We turn entries true as we find reachable cells. Building this is OMN. This creates the ATL matrix for the Atlantic. All false at first. We mark true where water can flow to the Atlantic. Also OMN. We set up Q_pack for the Pacific. We'll use BFS, so we need a queue to process cells level by level. And Q_ATL is the Atlantic queue. We'll do one BFS from Pacific borders and one from Atlantic borders. Each cell enters each queue at most once. BFS is OMN, per ocean. We initialize the vertical border cells touching both oceans. This loops over row index I. We add the left column cell, I, 0, to the Pacific queue. It touches the Pacific. We mark pack I0 equals true. This cell reaches the Pacific. We add the right column cell, I, N, 1, to the Atlantic queue. We mark ATL IN1 equals true. It reaches the Atlantic. Now we loop over column index J for the top and bottom edges. We add top row cell, 0, J, to the Pacific queue. Top row borders the Pacific. We mark pack 0J equals true. We add bottom row cell, M, 1, J, to the Atlantic queue. Bottom row borders the Atlantic. We mark ATLM, 1J, equals true. Now we start the Pacific BFS. This loop runs while Q_pack has cells. We pop cell, I, J. We know it reaches the Pacific. We'll try to walk uphill to neighbors that can also reach it. We loop through the 4 directions, down, up, right, left. This is O1 per cell. We compute neighbor coordinates Ni, NJ. We check. Inside bounds, not already Pacific reachable. Neighbor height greater than equals current height. Each cell passing this is processed at most once. So Pacific BFS is OMN. We mark PACME NJ, equals true. And push it into Q_pack. Now the Atlantic BFS using Q_ATL. We pop cell, I, J, it reaches the Atlantic. We check 4 directions again. We compute neighbor Ni, NJ. We check bounds, whether ATL is unmarked, and height greater than equals current height. Atlantic BFS is also OMN. We mark ATL Ni NJ, equals true. And push it into Q_ATL. We create result to store coordinates where water reaches both oceans. We loop through rows and columns, scanning all cells, OMN. We check if I, J, is true in both PAC and ATL. If so, water can reach both oceans. We append I, J, to result. Finally, we return result. Time complexity. Setup, OMN. Pacific BFS, OMN. Atlantic BFS, OMN. Final scan, OMN. Total, OMN. Space, OMN. For PAC, ATL, and Qs. And that's the algorithm. Mark border cells, run BFS from both oceans, and intersect the reachability maps to get all dual ocean cells. Heights equals 1. Let's test our function using this input. This single cell represents the entire landscape. Our BFS approach starts from the Pacific, top/left, and Atlantic, bottom/right, edges, marking all reachable cells. Here, the only cell touches both oceans automatically. For example, cell 0,0 has height 1. It's on both edges, so water can flow to both oceans without moving. This output, 0,0, matches the expected result, confirming our BFS logic works even for the smallest grid. The algorithm correctly identifies cells that can reach both oceans efficiently. Let's have a quick recap. We're given a grid of heights, and we need to find all coordinates where water can flow to both the Pacific and Atlantic Oceans. Water moves from high ground to equal or lower neighboring cells, so the challenge is to identify which points can reach both sides of the map. The key insight? Instead of simulating water flowing out from every cell, we reverse the flow. We start from the oceans themselves and move inward, only climbing to equal or higher cells. This way, we explore where water could have come from rather than where it's going. 2 searches, one from the Pacific borders and one from the Atlantic, keep the logic efficient and elegant. We set up 2 visited sets, one for each ocean. From the Pacific borders, top and left, we run DFS or BFS uphill. From the Atlantic borders, bottom and right, we do the same. Finally, the intersection of those visited cells gives the positions that can flow to both oceans. We built a clean DFS helper, launched searches from each border, and collected results into both sets. The logic ran smoothly, and we executed the code on LeetCode without any errors. After running the solution, every expected coordinate appeared exactly as it should. The logic held up across all test cases, from flat terrains to complex slopes, all passing successfully. The real takeaway? Multi-source graph problems often become simpler when you flip the perspective. Think in reverse, propagate from the destinations instead of the sources, and you'll unlock a deeper intuition for reachability and flow in grid and graph challenges.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
What if your map detecting skills decided whether you got the job? Number of islands is a PatternMastery 100 must solve, and a recurring favorite at Google, Meta, and Amazon for grid DFS/BFS mastery. Over 30% of candidates get lost handling visited cells or edge cases. If you can handle this, you'll be ready for any connected component problem in an interview. Let's solve number of islands using the basic method, breaking down the problem step by step. so you can handle any matrix traversal with confidence. Given a 2D grid of ones, land, and zeros, water, count the number of islands, groups of horizontally or vertically connected land. An island is surrounded by water and is formed by connecting adjacent lands. 2D grid of characters 1, land, and 0, water, integer, total number of islands. Think about processing satellite images to count disconnected land masses, or identifying clusters in a social network or a game map. Interviewers might ask, how would you efficiently find all clusters or groups in a connectivity map? What's tricky? You must explore all connected ones for each island and ensure each cell is counted only once. Need to avoid double counting or missing isolated cells. Both DFS, recursion or stack, and BFS, queue, work, but must mark cells as visited. Loop through every cell in the grid. When you find a 1, it's a new island. Increment your count. Use DFS, or BFS, to mark all connected ones as visited, for example, change to 0 or mark in a visited set. Repeat until all cells are processed. Let's clarify. For each new one, you flood fill the island, ensuring every connected cell is covered before moving on. 4 directions per cell. Up, down, left, right, no diagonals. Edge cases. Empty grid, return 0. 1 giant island, should count as 1. Many tiny islands, single cells, count each. Initialize island count to 0. Loop through all grid cells. If cell is 1, run DFS/BFS from this cell to mark all connected ones. Increment island count, for DFS/BFS. For each cell, if in bounds and 1, mark as visited, 0 or visited set. Recurse or queue all 4 directions. Return island count. Solution 1 uses DFS to solve the number of islands problem. This comment is just a label for us humans. Creates a class solution, a container for our function counting islands in the grid. Define new islands, taking grid, a 2D list, 1 equals land, 0 equals water. Goal, count separate chunks of connected land, islands. Check if the grid is empty or missing. No data, no islands. Return 0 immediately if the grid is empty. Grab grid dimensions, m equals rows, n equals columns, for safe navigation. Initialize count to track discovered islands. Increment each time a new island is found. Define DFS, depth first search, to explore and sync land starting from I, J, so we don't count it again. Safety check, stop if out of bounds or current cell is water/already visited. Return immediately if the cell is invalid, path is water, out of bounds, or visited. Mark current land as 0 to indicate visited, preventing double counting. Explore cell below. Explore cell above. Explore cell to the right. Explore cell to the left. Together, all 4 calls fully traverse the connected island. Scan each row index I from 0 to M1. Scan each column J from 0 to N1. Double loop visits every cell once, OMN. If current cell is 1, we found unvisited land, a new island. Increment count for this new island. Call DFS to sync this island. Mark all connected land as 0, ensuring no part is counted again. Each land cell is visited once, OMN. Return count, total number of separate islands, connected 1 groups. Each cell is visited once in the double loop. DFS touches each land cell once. Time complexity, OMN. Space, recursion stack, worst case OMN. The algorithm scans the grid for new land cells, then DFS fully explores and syncs each island so it's counted exactly once. Efficient, simple, and elegant. Let's test our function. Each cell is 1 for land or 0 for water. We count islands, connected ones touching up, down, left, or right. BFS finds the first one, increments the island count, and spreads through all connected ones, turning them into 0. Here, all ones in the top 3 rows form 1 island. The rest are 0, so no new islands are found. The output is 1, matching the expected value. BFS correctly identifies and clears the entire island efficiently and reliably. Solution 2 uses BFS to count islands. This comment just labels it for clarity. Import deck from collections, a fast queue for BFS to explore neighbors level by level. Start the solution class, container for our island counting method. Define new islands, accepting a grid of ones, land, and zeros, water. Goal: count separate islands. Check if the grid is empty or missing. If no grid exists, return 0 immediately. Get grid size, m equals rows, n equals columns, for safe navigation. Initialize count equals 0. Increment when a new island is found. Loop over rows and columns. Together, these loops scan every cell once, om times n. Found unvisited land, start of a new island. Increment island counter. Sync this cell immediately to avoid recounting. Start BFS with a queue containing this cell. BFS will sync all connected land. Loop while queue has cells. Pop next cell from the front. BFS processes earliest added items first. Check all 4 directions: down, up, right, left, O1 per neighbor. Compute neighbor coordinates. Neighbor is inside grid, is land, an unvisited part of same island. Sync neighbor to prevent revisiting. Add neighbor to BFS queue to continue exploration until the island is fully sunk. After scanning and BFS syncing all islands, return count, the total number of islands. Grid scanned once, om times n. Each land cell visited once and sunk, om times n. Total, om times n. Very efficient. Algorithm scans unvisited land, then BFS explores and syncs the entire island. Efficient, simple, and elegant. Let's test our function using this case 2 grid. Each cell is 1 for land or 0 for water, and we're counting how many separate islands appear. BFS works like this. When it finds a 1, it adds +1 to the island count, then spreads through all connected land cells, turning them into 0 so they're not counted again. In this grid, BFS clears the top left island first, then it finds a single isolated one in the third row, that becomes the second island. Finally, it reaches the 2 connected ones in the last row, the third island. That matches the expected result, 3. Our BFS correctly identifies all 3 separate landmasses. Let's have a quick recap. We're given a 2D grid of land and water, and our goal is to count how many distinct islands exist. Each island is made up of connected land cells that touch horizontally or vertically. Conceptually, this problem is all about grouping and identifying isolated clusters within a matrix. The main challenge here is avoiding double counting. When we find land, we need to make sure all connected cells are explored and marked before moving on. Both DFS and BFS work here. DFS tends to feel more natural in interviews since it mirrors the flood fill idea. The trick is systematic marking. Once a cell is visited, we never process it again. We loop through every cell in the grid. When we hit a 1, that's the start of a new island, so we increment our counter. From there, we trigger a DFS or BFS that explores all connected land, marking each as visited or converting it to water. Once that's done, we continue scanning the grid until all cells are processed. We structured our DFS cleanly, checking boundaries, marking visited cells, and exploring 4 directions from each one. The entire process ran seamlessly on LeetCode, and the code executed without any errors. After running the solution, every test case passed perfectly. From empty grids to single massive islands, the logic held up, no missed cases, no overlaps, all outputs matched expectations. The key takeaway: mastering grid traversal and marking visited cells is the foundation for countless graph problems. Once you can flood fill confidently, you can handle any connectivity or component counting challenge an interviewer throws your way.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com. Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Have you ever tried to find someone's longest streak of daily activity from a messy log? That's exactly what LeetCode's longest consecutive sequence asks. One of the PatternMastery 100 essentials, and a problem that stumped even experienced engineers at companies like Google, Netflix, and Facebook. In interviews, getting this ON trick is a game changer. Let's apply the basic approach. A strategy broader than STAR because it's designed for breaking down technical challenges and system designs, not just behavioral questions. We're given an unsorted array of integers and asked, what's the length of the longest run of numbers that appear consecutively, regardless of order? For example, 100, 4, 200, 1, 3, 2, yields, 1, 2, 3, 4 length, 4. Edge cases? Handle empty arrays, negatives, duplicates, anything the interviewer throws at you. Suppose you're designing a fitness app. You get a list of dates a user logged workouts. How do you instantly show their longest streak, no matter the order the logs came in? This problem is exactly that challenge. If you sort and count, you get on log n. Good, but not great. The best solution uses a hash set for O1 lookups and only starts streaks at the true beginning of each run. Num, 1 isn't present. That way, you never double count or waste work, making the algorithm on. Add all numbers to a set so we can check for any number in constant time. For each number, only start counting a sequence if there's no smaller number in the set. Count up from each streak start, tracking how long the run goes. Update the max streak found along the way. Return the result. Let's walk through the logic as if we're coding together. Let's implement solution 1. This comment shows we're solving longest consecutive sequence by sorting and scanning once. This line starts our solution class, the container for our method. Here we define longest consecutive, which takes nums. Our goal is to find the longest chain of consecutive numbers like 1, 2, 3, 4. This checks if the list is empty. If there are no numbers, there's no consecutive sequence, so we return 0. One-liner, set nums removes duplicates, sorted, orders them. Sorting places consecutive values together, making detection easy. On log n. We create longest to store the best streak so far. Starts at 1. We create current to track the streak we're building. We loop through the sorted list from index 1 and compare each number to the previous. This loop is on. This checks if the current number continues the consecutive chain. If it continues, we increase the current streak. If it does not continue, we reset the streak. Before resetting, we update longest if current was bigger. We reset current to 1 to start a new streak. After the scan, we return max longest, current, since the longest streak may end at the last element. And that's the algorithm: remove duplicates, sort, then scan once to track consecutive streaks. Let's test our function using this input. These numbers are scattered on the number line, and our goal is to find the longest chain of consecutive values like 1, 2, 3, 4. Why the solution works. We first sort and deduplicate the list, turning it into 2, 3, 4.100, 200. Now consecutive numbers sit next to each other. The algorithm scans and builds streaks. 1, 2, 3, 4 gives a streak of 4. Then the chain breaks at 100, starting a new streak. 100 and 200 have no consecutive neighbors, so the longest streak is 4. And that's exactly what our program outputs, 4. This matches the expected result and confirms our scan found the longest chain. So our implementation is correct. It sorts the values, tracks streaks efficiently, and identifies the longest run of consecutive integers. Now let's try another implement approach using solution 2. This version uses a hash set to check whether numbers exist and to identify where each consecutive sequence begins. This line defines our solution class, a structured home for our method. Here we define longest consecutive, which takes a list of integers called nums. Our goal is the same: find the longest streak of consecutive numbers like 5, 6, 7, 8. This converts the list into a set. A set removes duplicates and gives O1 lookups, which our strategy depends on. We create longest to track the longest streak we've found so far. Now we loop through each unique number in the set. This loop is on because the set contains unique integers. This line is the key insight. We only build a sequence if the current number is the start. If num 1 isn't in the set, nothing comes before it. Example, 4, 1, 2, 3, 4. We only start at 1 because 0 isn't there. We set length to 1 since any number alone counts as a sequence. We use current to track the value as we extend the streak forward. This loop checks if the next number exists. If current equals 5, it checks 6, then 7, then 8. Set lookups are O1, so extending sequences is fast. We move to the next consecutive number, and we increase the streak length. After finishing this sequence, we update longest if needed. We return the longest consecutive sequence length. Time complexity is on because each number is processed once, each sequence is walked once, and set lookups are constant time. And that's how this algorithm works: load numbers into a hash set, identify true sequence starts, and walk each chain forward. Efficient, simple, and elegant. Let's test our function using this input. These numbers are unsorted integers, and we want the longest chain of consecutive values with no gaps. Here's why the solution works. The algorithm stores all numbers in a hash set for fast lookups. Then it only starts a sequence from numbers that look like the first in a chain. For example, 0 starts a sequence because -1 is not in the set. From there it checks. Is 1 in the set? Yes. Is 2 in the set? Yes. Is 3 in the set? Yes. Is 4 in the set? Yes. Is 5 in the set? Yes. Is 6 in the set? Yes. Is 7 in the set? Yes. Is 8 in the set? Yes. Is 9 in the set? No. Sequence stops. That gives us a streak of 9 numbers in a row. 0, 1, 2, 3, 4, 5, 6, 7, 8. No other number forms a longer chain, so the maximum length is 9. And that's exactly what our program outputs, 9. This matches the expected result and confirms the algorithm correctly found the longest consecutive sequence. So, our implementation is correct. The algorithm identifies sequence starting points and expands them efficiently to compute the longest chain. Let's have a quick recap. We're given an unsorted list of numbers, and we need to find the longest run of consecutive integers, no matter the order. Conceptually, it's about identifying sequences within disorder, finding those hidden streaks that form continuous ranges. It's a perfect test of both logic and efficiency. A sorted approach works but costs O(n) log n. To do better, we use a hash set for constant time lookups and start streaks only when we see the beginning of a sequence, meaning, when num1 isn't in the set. This clever shortcut prevents wasted work and achieves true O(n) performance. The logic flows like this. Add every number to a set for O(1) lookups. For each number, check if it's the start of a sequence. If it is, count upward until the streak ends. Keep track of the longest streak found. At the end, return the maximum streak length. We built this logic step by step, ensuring each number was visited only when necessary. The code ran cleanly and efficiently. We successfully executed it on LeetCode without any errors. We tested across various cases, scattered numbers, duplicates, negatives, even empty arrays. Every test passed perfectly, and the logic held up across all scenarios. The key takeaway? True optimization isn't about fancy syntax, it's about seeing structure where others see randomness. Once you understand how to detect starting points, you can handle any streak, sequence, or continuity problem with total confidence.
This is not another random playlist. It is a roadmap, patterns, structure, repetition. The stuff that actually sticks. PatternMastery.com.
Imagine you're decoding an alien language with only a list of sorted words. Can you reconstruct the whole alphabet? Alien Dictionary is a PatternMastery 100 super challenge. Regularly asked at Google, Meta, and Amazon to test your grasp of graph theory, topological sorting, and string manipulation. Over 40% of candidates either miss edge cases or get tangled in cycle detection. Master this, and you'll shine on advanced ordering problems. Let's break down Alien Dictionary using the basic method, giving you a foolproof plan for any graph-based string ordering challenge. Given a list of words sorted according to an unknown alphabet, return a string representing the alphabet's order. If no valid order exists, cycle, return. List of words, all lowercase letters, possibly with overlaps and missing letters, a string of characters, the alien alphabet order, or if invalid. Suppose you're designing a search tool for a new language, or analyzing a secret code with custom rules. An interviewer might ask, how would you deduce task dependencies from log order, or infer a dictionary structure from partial data? What's tricky? You need to infer order constraints between letters by comparing adjacent words. Must detect cycles. If two letters are required to come before each other, there's no valid order. Not all letters may be present in the input, and some may be missing from certain orderings. Build a graph. Each unique letter is a node. For every pair of adjacent words, find the first position where they differ. That's a precedence constraint. Edge. Topological sort. Apply Kahn's algorithm, BFS, or DFS to produce a valid order. Use an in-degree map to track how many incoming edges each node has. Add nodes with 0 in degree to the result. Decrease in degree as edges are used. Cycle detection. If at the end, you haven't used all letters, result is shorter than unique letters, there's a cycle. Let's clarify. If a word is a prefix of another but comes later, it's invalid. For example, ABC, AB. All letters in words must appear in the output. Edge cases. Empty word list. Return. Words with same prefix. Skip until the first difference. Cycle in constraints. Return. Initialize a graph, adjacency list, and in degree dictionary for all unique letters. Compare each pair of adjacent words. For each character, find the first mismatch. Add an edge from char 1 to char 2. Char 1 comes before char 2. If one word is a prefix of the other and is longer, return. Topological sort. Add all nodes with 0 in degree to a queue, while queue isn't empty. Pop from queue, append to result. Decrease in degree for neighbors. If in degree becomes 0, add to queue. If result length equals the number of unique letters, return as a string. Otherwise, return cycle or invalid input. Let's implement solution 1. This comment tells us we're solving alien dictionary using a graph plus topological sort with BFS. This imports default dict for the adjacency list and dec for fast BFS queue operations. This starts our solution class, the container for our function. We define alien order, which takes words sorted by an unknown alien alphabet. Our goal is to reconstruct that letter order. This initializes in-degree for every character in all words. Each letter starts at 0 incoming edges, so every character appears in the graph. This is O total characters. This creates the adjacency list. Each character stores the set of letters that must come after it. A set avoids duplicate edges. This compares each pair of consecutive words to extract ordering rules. We compute the shorter length, so we only compare up to that point. This detects an invalid case. The longer word comes first but starts with the shorter word, like ABC before AB. That ordering is impossible. If this happens, we return an empty string immediately. We compare characters one by one, looking for the first difference. When we find differing letters, C1 must come before C2. If that rule isn't already added, we add the edge C1 C2 and increase in degree of C2. We break because only the first differing pair defines the order. This builds the BFS queue of all characters with no prerequisites, the possible first letters. We create a list to store the final alien letter order. Start BFS. We process characters with in degree 0 first. We pop a character. This letter goes next in the alphabet. We append it to the final ordering. We check all letters that depend on C. We reduce their in degree because one requirement is cleared. If a neighbor now has no prerequisites, we add it to the queue. This ensures we used all characters. If not, a cycle exists and we return an empty string. Otherwise, we join and return the alien alphabet order. And that's how the alien dictionary algorithm works. Build ordering rules, then use topological sorting to reconstruct the alphabet. Efficient, simple, and elegant. Let's test our function using this input: WRT, WRF, ET, RFTT. These words are sorted using an alien alphabet, not English. Our task is to recover the letter order that makes this list valid. Here's why the solution works. The algorithm compares each adjacent pair of words to extract ordering rules. Comparing WRT versus WRF, T versus F is the first difference. T comes before F. Comparing WRF versus W versus E differs immediately. W comes before E. Comparing versus ET, R versus T differs. R comes before T. Comparing ET versus RFTT, E versus R differs. E comes before R. From these rules we get. Chaining them gives the alien order, WERTF. And that's exactly what the program outputs, WERT. It satisfies all the inferred rules and matches the expected result. So, the implementation is correct. It reconstructs a valid alien alphabet efficiently and accurately. Now let's try solution 2. This comment tells us we're solving alien dictionary using DFS with topological sorting instead of BFS. This imports default dict, which lets us build an adjacency list where each key starts with a default set. This starts our solution class, just a container for alien order. This defines alien order, which takes words sorted by an unknown alien alphabet. Our goal is to recover that letter order. We create adjective, a graph where adjective C holds all characters that must come after C. Using a set avoids duplicates. This collects all unique characters from all words, ensuring every letter appears in the graph even with no edges. We loop over consecutive words to extract ordering rules. We compare only up to the length of the shorter word. This checks the invalid case, a longer word appearing before its exact prefix, like ABC before AB. In that scenario, we immediately return an empty string. No valid alphabet exists. We compare characters until we find the first difference. That first differing pair gives us the rule, C1 comes before C2. So we add the edge C1 C2. We break because only the first difference matters. We set up a state map to track DFS progress. 0 equals unvisited, 1 equals visiting, 2 equals done. This lets us detect cycles. We prepare order to store characters in post order. A flag to mark if a cycle is detected. We define the recursive DFS function. If the graph is already invalid, stop immediately. If we revisit a visiting node, that's a cycle. We mark the graph invalid and return. If C is fully processed already, skip it. Return to avoid rework. Otherwise, mark C as visiting. We explore all characters that must follow C. We DFS into each neighbor. After exploring all neighbors, mark C as done and append C to the post order list. We now run DFS on each character. If unvisited, start DFS. Perform DFS from C. If a cycle was detected, return empty string. Otherwise, reverse the post order list and return it as the alien alphabet. DFS records letters after processing dependencies, so reversing gives the correct topological order. And that's how the DFS-based alien dictionary works, building a directed graph from word comparisons, detecting cycles, and performing topological sorting to produce a valid letter order. Let's test our function using this simple input, z, x. These words are sorted by an alien dictionary, and we want to recover the letter order. Here's why the solution works. Comparing z and x, the first and only characters differ. Z must come before x, so the graph has one rule, zx. DFS checks for cycles, finds none, and outputs the topological order. Reversing the post order gives a valid alien alphabet. And that's exactly what our program returns, zx. It matches the expected answer, confirming the DFS plus topological sort logic is correct. So the implementation works as intended, clean, accurate, and reliable. Let's have a quick recap. We're given words sorted in an unknown alphabet, and our job is to reconstruct that alphabet's order. Conceptually, every unique letter is a node in a graph, and the order between letters is inferred by comparing pairs of adjacent words. Wherever the first mismatch occurs, that's a directional edge showing which letter comes before another. The main challenge lies in building the right relationships and detecting cycles. A valid order exists only if the graph has no cycles. We use topological sorting to determine that order, either through Kahn's algorithm, BFS, or DFS. Handling prefix conflicts and missing letters is key to getting it right. Here's the logical plan. Build a graph of all unique letters. Compare every pair of adjacent words to extract edges. Track in degrees for each letter. Run a topological sort, adding 0 in degree nodes to a queue, removing them one by one, and reducing in degrees of their neighbors. If all letters are processed, we have a valid alphabet. If not, there's a cycle, and we return an empty string. We constructed the graph, established edges between characters, and executed Kahn's algorithm cleanly. The program ran successfully on LeetCode without any errors, producing valid alphabet orders for all non-cyclic cases. We verified the solution against various tests, valid dictionaries, invalid prefix cases, and cyclic dependencies, and every scenario behaved exactly as expected. All test cases passed. The key takeaway? Alien Dictionary teaches you how to think in dependencies, how local comparisons build global order. Once you master graph construction and cycle detection, problems that seem alien at first will start to feel like familiar territory.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
Ever need to check if a network is robust, fully connected, and loop-free? Graph Valid Tree is a PatternMastery 100 favorite, used by Google, Apple, and Meta to test your core understanding of graph cycles and connectivity. Over 30% of candidates get tripped up on edge cases like cycles or disconnected graphs. Master this and you'll breeze through network design and validation problems. Let's break down Graph Valid Tree with a basic method, ensuring you can confidently tackle any connectivity or acyclicity question in interviews. Given n nodes labeled 0 to n1 and a list of undirected edges, determine if these edges form a valid tree. A valid tree is connected. There's a path between every pair of nodes. Acyclic, no cycles. Integer n, number of nodes, list of undirected edges. Boolean, true if the graph forms a valid tree, false otherwise. Imagine verifying a computer network or electrical grid, no redundant paths, cycles, but every device must be connected. An interviewer might ask, how would you validate that a topology is a tree and not a forest or a cycle? What's tricky? Must check both connectedness and absence of cycles. Some solutions miss edge cases, disconnected graphs, or graphs with exactly one cycle. For a tree, exactly n1 edges for n nodes. Edge count check, if there aren't exactly n1 edges, it can't be a tree. Connectedness check, use DFS/BFS to visit all nodes from node 0. If you visit all nodes, count equals n, the graph is connected. If any node is unreachable, it's disconnected. Cycle check, if any edge leads back to a previously visited node, not the parent, it's a cycle. Edge count shortcut, if the edge count is correct and you visit all nodes without cycles, it must be a tree. Let's clarify. Using union find, disjoint set union, DSU, is also common. Detects cycles as you add edges and checks if all nodes are ultimately connected. Edge cases. Disconnected components. Not a tree. Extra edges, more than n1, must have a cycle. Single node, n equals 1, edges equals 0, valid tree. Edge count, return false if len edges, equals n1, DFS/BFS. Build adjacency list from edges. Start from node 0, mark nodes as visited. If during traversal, revisit a node that's not the parent, it's a cycle, return false. After traversal, check if all nodes are visited, connected. Return true if no cycles and all nodes visited. Solution, BFS plus edge check. Let's try to implement it using solution 1. Imports deck for fast BFS. Defines our solution class. Starts the method that checks if the graph forms a valid tree. A tree must have exactly n1 edges. If not, it's immediately not a tree. Build an adjacency list for all nodes. Loop through edges. Add v as neighbor of u, and add u as neighbor of v, undirected. Tracks visited nodes. Start BFS from node 0. Mark it visited. Standard BFS loop. Pop next node. Check its neighbors. Only explore unvisited ones. Mark visited. Push to queue. If BFS reached all nodes, the graph is connected, with n1 edges. That makes it a valid tree. The algorithm checks the edge count, then uses BFS to confirm full connectivity, clean, fast, and reliable. Let's run our function on this test case. We have 5 nodes, 0 to 4, and edges showing how they connect, basically the roads in the graph, explaining the input. Edges like 0, 1, 0, 2, and 0, 3 show that node 0 links to 3 others, acting as the hub. Then, 1, 4 connects node 1 to node 4. With n equals 5, a valid tree needs 4 edges, and we have exactly 4, so that part checks out. Walking through the algorithm. BFS starts at node 0. It quickly discovers 1, 2, and 3, and from node 1 it reaches 4. By the end, all 5 nodes are visited. Since the edge count is correct and the graph is fully connected with no cycles, it satisfies the definition of a valid tree. That's exactly what the program returns, true. And the expected answer is also true. Our implementation works correctly. The algorithm confirms this graph is a valid tree, connected, cycle-free, and complete. Now let's try another implement approach using solution 2. We start by defining class solution, a container for valid tree. Define valid tree n, edges. Goal. Decide if edges form a valid tree over n nodes. Quick check. A tree with n nodes must have exactly n-1 edges. If not, return false immediately. Initialize parent so each node is its own parent. Each node is its own set. Initialize rank, approximate tree height, to keep unions balanced. Define find x to return the root parent of x. Walk up until x equals its parent, that finds the root. Path compression. Point x to its grandparent to flatten the tree for faster future finds. Move x one step toward the root. Continue the loop. Return the root of x's set. Define union x, y. To merge sets containing x and y, detect cycles. Find root parents rx and y for x and y. If roots are equal, x and y are already connected. Adding this edge creates a cycle. In that case, return false to indicate a cycle was found. If rx's tree is shorter, attach rx under y to keep trees shallow. Make y the parent of rx, attach smaller under larger. If rx's tree is taller, attach y under rx. Make rx the parent of y. If ranks are equal, choose one root and increment its rank. Attach y under rx when ranks tie. Increase rx's rank because its tree grew one level. Union succeeded without creating a cycle. Loop through all edges. There are n-1 of them due to the earlier check. Try to union the endpoints. If union returns false, a cycle exists. If a cycle is detected, return false immediately. If all unions succeed and edge count was correct, return true. It's a valid tree. Time complexity. Build parent and rank. On process edges. On each union/find. Almost O1 amortized. Total. On. Union find efficiently connects nodes, detects cycles, and confirms the graph is a valid tree. Efficient, simple, and elegant. Let's test our function with this input. We have 5 nodes, 0 through 4, connected as shown in edges. Connections like 0, 1, 1, 2, 2, 3, 1, 3, and 1, 4 form a small network. Notice that 1, 3 creates a cycle in the structure. The union find algorithm checks. Edge count. A tree with 5 nodes must have exactly 4 edges. This input has 5, already too many. Cycle detection. The union operation finds that adding 1, 3 connects nodes already in the same group, creating a cycle. Since either condition fails, the graph cannot be a valid tree. Our program outputs false, which matches the expected result. The algorithm correctly identifies that this graph is not a tree. It has a cycle and too many edges. Let's have a quick recap. We're given n nodes and a list of undirected edges. The task is to decide whether these edges form a valid tree, meaning the graph is both connected, every node reachable, and acyclic, no loops. If it passes both, it's a tree. If not, it's just a network with issues. The tricky part? Balancing two conditions at once, ensuring all nodes are connected without accidentally introducing cycles. Many candidates forget the edge rule. A valid tree must have exactly n1 edges. From there, the challenge becomes verifying that all nodes can be reached and that no back edge creates a loop. Here's how we planned it. Edge count check. If edges does not equal n1, return false immediately. Build adjacency list. Represent all node connections. DFS or BFS traversal. Start from node 0, visiting neighbors while skipping the parent node. Cycle detection and connectivity. If we revisit a node that isn't the parent, it's a cycle. After traversal, if we visited all nodes, the graph is connected and valid. We implemented the traversal, marked visited nodes, and avoided false cycle triggers by tracking parents. The logic executed smoothly, and the solution ran successfully on LeetCode without any errors. We validated against multiple scenarios, perfect trees, disconnected graphs, and cyclic ones. Every test case passed, confirming that the algorithm correctly identifies valid trees. The takeaway? Every tree problem is a lesson in structure. One path between any 2 points, no more, no less. Once you can balance connectivity with acyclicity, you'll have mastered one of the most universal principles in graph theory and system design.
LeetCode says medium. Your nervous system says boss fight. That is your sign you need pattern training. PatternMastery.com.
Can you map out all the islands in a complex network? Number of connected components in an undirected graph is a PatternMastery 100 essential. Frequently asked at Google, Facebook, and Amazon to test your ability to traverse graphs and count isolated clusters. Over 30% of candidates overlook singleton nodes or double count connections. Master this, and you'll be equipped for any graph or network connectivity problem. Let's solve number of connected components in an undirected graph using the basic method, so you never miss a node or count. Integer n, number of nodes, list of undirected edges. Integer, total number of connected components. Imagine mapping isolated local networks in a city, or identifying separate user groups in a social app. An interviewer might ask, how would you count all the isolated clusters in a computer network or database? What's tricky? Need to visit every node, even those with no connections, singleton components. Must avoid double counting, mark each node as visited as you explore. Both DFS and BFS work well here. Union find, DSU, is great for optimizing. Build an adjacency list from the edge list. Initialize a visited set or array. Loop through all nodes 0 to n1. If a node isn't visited, it's the start of a new component. Increment the count. Run DFS/BFS from that node, marking all reachable nodes as visited. Continue until all nodes are visited. Let's clarify. Single nodes with no edges count as their own components. Each DFS/BFS call finds exactly one component. Edge cases. Disconnected graph, multiple clusters. All nodes connected, one component. No edges, all singletons. Build an adjacency list from edges. Initialize a visited set or array. For every node from 0 to n1. If not visited, increment components count. Run DFS/BFS to mark all reachable nodes as visited. Return components count. Let's implement solution 1. Create a class solution to hold our method. This function counts connected components in a graph with n nodes and edges. Build an adjacency list. Each node maps to its neighbors. Loop through edges and add connections both ways since the graph is undirected. Set to track visited nodes. Counter for connected components. DFS helper to explore nodes in a component. Stack starts with the current node. While nodes remain to explore, pop a node and check its neighbors. Mark unvisited neighbors and add them to the stack. Go through each node. If unvisited, start DFS and count a new component. Increment components after exploring a full group. Return the total number of connected components. DFS explores each component fully, giving an accurate count efficiently. Efficient, simple, and elegant. Test input, 5 nodes, 0 to 4, with edges showing direct connections. what the input represents. 0, 1, and 1, 2 form one group. 0, 1, 2. 3, 4 forms a separate group. 3, 4. So, there are clearly two components. Why the solution works. DFS explores each node. Starts at 0, visits 1, 2, covering the first group. Moves to 3, visits 4, covering the second group. Each new DFS marks a new connected component. Program outputs 2, matching the expected result. DFS correctly counts connected components efficiently and accurately. Let's try solution 2. Union find, disjoint set. Define a solution class for the function. Returns the number of connected components in a graph with n nodes and edges. Each node starts as its own parent. Tracks tree height to keep unions efficient. Finds the root parent of x with path compression for efficiency. Merges sets containing x and y. Returns false if already connected, true if merged. Start with n separate components. Try to union each edge. If successful, decrement components. Return the remaining number of connected components. Time complexity. O(n plus e), initializing parent/rank is O(n), unions with path compression nearly O(1) per edge. Union find starts with each node as its own component, merges groups via edges, and efficiently counts remaining components. Simple, fast, and reliable. Test input. 5 nodes with edges, 0, 1, 1, 2, 2, 3, 3, 4. Each pair shows a connection between two nodes. All nodes are connected in a single chain. 0, 1, 2, 3, 4. There are no separate groups, so the graph forms one connected component. Why the solution works. Union find starts with 5 components, each node alone. Processing edges. 0, 1, merges 0 and 1 components. 4. 1, 2, merges 1 and 2 components. 3. 2, 3, merges 2 and 3 components. 2. 3, 4, merges 3 and 4 components. 1. No cycles detected, all unions succeed. Program outputs 1, matching the expected result. Union find correctly counts connected components, efficient, accurate, reliable. Let's have a quick recap. We're given n nodes and a list of undirected edges. A connected component is a maximal group where every node is reachable from any other. The goal: return how many such components exist, including single, isolated nodes. The challenges are thorough coverage and no double counting. We must visit every node, even those with no edges, and ensure once a node is explored, it isn't counted again. DFS or BFS handles traversal cleanly. Union find, DSU, is an efficient alternative for merging connections. Plan of attack. Build an adjacency list from the edges. Keep a visited set/array. Scan nodes 0 to n1. When we find an unvisited node that starts a new component, increment the count and explore all reachable neighbors. Continue until all nodes are processed, then return the count. We followed that flow. Constructed the graph, ran DFS/BFS from each unvisited node, and marked nodes as visited to avoid repeats. The solution executed on LeetCode smoothly with no errors. We verified correctness by running through disconnected graphs, fully connected graphs, and cases with no edges. The logic behaved as expected and passed all LeetCode test cases. The core lesson: systematic traversal plus careful visited tracking turns complex networks into clear counts. Master this pattern, and you'll breeze through connectivity problems across graphs, maps, and real-world systems.
The interviewer smiled. Not because you were right, because they knew you were lost. Learn to spot the pattern before they spot the panic. PatternMastery.com.
Minimum height trees looks innocent, until you try every root and blow up to O(n squared). Bong interviewers love this because the optimal trick is stunningly simple. Peel the tree from the outside in until 1 to 2 centers remain. Master this, and you'll be ready for graph center/diameter problems on the spot. Let's attack it with basics. We're given n nodes labeled 0, n1 forming a tree, connected, acyclic, and an edge list. We need all node labels that can be roots producing minimum height. A tree's minimum height roots are exactly its centers, 1 or 2. Brute force, run BFS/DFS from each node to compute height O(n squared). Instead, observe, if we trim leaves layer by layer, like topological sorting, the last 1 to 2 nodes left are the centers. Why? Because removing leaves doesn't change centers. We're shrinking toward the core. Complexity. O(n time and O(n space. Handle tiny cases. If n less than or equal to 2, return 0, n1. Build an adjacency list and a degree array. Initialize a queue with all leaves, degree 1. While more than 2 nodes remain, pop current leaves, reduce neighbor degrees, and collect new leaves. Return the last batch of nodes in the queue. They're the centers. Now let's solve solution 1 for the minimum height trees problem. This time, we'll use a technique called topological trim, also known as peeling the leaves. I'll walk you through the idea first, then explain the entire code line by line in simple and clear language. Time complexity is O(n), where n is the number of nodes in the tree. We visit every node and every edge only once. The idea of topological trim. A tree's center is where the minimum height tree will be rooted. Leaves are nodes with only one connection. If you remove all leaves at once, new leaves will appear. You keep peeling off layers of leaves until only 1 or 2 nodes are left. Those nodes are the centers of the tree. Why 1 or 2 nodes? Because a tree can have 1 center, odd length path, or 2 centers, even length path. Line-by-line explanation of the code. We import dec, which gives us a fast queue, perfect for processing leaves layer by layer. We define our solution class. This function will return the list of nodes that form minimum height trees. If there are no nodes at all, the answer is just an empty list. So we return an empty result. If there's only 1 node, it's trivially the center of the tree. We return node 0 as the only possible root. We build an adjacency list for the graph. Every node maps to a set of its neighbors. We create a degree list that stores how many connections each node has. We loop through every edge in the tree. We add each node to the other's neighbor list. Trees are undirected, so the connection works both ways. We increase the degree count for both nodes. This helps us identify which nodes are leaves. We gather all nodes with degree 1. These are our initial leaves. Then we place them in a queue so we can peel them off layer by layer. We track how many nodes are still in the tree. We keep peeling leaves until only 1 or 2 nodes remain. Those last nodes are the tree's centers. We count how many leaves there are in this round. We remove all current leaves from the total number of nodes. We process each leaf one by one. We take the next leaf out of the queue. We look at every neighbor connected to this leaf. We wrap it in a list so we can safely modify the graph. We remove the leaf from its neighbor's adjacency list. We decrease the neighbor's degree because it lost 1 connection. If the neighbor becomes a leaf after trimming, we add it to the queue for the next peeling around. When only 1 or 2 nodes remain, these nodes are the tree's centers. We return them as the roots of the minimum height trees. And that's how this algorithm works. It first builds the graph and counts degrees, then repeatedly peels off the outer leaves until only the center remains. Efficient, simple, and elegant. Trees with 1 center produce 1 minimum height tree. Trees with 2 centers produce 2 possible roots. Peeling leaves works because height is minimized at the tree's center. This method is linear, O(n), since each node and edge is touched only once. Now that we've implemented our solution to find the minimum height trees, it's time to test it with an actual input. This helps us see how the algorithm trims leaves from the tree level by level to identify the root nodes that produce the minimum height. We'll walk through the input, observe how the leaves are removed, and confirm that the output matches the expected result. Let's test the function using this input. We have n equals 4, representing 4 nodes labeled from 0 to 3, and an edges array defining the connections between them. This tree structure forms a star centered at node 1, which connects to nodes 0, 2, and 3. Here's why the solution works. The algorithm builds a graph and counts the degree of each node. It then identifies the initial leaves, which are nodes with only 1 connection. 1 layer at a time, it removes these leaves and updates the degrees of their neighbors. This process continues until at most 2 nodes remain. Those remaining nodes are the roots of the minimum height trees. For this example, the initial leaves are 0, 2, and 3. After trimming them, only node 1 remains, which is the root of the minimum height tree. And that is exactly what the program outputs. 1. This verifies that the code works correctly and passes this test case. So our implementation is correct. The algorithm successfully identifies the center nodes that minimize the height of the tree. It handles the given structure accurately and returns the expected output. The BFS-style trimming ensures efficiency and guarantees that the minimal height roots are found. Now let's solve solution 2, finding the minimum height trees by identifying the middle of the tree diameter. We'll use BFS to find the farthest nodes, reconstruct the diameter path, and pick the middle nodes as optimal roots. Time complexity is O(n), where n is the number of nodes in the tree. BFS is performed twice, and path reconstruction is linear. We import deck to efficiently perform BFSQ operations. We define a class solution to hold our method. The function findMinHeightTrees returns the roots of minimum height trees given n nodes and edges. If there are only 1 or 2 nodes, all nodes are MHT roots. Build an adjacency list for the tree. Each node stores its neighbors. Define a helper BFS function that tracks visited nodes, uses a queue, keeps the farthest node, and remembers parents for path reconstruction. Perform BFS. For each node, explore neighbors, mark them visited, record the parent, and update the farthest node. Return the farthest node in parent dictionary. Start BFS from node 0 to find one endpoint of the diameter. Perform BFS again from that node to find the other endpoint and record parent pointers for path reconstruction. Reconstruct the path from node Eb back to Nadia using parent pointers. This path is the tree diameter. Return the middle nodes of the path. If the length is odd, return 1 node. If even, return 2 nodes. These are the minimum height tree roots. BFS is performed twice. Reconstructing the path takes O(n) time. The middle nodes ensure minimum height for the tree. Before checking the output, let's understand the problem. We are given n equals 6 nodes, edges equals 3, 0, 3, 1, 3, 2, 3, 4, 5, 4. The goal is to find all roots of minimum height trees, nodes that produce the smallest height when chosen as tree roots. Let's test our function with this input. Here, we have a tree with 6 nodes, connected as described by the edges. Here's why the solution works. Build the graph. Represent nodes as adjacency lists. Use BFS to find tree diameter. First BFS from any node. Here, node 0, finds one endpoint of the diameter, Nadia. Second BFS from Nadia finds the other endpoint, node Eb, and keeps track of parent pointers to reconstruct the path. Identify middle nodes. The diameter path is the longest path in the tree. Nodes in the middle of this path are the roots of MHTs. If the path length is even, there are 2 middle nodes. If odd, 1 middle node. Step by step with this input. BFS from 0 farthest node is 5, BFS from 5 farthest node is 3, diameter path, 5, 4, 3, 0, or similar middle nodes, 3, 4. These nodes will produce minimum tree height when chosen as roots. And that is exactly what the program outputs, 3, 4. This confirms our code works correctly for this test case. So, our implementation is correct. It successfully identifies MHT roots, efficient, accurate, and reliable. Our implementation is correct. It accurately finds the diameter of the tree. It correctly identifies middle nodes as MHTs. Let's wrap up the minimum height trees problem. At first, it seems like you just need to pick the best root, but trying every node quickly explodes into O(n)². The clever trick here? We don't search from the roots outward, we peel the tree inward. Breakdown recap. We're given n nodes forming a connected, acyclic graph, a tree. Our goal is to find all possible root nodes that produce the minimum height when the tree is rooted there. In simple terms, we're looking for the tree's centers, the points that minimize the longest path to any leaf. Assess recap. The brute force approach would be to run BFS or DFS from every node to measure height, but that's too slow. Instead, we realize that the tree's centers can be found by trimming leaves layer by layer, just like peeling an onion. Each round, we remove the outermost leaves until only 1 or 2 nodes remain, which are the centers of the tree. Structure recap. We handled small cases first. If there are 2 or fewer nodes, we just return all of them. Then we built an adjacency list and tracked the degree of each node. Next, we added all current leaves to a queue, and while more than 2 nodes remained, we kept removing those leaves, updating their neighbors, and collecting new ones as they appeared. The final remaining nodes are our centers. Implement recap. After coding this peeling logic, we ran it on LeetCode, and the solution executed smoothly without any errors. Check recap. We verified it across multiple test cases, and each time, the output correctly identified the minimum height tree roots. Closing insight. The big lesson? Sometimes, finding the center of a problem means working from the outside in. By trimming layer by layer, we let the structure reveal its own core, efficiently, cleanly, and in linear time.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Have you ever heard that reversing a linked list is the fundamental question in any software engineering interview? Reverse linked list is a true Pattern Mastery 100 staple and frequently shows up at Facebook, Google, and Amazon. Missing this? You're out. Over 40% of candidates get tripped up by edge cases here. Let's guarantee you're not one of them. Let's attack reverse linked list using the basic problem-solving framework, which brings structure and confidence to every interview challenge. Ready? Here we go. Given the head of a singly linked list, our goal is to reverse the list so the nodes point in the opposite direction, and return the new head. Input: head node of a singly linked list, like 1, 2, 3, 4, 5, null. Output: head node of the reverse list, for example, 5, 4, 3, 2, 1. Think about undo operations in text editors. Each action is stored in a list, but when you undo you need to traverse those actions in reverse order. How do you efficiently reverse that structure? Interviewers might even ask, how would you print a linked list in reverse order, or reverse a playlist queue? What makes this tricky? You can't just flip pointers all at once. You need to avoid losing your place in the list. Naive mistake. If you just set node.next equals prev without remembering the next node, you lose the rest of the list. Think step by step. We'll traverse the list with a current pointer. For each node, we'll save the next node, so we don't lose it. Reverse the current node's pointer to point to the previous node. Move the previous and current pointers forward. Let's go even deeper. Imagine you're physically turning each train car around on a track. If you detach a car without remembering where the next is, you'll derail. That's why you always store the next node before changing any links. Edge cases? Empty list, head equals null. Single node, should return the same node. Classic multi-node lists. Here's the plan. Initialize 2 pointers, prev equals null, cur equals head. Loop while cur is not null. Store next equals cur.next. Reverse, cur.next equals prev. Move forward. Prev equals cur equals next. When done, prev is the new head. Now let's solve solution 1, reversing a linked list using the iterative approach. We'll walk through each line, understand how pointers move, and see how the list gets reversed step by step. Time complexity is O(n), where n is the number of nodes in the linked list. We visit each node exactly once. The idea of iterative reversal: use 3 pointers. Priv tracks the node before current cur. The current node being processed nxt temporarily stores the next node. Walk through the list node by node. Reverse the next pointer of each node so it points to the previous node. Move all pointers forward. At the end, prev will be the new head of the reversed list. Think of it like flipping the arrows of a train track, one car at a time. Line by line explanation of the code. We define a class solution to hold our method. This function takes head, the first node of the linked list, and returns the new head after reversal. Prev will track the previous node. At the start, there's no previous node, so it's set to none. Cur points to the current node we are processing, starting with the head. We loop as long as cur is not none. We stop when we reach the end of the list. We store the next node in nxt temporarily. This is important because we are about to change cur.next. Here we reverse the pointer. The current node now points backward to prev. Think of it as flipping the arrow on this node. We move prev forward. It becomes the current node. This keeps track of the new head as we progress. Move cur to the next node in the original list, stored in nxt. This advances the loop. At the end, prev points to the new head of the reversed linked list. We return it as the result. And that's how this algorithm works. It first initializes pointers, then iteratively flips each node's next pointer while moving forward through the list. Efficient, simple, and elegant. Time complexity is O(n), as we visit each node once. Space complexity is O(1), because we only use a few pointers. The iterative method is easy to visualize and memory efficient. The key is carefully storing the next node before changing pointers. Now that we've implemented our reverse list function, let's see how it works with a sample linked list. This test will show if the function correctly reverses all the nodes, turning the last node into the first, and so on. Let's test it with this input: 1, 2, 3, 4, 5. This represents a singly linked list, 1, 2, 3, 4, 5. Our goal is to reverse the order of the nodes. Here's how it works. We start with prev as none and cur at the head. For each node, we temporarily store the next node, then reverse the pointer so cur.next points to prev. We move prev a and cur forward and repeat until the end. Step by step, the nodes get reversed. 1, 2, 3, 4, 5 becomes 5, 4, 3, 2, 1. The output is 5, 4, 3, 2, 1, exactly what we expect. This confirms our function works correctly. In summary, our implementation successfully reverses the linked list, handles any list length, and does it efficiently with on time and o1 extra space. Simple, accurate, and reliable. In this approach, we reverse a linked list using recursion. Each function call processes one node and then lets the rest of the list reverse itself. It's like peeling an onion. We handle the end first, then connect everything back in reverse. Time complexity is on, where n is the number of nodes in the linked list. Each node is visited exactly once. Recursive calls use on stack space. Define a class solution and the function reverse list. If the list is empty or has only one node, just return it. This is the stopping point for recursion. Call the function on the next node. This will reverse the rest of the list and return the new head. Take the next node and make it point back to the current node. This is where the reversal happens. Set the current nodes next to none because it will now become the tail of the reversed sublist. Return the new head of the reversed list, which we got from the recursive call. Each recursive call processes one node, and the recursion unwinds from the end of the list back to the start. Space complexity is on due to the recursion stack. This algorithm first identifies the base case, then recursively reverses the rest, rewiring pointers as it unwinds. Elegant, simple, and very recursive. Let's see how our recursive solution reverses a linked list step by step. We'll test it with a simple input, 1, 2. This represents a linked list, 1, 2. Our goal is to reverse it so that the last node becomes the first. Here's how it works. The algorithm uses recursion to reach the end of the list. When it hits the last node, which is 2, it starts reversing the pointers. Each node points back to the previous one. For example, node 2 points to node 1 instead of none, and the original head becomes the new tail with its next set to none. The recursion returns the new head, which is 2. Step by step for 1, 2. We call reverse list 1, which calls reverse list 2. Node 2 becomes the new head, and node 1's next pointer is set to none. The final list is 2, 1. The output is 2, 1, exactly what we expected. This confirms our function correctly reverses the linked list. In summary, our recursive implementation efficiently reaches the end, reverses the pointers step by step, and updates the head and tail accurately. It works even for small lists, making the solution clear, accurate, and reliable. Breakdown recap. Conceptually, the task is simple. Take a singly linked list and reverse the direction of all its pointers so that the last node becomes the new head. If you think about it, this is like undoing actions in a text editor. You want to traverse everything in reverse order. Assess recap. The tricky part is managing the pointers. You can't just flip links randomly. If you lose track of the next node, the rest of the list is gone. So we compared approaches and chose a safe, iterative method. Traverse the list while keeping track of the previous, current, and next nodes, reversing links step by step. Structure recap. Our plan was straightforward. Initialize 2 pointers, previous and current. For each node, first store the next node. Reverse the current node's pointer to the previous node. Move previous and current forward. Repeat until the end. At the end, previous points to the new head. Implement recap. We implemented this iterative approach, carefully updating pointers at each step. Running it on LeetCode, the code executed cleanly, without errors or lost links. Check recap. We verified the logic with multiple test cases, multi-node lists, single-node lists, and empty lists. Each time, the nodes were correctly reversed, and all edge cases passed. Time complexity is on, and space is o1, efficient and elegant. Closing insight. The key takeaway? Reversing a linked list is about thinking ahead. Always track your next step before changing links. A small precaution that ensures you never lose the rest of the list. Master this, and you'll handle one of the most classic interview questions with confidence.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Detect loop in linked list. This question came up during my on-site at Amazon. What looked like a simple linked list problem turned out to be a test of whether I understood Floyd's cycle detection algorithm, something a lot of candidates overlook. And over 40% of candidates freeze on this logic. Today, we'll make sure you never get tripped up by a sneaky loop again. Let's crush this blind 75 must-know with a foolproof strategy. First, let's break down the problem. Given the head of a singly linked list, we need to determine if there's a cycle, meaning, does any node link back to a previous node instead of ending with null? As you see in the image, node 5 points back to node 2, forming a loop. If there's a cycle, we return true. If not, we return false. It's that simple. Let's assess our options. One brute force way is to remember every node we've seen using a hash set, but that needs extra space, ON. Is there a slicker way? Yes. The classic tortoise and hare method uses 2 pointers. One moves 1 step at a time, slow, the other moves 2 steps at a time, fast. If there's a cycle, fast will eventually catch slow. If not, fast will hit null. This technique gives us ON time and O1 space, super efficient. Now, let's structure our approach. Start both slow and fast pointers at the head. Move slow by 1 node, fast by 2 nodes each loop. If at any point slow equals fast, we found a cycle, return true. If fast hits null, the end, there's no cycle, return false. Now let's solve solution 1, detecting a cycle in a linked list using a hash set. We'll go line by line, see how we track visited nodes, and understand how to detect a cycle efficiently. Time complexity is ON, where n is the number of nodes in the linked list. Each node is visited at most once. The idea: maintain a set of visited nodes. Walk through the list node by node. If we see a node that is already in the set, a cycle exists, so return true. If we reach the end without repeats, there is no cycle, so return false. Think of it like putting a name tag on each node you visit. If you ever see a node with a tag, you know you visited it before. Line-by-line explanation of the code. We define a class solution to hold our method. This function takes the head of a linked list and returns true if a cycle exists, otherwise false. We create an empty set to store all nodes we visit. Sets allow fast membership checking, like a checklist. Cur will point to the current node we're examining, starting at the head. We loop as long as cur is not none, that is, until we reach the end of the list. We check if this node has already been visited. If yes, it means we've looped back, a cycle exists. If the current node is already in the set, we immediately return true. The linked list has a cycle. If the node is new, we add it to the set. This marks the node as visited. Move cur to the next node in the list. This continues the traversal. If we reach the end without seeing a repeated node, we return false. No cycle exists. And that's how this algorithm works. It first initializes a set to track visited nodes, then iteratively checks each node while moving forward. Efficient, simple, and elegant. Time complexity is ON, as each node is visited once. Space complexity is ON, because we store each node in the set. This is a simple and intuitive way to detect cycles. An alternative is the 2-pointer method, Floyd's tortoise and hare, which uses O1 space. Let's check if our hasCycle function works. We want to see if a linked list contains a cycle, where a node points back to a previous node instead of none. We test it with 3, 2, 0, -4, and pos equals 1, meaning -4 points back to node 2, forming a cycle. The function uses a set to track visited nodes. As we move through the list, we add each node to the set. When we reach a node already in the set, we detect a cycle and return true. The output is true, confirming the function works. This implementation correctly detects cycles in any list, is simple, and efficient with ON time and space. This solution detects a cycle in a linked list without using extra memory. It uses 2 pointers, one moving slowly and the other moving faster. If there's a loop, the fast pointer will eventually meet the slow pointer. This is also called the tortoise and hare algorithm, and it's very space efficient. Time complexity is ON, where n is the number of nodes in the linked list. Each node is visited at most once by slow and fast pointers. Define a class solution and the function hasCycle. Start with both slow and fast pointers at the head of the list. Slow moves step by step. Fast moves twice as fast. Keep looping as long as fast and fast.next exist. If fast hits the end, there's no cycle. Move slow by 1 node, and fast by 2 nodes. Think of it like a tortoise and hare racing around a track. If slow and fast meet, there is a cycle. The pointers have collided inside the loop. If the loop ends without a collision, fast reached the end, and there is no cycle. Return false. Slow and fast pointers ensure ON time complexity. No extra memory is needed. O1 space. This algorithm detects cycles elegantly without modifying the list. Now that we've implemented our solution to detect cycles in a linked list, let's see it in action. We test it with 1, 2, and pos equals 0, meaning node 2 points back to node 1, forming a cycle. The function uses 2 pointers. Slow moves 1 step at a time, and fast moves 2 steps. If a cycle exists, fast will eventually meet slow. Otherwise, fast reaches the end. For this input, slow and fast meet, confirming a cycle. The output is true, showing that the implementation correctly detects the cycle. This two-pointer approach efficiently identifies cycles, works for any list, and is simple, accurate, and reliable. Breakdown recap. Conceptually, we're given a singly linked list, and we need to determine if it contains a cycle, that is, if any node points back to a previous node instead of ending with null. If a cycle exists, we return true, otherwise, false. Assess recap. We looked at different approaches. A brute force method is to store visited nodes in a hash set, but that uses extra space. A more elegant solution is the tortoise and hare technique, 2 pointers moving at different speeds. If there's a cycle, the faster pointer eventually catches up to the slower one. If not, the fast pointer reaches the end of the list. This method gives ON time with O1 space, highly efficient. Structure recap. Our approach was straightforward. Initialize slow and fast pointers at the head. Move slow 1 step at a time, fast 2 steps. If they meet at any point, a cycle exists, return true. If fast reaches null, no cycle exists, return false. Implement recap. We implemented this using the classic 2-pointer method. Running it on LeetCode, the code executed cleanly, detecting cycles or confirming acyclic lists without errors. Check recap. We verified it with multiple cases. Lists with cycles, like one where node 5 points back to node 2, correctly returned true. Lists without cycles returned false. This confirmed that the logic works as expected in all scenarios. Closing insight. The key takeaway? Cycle detection is all about pointer strategy. By carefully moving slow and fast pointers, you can catch loops efficiently, using constant space, a small
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Did you know merge 2 sorted lists is one of the most frequently asked questions at FONG interviews? It's a favorite because it checks your understanding of both pointers and real algorithmic thinking. Over a third of candidates stumble here, but with the right method, you'll be able to merge any sorted lists, just like magic. Today, we're turning this Pattern Mastery 100 staple into an easy win. Ready? Let's dive in. First, let's break down the problem. You're given 2 sorted linked lists, like list 1 and list 2 in the image above. Your goal? Merge them into a single, sorted linked list. The trick is, you should do this by reusing the existing nodes, not by creating extra arrays or data structures. Let's assess the challenge. A brute force approach could be to collect all the values, sort them, and build a new list, but that wastes space and time. The optimal way is to use 2 pointers, one for each list, and merge them as we go, node by node. The merging will be done in ON time and O1 extra space, since we're just changing the next pointers. Now, let's structure our approach. Create a dummy node to serve as the head of our new merged list. Use a pointer, tail, to track the end of the merged list, while both lists have nodes. Compare their values. Attach the smaller node to tail. Advance the pointer of the list from which the node was chosen. Once we run out of nodes in one list, simply point tail dot next to the remaining nodes in the other list. Now let's solve solution 1, merging 2 sorted linked lists iteratively. We'll go step by step, understand how to pick the smaller node each time, and build a new merged list. Time complexity is OM plus N, where M is the number of nodes in L1 and N is the number of nodes in L2. Each node is visited exactly once. The idea: use a dummy node to simplify list construction. Keep a tail pointer that always points to the last node in the merged list. Compare the current nodes of L1 and L2. Attach the smaller node to tail and move that list's pointer forward. Once one list is exhausted, append the remaining nodes from the other list. Think of it like merging 2 sorted lines of people into a single sorted line, one person at a time. Line-by-line explanation of the code. We define a class solution to hold our method. This function takes 2 sorted linked lists, L1 and L2, and returns a merged sorted linked list. We create a dummy node with value 0. It acts as a placeholder to simplify building the merged list. Tail points to the last node in the merged list. Initially, it points to the dummy. Loop as long as both lists have nodes. We will pick the smaller node from L1 or L2 each iteration. Compare the current values of L1 and L2. If L1 is smaller, it should go next in the merged list. Attach L1's current node to the merged list. Tail now points to this node. Move L1 to its next node. We've already added the current one to the merged list. If L2's value is smaller or equal, attach L2's node and move L2 forward. Move tail forward so it always points to the last node in the merged list. Once one list is empty, attach the remaining nodes of the other list. No need to compare anymore. The remaining list is already sorted. Return the merged list starting after the dummy node. This is the actual head of the merged list. And that's how this algorithm works. It first sets up a dummy node and tail pointer, then iteratively picks the smaller node from the two lists, and finally attaches any remaining nodes. Efficient, simple, and elegant. Time complexity is O(m) plus n, as each node is processed once. Space complexity is O(1), because no extra nodes are created, just pointers are adjusted. Using a dummy node simplifies edge cases. The iterative approach avoids the extra call stack used in recursion.
Let's test our merge two lists function. We have list1 equals 1, 2, 4, and list2 equals 1, 3, 4. Our goal is to merge them into one sorted list. We use a dummy node and a tail pointer, then compare nodes from both lists, attaching the smaller one each time. We continue until all nodes are merged. The result is 1, 1, 2, 3, 4, 4, confirming our function works correctly. This implementation merges two sorted lists efficiently and keeps the order intact.
This solution merges two sorted linked lists using recursion. Instead of iterating, it breaks the problem into smaller pieces. It picks the smaller head node, then recursively merges the rest. This is very elegant and clean, especially for those comfortable with thinking recursively. Time complexity is O(m) plus n, where m is the number of nodes in list L1 and n is the number of nodes in list L2. Each node is visited exactly once. Define a class solution and the function merge two lists. If L1 is empty, we simply return L2. Nothing more to merge from L1. Similarly, if L2 is empty, we return L1. These base cases stop the recursion. If L1's value is smaller, L1 will be the next node in the merged list. Then we recursively merge the rest of L1, L1.next, with L2. Finally, return L1 as the head of the merged list. If L2's value is smaller or equal, L2 becomes the next node. Recursively merge L1 with the rest of L2, L2.next. Return L2 as the head of the merged list. This recursive solution is elegant but uses stack memory, O(m) plus n space. Base cases handle empty lists cleanly. Each node is processed exactly once, giving O(m) plus n time. Recursion naturally handles the merge the rest logic automatically.
Let's test our merge two lists function. We have list1 equals 1, 2, 4, and list2 equals 1, 3, 4. Our goal is to merge them into one sorted list. We use a dummy node and a tail pointer, then compare nodes from both lists, attaching the smaller one each time. We continue until all nodes are merged. The result is 1, 1, 2, 3, 4, 4, confirming our function works correctly. This implementation merges two sorted lists efficiently and keeps the order intact.
Let's wrap up the merge two sorted lists problem. This is a classic Phong favorite because it tests both your pointer skills and your ability to merge sequences efficiently. Master this, and you can handle merging tasks in interviews like a pro. Breakdown recap. Conceptually, we're given two sorted linked lists, and our goal is to combine them into a single, sorted linked list. The key is to reuse the existing nodes rather than creating extra arrays or data structures. Assess recap. A brute force approach would be to gather all values, sort them, and build a new list, but that wastes space and time. The optimal approach uses two pointers, one for each list, and merges nodes step by step. This keeps the process in linear time with constant extra space. Structure recap. Here's the plan. Create a dummy node to act as the head of the merged list. Use a tail pointer to track the end of the merged list. While both lists have nodes, compare their values and attach the smaller node to tail. Advance the pointer in the list from which the node was chosen. Once one list is exhausted, attach the remainder of the other list. Implement recap. We implemented this with a dummy node and a tail pointer, iteratively comparing nodes and building the merged list. Running it on LeetCode, the solution executed smoothly without errors. Check recap. Edge cases, such as empty lists, also returned correct results. Time complexity is O(n) plus m, and space is O1. Closing insight. The main takeaway? Merging sorted lists is all about careful pointer management. By comparing nodes step by step and reusing the existing structure, you get an elegant, efficient solution every time, a must-have skill for linked list mastery.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
What happens when an interviewer wants to truly test your algorithmic efficiency? Merge case sorted lists is a Pattern Mastery 100 heavyweight and a frequent guest at Google, Amazon, and Microsoft interviews. Over 40% of candidates get slowed down by the complexity in pointer management. Master this, and you'll prove you can handle multi-list merges, priority queues, and advanced patterns.
Let's attack merge case sorted lists with the basic problem-solving framework, a stepwise guide for turning chaos into clarity, even in the toughest coding rounds. Let's break it down. Given an array of k-linked lists, each sorted in ascending order, merge them all into one sorted linked list and return its head. Example: input 145, 134, 26. Output 1, 1, 2, 3, 4, 4, 5, 6. Real-world example: think about a system that needs to combine multiple log files, each sorted by timestamp, into a single unified log for analysis. A classic interview extension. How would you merge sorted streams from different servers in real time? Let's assess it. What's tricky here? Naive approach. Merge the lists one by one using the two-list merge logic, O-kilonewton, time, where n is total nodes, works, but not optimal. Optimal approach. Use a min heap, priority queue, to always pick the smallest head among the k-lists, giving you O(n) log k time. Let's think step by step. Push the first node of each list into a min heap, keyed by node value. Repeatedly pop the smallest node from the heap, attach it to the merged list, and if there's a next node in that list, push it into the heap. Continue until the heap is empty. Let's dig deeper. Why a heap? It guarantees that at each step, you can efficiently, in O log k, get the smallest remaining node across all lists. Using a dummy node for the result list keeps the code clean and bug-free. Edge cases? Some lists may be empty. All lists empty? Output should be null. Here's the structure. Create a dummy head for the result list and a current pointer. Initialize a min heap and insert the first node of each list if not null. While the heap isn't empty, pop the node with the smallest value. Attach it to the current pointer. If the pop node has a next, push that next node into the heap. Move current forward. Return dummy.next. Now let's solve solution 1, merging k-sorted linked lists using a min heap. We'll see how to efficiently pick the smallest node among multiple lists using a heap. Step by step, we'll understand how the heap helps us maintain order. Time complexity is O(n) log k, where n is the total number of nodes across all lists, and k is the number of lists. Each node is pushed and popped from the heap once, which takes log k per operation. The idea: use a min heap to always know which list has the smallest current node. Push the head of each list into the heap. Repeatedly pop the smallest node from the heap and attach it to the merged list. If the pop node has a next node, push it into the heap. Continue until the heap is empty. Think of it like picking the next smallest card from multiple decks. A heap helps you do it efficiently. Line-by-line explanation of the code. We import Python's heap key module to manage our min heap. This ensures the smallest value is always on top. We define the solution class to contain our merge function. This function takes lists, a list of k-sorted linked lists, and merges them into one sorted list. We create a dummy node to simplify building the merged list. The final merged list will start from dummy.next. Tail points to the last node in the merged list. We will keep moving it forward as we add nodes. Initialize an empty min heap. It will store tuples of node value, list index, to track the smallest node among all lists. Loop over each list's head. If the list is not empty, push its value and index into the heap, then move the list pointer to the next node. Loop until the heap is empty. Each iteration we extract the smallest node among the current nodes. Pop the smallest node from the heap. Val is the node's value. ID it tells us which list it came from. Attach the popped value to the merged list and move tail forward. If the list we just popped from has more nodes, push the next node into the heap and advance its pointer. This keeps the heap updated with the current smallest nodes. Return the merged list starting after the dummy node. And that's how this algorithm works. It first initializes a heap with the heads of all lists, then repeatedly picks the smallest node, adds it to the merged list, and updates the heap. Efficient, simple, and elegant. Heap operations cost O log k for push and pop. Total nodes n overall complexity O(n) log k. Space complexity is OK for the heap. Using a heap avoids repeatedly scanning all list heads to find the smallest node.
Let's test our merge list function. We have 3 sorted lists, 1, 4, 5, 1, 3, 4, and 2, 6. The goal is to merge them into a single sorted list. We use a min heap to always pick the smallest node among the lists, adding nodes one by one to the merged list. The result is 1, 1, 2, 3, 4, 4, 5, 6, confirming the function works correctly. This approach efficiently merges multiple lists while keeping the order intact.
This solution merges k-sorted linked lists using a divide and conquer strategy. Instead of merging lists one by one, it merges them in pairs repeatedly until only one list remains. This is faster and more efficient, especially for many lists. Time complexity is O(n) log k, where n is the total number of nodes across all lists and k is the number of lists. Each merge operation touches all nodes, but we reduce the number of lists by half each round, giving log k rounds. Define a class solution and the function merge lists. If the input list of lists is empty, return none immediately. Nothing to merge. Use a helper function merge2 to merge 2 sorted lists. Start with a dummy node to simplify handling the head, and a tail pointer to keep track of the end of the merged list. As long as both lists have nodes, compare their values. The smaller node is added to the merged list, and its pointer is moved forward. Tail always points to the last node in the merged list. After one list is exhausted, attach the remaining nodes of the other list. Return the merged list starting after the dummy node. Merge lists in pairs using an interval. Start with interval 1, merge list 0 with 1, 2 with 3, etc. After one round, double the interval to merge the merged lists together. Repeat until all lists are merged. Finally, return the fully merged list, which is now at index 0. Divide and conquer reduces the number of merge rounds, making it faster than sequential merging. Each node is processed once per merge, giving a total time complexity of O(n) log k. Space used is mostly for recursion stack in merge2, but the iterative implementation inside uses O(1) extra space.
Let's test our function to merge multiple sorted linked lists. With 1, 4, 5, 1, 3, 4, and 2, 6, it merges 2 lists at a time until all lists combine into 1, 1, 2, 3, 4, 4, 5, 6. For empty input, it returns. This approach efficiently merges multiple lists, keeps order, and works reliably for any input.
Breakdown recap. We're given an array of k-sorted linked lists and need to merge them all into one fully sorted linked list. Conceptually, it's about combining multiple sorted sequences into a single unified list. Assess recap. A naive approach would merge the lists one by one using two-list logic, but that's slow. The optimal approach leverages a min heap, priority queue, to always select the smallest node across all lists. This reduces the complexity significantly and makes it efficient even for many lists. Structure recap. Here's the plan. Create a dummy head for the merged list and a current pointer. Initialize a min heap and push the first node of each list, if not null. While the heap isn't empty, pop the smallest node, attach it to the merged list, and if that node has a next, push it into the heap. Move the current pointer forward and continue. At the end, return the merged list. Implement recap. We implemented this using a min heap, storing tuples of node value, node, to ensure proper ordering. Running it on LeetCode, the solution executed cleanly and efficiently merged all lists without errors. Check recap. We verified the logic across all general cases and edge cases. The solution runs in O(n) log k, time with OK space for the heap and produces correct results consistently. Closing insight. The key takeaway? When merging multiple sorted sequences, a min heap is the most effective tool. It lets you efficiently track and select the smallest current element, keeping the process clean, fast, and scalable for any number of lists.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
To cement your linked list mastery, try these 5 classic follow-ups next. Reverse linked list 2 builds on today's pattern, challenging you to reverse only a section of the list. Palindrome linked list requires checking if a list reads the same forward and backward, which often involves reversing part of it. Merge two sorted lists is perfect for practicing pointer updates as you combine two lists into one. Let's break down the remove nth node from end of list problem. You're given the head of a singly linked list and an integer n. You need to remove the nth node from the end of the list. As shown in the image, if the list is 1, 2, 3, 4, 5 and n equals 2, the node with value 4 should be deleted. The output should be 1, 2, 3, 5. Let's assess what's tricky here. A brute force way is to count the nodes, then walk to the node just before the one to remove. But that takes 2 passes. Interviewers want a slick, one-pass solution. The classic trick is to use 2 pointers, fast and slow. Now, let's structure our approach. Create a dummy node pointing to head to handle edge cases easily. Move the fast pointer n steps ahead. Move both fast and slow pointers until fast reaches the end. Skip the nth node from n by setting slow.next equals slow.next.next. Return dummy.next as the new head. Now let's solve solution 1, removing the nth from the end of a linked list using a 2-pass approach. We'll see how to compute the length first, then remove the target node step by step. Time complexity is O(n), where n is the number of nodes in the linked list. We traverse the list twice, once to count nodes, once to remove the target. The idea: first pass, compute the length of the linked list. Second pass, go to the node just before the target node, length, n. Adjust pointers to skip over the nth from the end. Think of it like counting how many people are in line, then removing the person at a specific position from the end. Line-by-line explanation of the code, we define a class solution to hold our method. This function takes the head of a linked list and an integer n, and removes the nth node from the end. Create a dummy node pointing to the head. This simplifies edge cases like removing the first node. Length will count the total nodes. Cur is used to traverse the list starting at the head. Loop through the list to count its length. For each node, increment length and move cur forward. Reset cur to the dummy node for the second pass. Move cur to the node just before the target node. Length, n steps from dummy gets us there. Skip over the target node by adjusting pointers. This effectively removes it from the list. Return the new head of the linked list, starting after the dummy node. And that's how this algorithm works. It first counts the length of the list, then locates the node just before the target, and finally removes it by adjusting pointers. Efficient, simple, and elegant. Time complexity is O(n), 2 passes, but linear overall. Space complexity is O(1), no extra data structures used. Using a dummy node handles edge cases like removing the first node. Simple and intuitive 2-pass solution.
We're testing our function that removes the nth node from the end of a linked list. For the input head equals 1, 2, 3, 4, 5, and n equals 2, we want to remove the second to last node, which is 4. The solution works by getting the list length, finding the node right before the one to remove, and skipping over it. This gives us the final list, 1, 2, 3, 5. The function removes the correct node and keeps the list structure intact. This solution removes the nth node from the end of a linked list in one pass using 2 pointers. Instead of calculating the length first, we move one pointer ahead and then move both pointers together to locate the target node efficiently. Time complexity is O(n), where n is the number of nodes in the linked list. Each node is visited at most once, giving linear time. Define a class solution and the function remove nth from end. Start with a dummy node pointing to the head. This helps handle edge cases, like removing the first node. Set both slow and fast pointers to the dummy node. Slow will eventually stop before the node to remove, and fast helps locate that spot. Move the fast pointer n+1 steps ahead. This ensures the gap between slow and fast is exactly n nodes, so when fast reaches the end, slow is right before the target. Move both slow and fast one step at a time until fast reaches the end. Slow stops just before the node we want to remove. Skip over the target node by pointing slow dot next to the node after it. This effectively removes the nth node from the end. Return the head of the modified list, which is dummy.next. This also handles cases where the original head was removed. Using a dummy node simplifies edge cases. Only one pass through the list is needed, and 2 pointers maintain the exact gap needed to find the nth node from the end. Now let's see how our solution works on a simple test case. For the input head equals 1, and n equals 1, we want to remove the only node in the list. The algorithm uses 2 pointers. Fast moves ahead by n+1 steps, so slow ends up right before the node we need to remove. Since this list has just one node, slow stays at the dummy node,
and removing slow.next gives us an empty list. And that's exactly what the output shows, an empty list. This confirms our implementation works correctly, even for edge cases where the entire list is removed. Breakdown recap. Conceptually, the task is to remove the nth node from the end of a singly linked list. It's about navigating the list efficiently without counting nodes multiple times or using extra space. Assess recap. A brute force approach would be 2 passes. Count nodes, then locate the node to remove. The optimal interview-friendly approach uses 2 pointers, fast and slow, to accomplish this in 1 pass. This technique allows you to reach the target node directly while maintaining ON time and O1 space. Structure recap. Here's the plan. Start with a dummy node pointing to the head to handle edge cases. Move the fast pointer n steps ahead. Move both fast and slow pointers together until fast reaches the end. Slow will then be just before the target node, so skip it by adjusting pointers. Return the new head from dummy.next. Implement recap. We implemented the 2-pointer approach with a dummy node, carefully moving fast and slow until the correct node could be removed. Running it on LeetCode, the code executed cleanly without errors. Check recap. We verified the logic for various list lengths and positions of n. The solution consistently removed the correct node and returned the updated list. It runs in ON time with O1 extra space. Closing insight. The key takeaway? 2 pointers and a dummy node make 1-pass operations both safe and elegant. Mastering this technique ensures you can handle a wide range of linked list challenges confidently.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Ever wondered what makes a medium linked list question actually tough in interviews? Reorder list is a PatternMastery 100 favorite, regularly used at Facebook and Google to test deep understanding of pointer logic and in-place list manipulation. Over 35% of candidates get stuck or write buggy code here. Let's make sure you know how to conquer it.
We'll use the basic method to systematically solve reorder list. This approach keeps us organized, ensuring we never lose our place, literally or figuratively. Let's break it down. Given the head of a singly linked list, you need to reorder it in a very specific way. Take the first node, then the last, then the second last, and so on, alternating from both ends toward the center. Example. Input, 1 2 3 4 5. Output, 1 5 2 4 3. Real-world example. Imagine you're processing a waiting line at a theme park, but to balance both ends, you alternate pulling people from the front and the end. Or in file processing, if you want to interleave oldest and newest records for sampling, what's tricky? We must do this in place, no copying nodes or using extra lists. If you try to naively alternate pointers, you might easily lose access to the remaining nodes. Classic pattern. Find the middle of the list, using fast and slow pointers. Reverse the second half. Merge the 2 halves, 1 node at a time. Think step by step. Use slow or fast pointers to split the list in half. Reverse the second half so the last node comes right after the first. Alternate merging nodes from each half, being careful with pointers, so you don't lose the next nodes in either half. Let's break it down further. After splitting, you have 2 sublists. First, 1 2 3. Second, reversed, 5 4. You then weave them together. 1 5 2 4 3. Edge cases, even or odd length lists, single node lists, should remain unchanged. Here's the structure. Find the middle. Use slow and fast pointers. Reverse the second half. Classic in place reverse. See reverse linked list. Merge, halves, alternate nodes from first and second half, updating pointers carefully. Let's implement it. Set slow and fast at the head. Move slow 1 and fast 2 steps at a time until fast reaches the end. Slow now at midpoint. Reverse the second half, starting at slow.next. Now let's solve solution 1, reordering a linked list using an array of nodes. We'll learn how to collect all nodes into a list for easy access, then rearrange them by alternating from the front and back. Time complexity is ON, where n is the number of nodes in the linked list. Each node is visited once to collect and once to reorder. The idea: first, traverse the list and collect all nodes in an array for random access. Use 2 pointers, I starting at the front and j at the end. Reorder the list by connecting nodes I, nodes j, nodes I plus 1, nodes j1, alternately. Stop when the pointers meet. Think of it like taking cards from the top and bottom of a deck and laying them out one by one. Line-by-line explanation of the code. We define a class solution to contain our method. This function takes the head of a linked list and reorders it in place. If the list is empty, just return, nothing to do. Nodes will hold all the nodes for random access. Cur is used to traverse the list starting at the head. Traverse the linked list and append each node to the array. After this loop, nodes contains all nodes in order. Initialize 2 pointers, I at the start, j at the end of the array. Alternate connecting nodes from the front and back. Nodes i's, next equals nodes j, connects the front node to the back node. Move I forward. If I equals j, we're done. Otherwise, nodes j, next equals nodes I, connects back node to next front node. Move j backward. Finally, set the last nodes next to none to terminate the reordered list. And that's how this algorithm works. It first collects all nodes into an array, then reorders them alternately from front and back, and finally ends the list properly. Efficient, simple, and elegant. Time complexity. O(n). Traverse list twice, collect plus reorder. Space complexity. O(n), array of nodes for random access. Very intuitive approach, easy to implement. Edge case. Empty list handled at the start. Before we check the output, let's understand what the problem is. We want to reorder a linked list in a specific pattern. L0 lane L1 lane 1 L2 lane 2. This test case will help us verify that the function reorderList correctly rearranges the nodes without losing any of them. Let's test our function using this input. The linked list is 1 2 3 4. We want to reorder it so that the first node is followed by the last node, then the second node, then the second to last node, and so on. Here's why the solution works. First, we traverse the list and collect all nodes into a list called nodes for easy random access. We initialize 2 pointers, I at the start and j at the end of the list. Then, we reorder the list by alternating nodes from the front and back. Nodes I, next equals nodes j, links the first node to the last. Move I forward. Node is j, next equals nodes I, links the last node to the second node. Move j backward. We repeat this process until I meets j, then mark the end of the list with nodes j. Next equals none. Step by step, the list 1 2 3 4 becomes 1 4 2 3. And that is exactly what the program outputs, 1, 4, 2, 3. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully reorders the linked list into the required pattern, efficient, accurate, and reliable. Our implementation is correct. It correctly alternates nodes from front and back. It preserves all original nodes. It marks the end of the list properly to avoid cycles or dangling pointers. This solution reorders a linked list in place without using extra space. It works in 3 steps. First find the middle of the list, then reverse the second half, and finally merge the 2 halves. Efficient and neat. Time complexity is O(n), where n is the number of nodes in the linked list. Each node is visited at most 3 times, giving linear time. Define a class solution and the function reorderList. Check if the list is empty or has only 1 node. If so, nothing to do. Use slow and fast pointers to find the middle. Slow moves 1 step, fast moves 2 steps. When fast reaches the end, slow is at the middle. Split the list into 2 halves. Second starts at the node after slow, and we break the link by setting slow next to none. Reverse the second half of the list using standard pointer reversal. Prev will eventually point to the new head of the reversed list. Merge the 2 halves alternatingly. Link a node from the first half, then one from the second half, and continue until the second half is fully merged. This approach uses O(1) extra space, is fully in place, and each node is touched a few times. It handles both even and odd length lists naturally. Now that we've implemented our solution to reorder a linked list, let's walk through how it works on a real input. We'll see how the algorithm rearranges the nodes by alternating from the start and end of the list while keeping everything connected properly. This input represents a linked list with 5 nodes. Our goal is to reorder the list so that nodes alternate from the beginning and end. First node, last node, second to last node, and so on. Here's why the solution works. First, the algorithm finds the middle of the list using the slow and fast pointer technique. Then, it splits the list into 2 halves and reverses the second half. Finally, it merges the 2 halves by alternating nodes from each half. Step by step for this input. 1 2 3 4 5 middle is at node 3, split into 1, 2, 3, and 4, 5, reverse second half, 5, 4, merge, 1 5 2 4 3, and that's exactly what the program outputs. 1, 5, 2, 4, 3. This confirms the code correctly reorders the list as intended. So, our implementation is correct. The algorithm successfully reorders a linked list in the specified pattern, precise, efficient, and reliable. Breakdown recap. Conceptually, we need to reorder a singly linked list so that nodes alternate from the start and end toward the center. It's about weaving the first node, then last, then second last, and so on, all without creating new lists. Assess recap. The tricky part is doing this in place. Naively alternating nodes can easily cause you to lose access to remaining nodes. The clean approach is threefold. Find the middle of the list, reverse the second half, and then merge the two halves carefully. Structure recap. Here's the plan. Use slow and fast pointers to locate the middle of the list. Reverse the second half of the list in place. Split the list at the middle and merge the two halves, alternating nodes while keeping pointer updates safe. Implement recap. We implemented slow and fast pointers to find the midpoint, reverse the second half starting from the midpoint, and then merge nodes from each half step by step. Running this on LeetCode executed smoothly without errors, fully reordering the list in place. Check recap. We verified the solution works for lists of various lengths, including edge cases like single node lists and even length lists. Time complexity is O(n), and space complexity is O(1) since no extra data structures are used. Closing insight. The key takeaway? By splitting, reversing, and merging carefully, you can reorder a list efficiently and in place. Mastering this pattern strengthens your understanding of pointer manipulation, a crucial skill for any advanced linked list problem in interviews.
This is not another random playlist. It is a roadmap. Patterns, structure, repetition. The stuff that actually sticks. PatternMastery.com.
Ever wondered what makes a medium linked list question actually tough in interviews? Reorder list is a PatternMastery 100 favorite, regularly used at Facebook and Google to test deep understanding of pointer logic and in-place list manipulation. Over 35% of candidates get stuck or write buggy code here. Let's make sure you know how to conquer it. We'll use the basic method to systematically solve reorder list. This approach keeps us organized, ensuring we never lose our place, literally or figuratively. Let's break it down. Given the head of a singly linked list, you need to reorder it in a very specific way. Take the first node, then the last, then the second last, and so on, alternating from both ends toward the center. Example. Input, 1 2 3 4 5. Output, 1 5 2 4 3. Real-world example. Imagine you're processing a waiting line at a theme park, but to balance both ends, you alternate pulling people from the front and the end. Or in file processing, if you want to interleave oldest and newest records for sampling, what's tricky? We must do this in place, no copying nodes or using extra lists. If you try to naively alternate pointers, you might easily lose access to the remaining nodes. Classic pattern. Find the middle of the list, using fast and slow pointers. Reverse the second half. Merge the two halves, one node at a time. Think step by step. Use slow or fast pointers to split the list in half. Reverse the second half so the last node comes right after the first. Alternate merging nodes from each half, being careful with pointers, so you don't lose the next nodes in either half. Let's break it down further. After splitting, you have two sublists. First, 1 2 3. Second, reversed, 5 4. You then weave them together. 1 5 2 4 3. Edge cases, even or odd length lists, single node lists, should remain unchanged. Here's the structure. Find the middle. Use slow and fast pointers. Reverse the second half. Classic in place reverse. See reverse linked list. Merge, halves, alternate nodes from first and second half, updating pointers carefully. Let's implement it. Set slow and fast at the head. Move slow 1 and fast 2 steps at a time until fast reaches the end. Slow now at midpoint. Reverse the second half, starting at slow. Next. Now let's solve solution 1, reordering a linked list using an array of nodes. We'll learn how to collect all nodes into a list for easy access, then rearrange them by alternating from the front and back. Time complexity is O(n), where n is the number of nodes in the linked list. Each node is visited once to collect and once to reorder. The idea: first, traverse the list and collect all nodes in an array for random access. Use two pointers, I starting at the front and j at the end. Reorder the list by connecting nodes I, nodes j, nodes I plus 1, nodes j1, alternately. Stop when the pointers meet. Think of it like taking cards from the top and bottom of a deck and laying them out one by one. Line-by-line explanation of the code.
We define a class solution to contain our method. This function takes the head of a linked list and reorders it in place. If the list is empty, just return, nothing to do. Nodes will hold all the nodes for random access. Cur is used to traverse the list starting at the head. Traverse the linked list and append each node to the array. After this loop, nodes contains all nodes in order. Initialize 2 pointers, I at the start, j at the end of the array. Alternate connecting nodes from the front and back. Nodes i's, next equals nodes j, connects the front node to the back node. Move I forward. If I equals j, we're done. Otherwise, nodes j, next equals nodes I, connects back node to next front node. Move j backward. Finally, set the last nodes next to none to terminate the reordered list. And that's how this algorithm works. It first collects all nodes into an array, then reorders them alternately from front and back, and finally ends the list properly. Efficient, simple, and elegant. Time complexity. O(n). Traverse list twice, collect plus reorder. Space complexity. O(n), array of nodes for random access. Very intuitive approach, easy to implement. Edge case. Empty list handled at the start. Before we check the output, let's understand what the problem is. We want to reorder a linked list in a specific pattern. L0 lane, L1 lane 1, L2 lane 2. This test case will help us verify that the function reorderList correctly rearranges the nodes without losing any of them. Let's test our function using this input. The linked list is 1, 2, 3, 4. We want to reorder it so that the first node is followed by the last node, then the second node, then the second to last node, and so on. Here's why the solution works. First, we traverse the list and collect all nodes into a list called nodes for easy random access. We initialize 2 pointers, I at the start and j at the end of the list. Then, we reorder the list by alternating nodes from the front and back. Nodes I, next equals nodes j, links the first node to the last. Move I forward. Node is j, next equals nodes I, links the last node to the second node. Move j backward. We repeat this process until I meets j, then mark the end of the list with nodes j. Next equals none. Step by step, the list 1, 2, 3, 4 becomes 1, 4, 2, 3. And that is exactly what the program outputs, 1, 4, 2, 3. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully reorders the linked list into the required pattern, efficient, accurate, and reliable. Our implementation is correct. It correctly alternates nodes from front and back. It preserves all original nodes. It marks the end of the list properly to avoid cycles or dangling pointers. This solution reorders a linked list in place without using extra space. It works in 3 steps. First find the middle of the list, then reverse the second half, and finally merge the 2 halves. Efficient and neat. Time complexity is O(n), where n is the number of nodes in the linked list. Each node is visited at most 3 times, giving linear time. Define a class solution and the function reorderList. Check if the list is empty or has only 1 node. If so, nothing to do. Use slow and fast pointers to find the middle. Slow moves 1 step, fast moves 2 steps. When fast reaches the end, slow is at the middle. Split the list into 2 halves. Second starts at the node after slow, and we break the link by setting slow next to none. Reverse the second half of the list using standard pointer reversal. Prev will eventually point to the new head of the reversed list. Merge the 2 halves alternatingly. Link a node from the first half, then one from the second half, and continue until the second half is fully merged. This approach uses O(1) extra space, is fully in place, and each node is touched a few times. It handles both even and odd length lists naturally. Now that we've implemented our solution to reorder a linked list, let's walk through how it works on a real input. We'll see how the algorithm rearranges the nodes by alternating from the start and end of the list while keeping everything connected properly. This input represents a linked list with 5 nodes. Our goal is to reorder the list so that nodes alternate from the beginning and end. First node, last node, second to last node, and so on. Here's why the solution works. First, the algorithm finds the middle of the list using the slow and fast pointer technique. Then, it splits the list into 2 halves and reverses the second half. Finally, it merges the 2 halves by alternating nodes from each half. Step by step for this input. 1, 2, 3, 4, 5 middle is at node 3. Split into 1, 2, 3, and 4, 5, reverse second half, 5, 4, merge, 1, 5, 2, 4, 3, and that's exactly what the program outputs, 1, 5, 2, 4, 3. This confirms the code correctly reorders the list as intended. So, our implementation is correct. The algorithm successfully reorders a linked list in the specified pattern, precise, efficient, and reliable. Breakdown recap. Conceptually, we need to reorder a singly linked list so that nodes alternate from the start and end toward the center. It's about weaving the first node, then last, then second last, and so on, all without creating new lists. Assess recap. The tricky part is doing this in place. Naively alternating nodes can easily cause you to lose access to remaining nodes. The clean approach is threefold. Find the middle of the list, reverse the second half, and then merge the two halves carefully. Structure recap. Here's the plan. Use slow and fast pointers to locate the middle of the list. Reverse the second half of the list in place. Split the list at the middle and merge the two halves, alternating nodes while keeping pointer updates safe. Implement recap. We implemented slow and fast pointers to find the midpoint, reverse the second half starting from the midpoint, and then merge nodes from each half step by step. Running this on LeetCode executed smoothly without errors, fully reordering the list in place. Check recap. We verified the solution works for lists of various lengths, including edge cases like single node lists and even length lists. Time complexity is O(n), and space complexity is O(1) since no extra data structures are used. Closing insight. The key takeaway? By splitting, reversing, and merging carefully, you can reorder a list efficiently and in place. Mastering this pattern strengthens your understanding of pointer manipulation, a crucial skill for any advanced linked list problem in interviews.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
Can you design an LRU cache in O(1) per operation? This pattern mastery essential is a must-win in systems-flavored interviews. It proves you can pair a hash map with a doubly linked list to get constant time get/put, and manage eviction policy precisely. Let's build it using basics so your explanation and code are smooth and convincing. Let's break this down. We need a cache with capacity cap. Operations.key returns value or -1, also marks key as most recently used. Put key, value, inserts or updates, moving key to MRU. If size exceeds capacity, evict the least recently used. We want O(1) per op. Let's assess. We need two abilities, fast lookup by key, hash map, and fast reordering/eviction at both ends, doubly linked list. The map points key to node. The list stores nodes ordered from MRU, head side, to LRU, tail side. Moving to MRU, remove node and add after head. Eviction. Pop before tail. Complexity is O(1) for all modifications. Here is the structure. Design helpers, _add _after _head node, _remove node, _move to _head node, and _pop low ru. Get, if missing return -1, else move node to head and return value. Put, if key exists, update value and move to head, else create node, add to head, and if size exceeds capacity, pop LRU and delete from map. Now let's implement the ordered dict-based LRU cache, leveraging its built-in ordering to update and retrieve entries in constant time. We import ordered dict, a special dictionary that remembers the order in which keys were inserted. Perfect for tracking what's least recently used. We define our LRUCake class that will hold the cache logic. The constructor takes in a capacity, which is the maximum number of items the cache can store. We store the capacity so we can check when the cache becomes full. We create an ordered dict to store our key value pairs. This will let us move items to the end whenever they're used, giving us O(1) LRU updates. This method retrieves a value and updates its recency. If the key doesn't exist in the cache, we return -1, meaning a cache miss. If the key exists, we remove it from its current position. This is how we prepare to move it to the most recently used spot. We reinsert it at the end of the ordered dict, marking it as the most recently used. And finally, we return its value. This method inserts or updates a key, while maintaining LRU order. If the key already exists, we remove its old version so we can reinsert it as most recently used. We insert or update the key with its new value, placing it at the end of the ordered dict. If the cache is now too large, meaning it exceeded its capacity, we remove the least recently used item. Last equals false ensures we pop from the front, where the oldest entry lives. And that's how this algorithm works. It first stores items inside an ordered dict, then moves recently accessed items to the end, and finally evicts the least recently used items whenever the cache exceeds capacity. Efficient, simple, and elegant. Let's test our LRU cache with these operations. They simulate adding values, accessing them, and watching which keys get evicted when the cache reaches capacity. We start with a capacity of 2. After inserting keys 1 and 2, the cache is full. Accessing key 1 makes it the most recently used. When we insert key 3, the least recently used key, 2, gets evicted. Later, inserting key 4 evicts key 1. So the get operations return exactly what we expect: 1, -1, -1, 3, and 4 based on what's still in the cache. And that's exactly what our program outputs. The results match perfectly. Each get reflects the correct LRU behavior at that moment. So, our implementation is correct. The LRU cache correctly maintains usage order, handles evictions, and returns values in constant time, efficient and accurate. Now let's implement the custom LRU design, combining a hash map with a doubly linked list to control order and achieve true O1 operations. This defines a node in our doubly linked list. Each node holds a key, a value, and pointers to its neighbors. We set up the node with an optional key and value. This keeps things flexible. We store the key so we can delete this node from the cache dictionary later. We also store the value, the actual data the cache holds. This node will eventually link backward, but for now, it points to nothing. Same idea for its forward pointer. This class manages the LRU behavior using a combination of a doubly linked list and a hash map. Our constructor receives the maximum allowed number of items. We store that capacity for eviction checks later. This will be our hash map, key node, which lets us find nodes instantly in O1 time. We create a dummy head node. It doesn't store real data but helps mark the left boundary of our list. And a dummy tail node, marking the right boundary, where most recently used items will go. We connect head to tail to form an empty list, and connect tail back to head, completing the two-node base structure. This helper method removes a node from the doubly linked list in O1 time. We grab the node's neighbors, the one before and the one after. We link the previous node forward to the next node, and link the next node back to the previous. The node is now fully detached. This helper pushes a node to the most recently used spot, right before the tail. We get the node currently at the end. We attach our new node right after that node, and set its backward pointer. This node should sit right before the tail boundary. We finalize the connection. Tail now points back to our newly added node. This method retrieves a value and updates its recency ranking. If the key doesn't exist in the hash map, we return -1, signaling a cache miss. We fetch the node in O1 time through the hash map. We detach the node from its current position, and move it to the tail, the most recently used spot. We return its stored value. Simple and fast. This method inserts a key value pair or updates an existing one. If the key already exists, we're updating it. We fetch the node from the hash map. We update its value. We remove it from its current position, and reinsert it at the tail as most recently used. If the key is brand new, we create a fresh node holding this key value pair, and store it in the hash map for quick lookup. We add it to the tail, again marking it as most recently used. If the cache size now exceeds capacity, we must evict the LRU item. The least recently used item always sits right after the dummy head. We remove that node from the list, and delete it from the hash map, completely removing it from the cache. And that's how this algorithm works. It first builds a fast lookup table with a hash map, then manages recency using a doubly linked list. Recently used items move to the tail, and the least recently used one is evicted from the head. Efficient, simple, and elegant. Let us test our LRU cache that uses a doubly linked list and a hash map with these operations. They represent inserting keys, accessing them, and evicting entries once the cache reaches capacity. We start with capacity 2. Insert key 1 with value 1, and key 2 with value 2. Calling get of 1 returns 1 and moves key 1 to the most recently used position. Inserting key 3 with value 3 forces an eviction, and the least recently used key is 2. So key 2 is removed. Calling get of 2 correctly returns -1. Next, inserting key 4 with value 4 evicts key 1, since it is now the least recently used. The final get calls return -1 for key 1, then 3, then 4. Everything follows the LRU rules exactly. And that is exactly what our program outputs. Every result matches the expected behavior. So our implementation is correct. The linked list and hash map structure is maintaining LRU order precisely and returning values in constant time. If you want to show real systems thinking in an interview, the LRU cache is it. Constant time lookups, constant time updates, and precise eviction. It proves you can pair the right data structures to hit strict performance targets. Let's do a recap. The task is to design a cache with a fixed capacity that supports 2 operations in O1. Get key returns the value and marks it most recently used. Put key, value, inserts or updates, and if we're over capacity, evicts the least recently used entry. We compared options and landed on the classic pairing, a hash map for instant key lookup, and a doubly linked list to maintain usage order. This combination avoids linear scans and lets us move items to most recent or evict from least recent in constant time. The plan is simple and disciplined. The map stores key node, and the list orders nodes from most recently used at the head to least at the tail. Helpers handle add to head, remove from list, move to head, and pop from tail. Get moves the access node to the head, put updates or inserts, then evicts from the tail if needed. We followed that blueprint exactly, using head/tail sentinels for clean pointer ops, and successfully ran the solution on LeetCode without any errors. We verified behavior through LeetCode runs, accesses updated recency correctly, evictions occurred at capacity, and all test cases passed as expected. The takeaway: great performance comes from the right pairing. Hash map plus doubly linked list gives true O1 for both operations, and shows you can design for speed, order, and correctness all at once.
LeetCode says medium. Your nervous system says boss fight. That is your sign you need pattern training. PatternMastery.com.
Stacks are interview catnip. Evaluate reverse Polish notation, RPN. Looks tiny, but it reveals whether you truly understand order of operations and data structures. Phone screens love it because one clean stack pass solves everything. No parentheses panic, no precedence chaos. Let's crush it with basic and finish with rock-solid, production-ready code. We're given a list of tokens representing an arithmetic expression in postfix form. Operands are integers. Operators are plus, slash. Evaluate the expression and return an integer, with division truncating towards 0. RPN is tailor-made for a stack. Scan left to right, push numbers. When we see an operator, pop the last 2 operands, write operand first, apply the operator, and push the result. Single pass, ON time, ON worst case space. Watch the Python gotcha. Integer division must truncate towards 0, use int a, b, not a // b. Plan. Create stack equals. For each token t, if t is an operator, pop b, then a, compute a, t, b, push result. Else, push in t. At the end, top of stack is the result. Let's try to implement it using solution 1. We define a solution class, the standard structure LeetCode expects. This method evaluates an expression written in reverse Polish notation, RPN. We create a stack to store numbers and intermediate results. We iterate through each token from left to right. If the token isn't an operator, it must be a number. We convert it to an integer and push it onto the stack. Otherwise, the token is an operator and we need to compute a result. We pop the second operand, and then the first operand. We apply the correct operation to A and B. We push the computed value back onto the stack. When all tokens are processed, the final answer is the only value left on the stack. And that's how the algorithm works. It scans tokens, pushes numbers, applies operations when needed, and leaves the final evaluated value on the stack. Efficient, simple, and elegant. Tokens equals 2, 1, plus 3. Let's test our function using this input, 2, 1, plus 3. These tokens represent an arithmetic expression written in reverse Polish notation, RPN, where the operators come after the numbers, what the input represents in RPN. Numbers get pushed onto the stack. When an operator appears, it applies to the 2 most recent numbers on the stack. So the expression here is push 2. Push 1. Apply plus compute 2 plus 1 equals 3. Push 3. Apply compute 3 times 3 equals 9. This is equivalent to the normal infix expression. 2 plus 1, 3. Here's why the solution works. Our stack-based algorithm handles this input perfectly. 2 push 2. 1 push 1. Plus pop 2 and 1 compute 2 plus 1 push 3. 3 push 3. Pop 3 and 3 compute 3 times 3 push 9. At the end, the stack contains a single value, 9. And that's exactly what our program outputs. 9. This matches the expected answer, so the test case passes successfully. So, our implementation is correct. The algorithm successfully evaluates the reverse Polish notation expression by pushing numbers, applying operators when needed, and leaving the final result on the stack, efficient, accurate, and reliable. Now let's try another implement approach using solution 2. We import operator to use built-in math functions. We define the standard solution class. This method evaluates an RPN expression. We map each operator, plus, slash, to a function, using a lambda for division to handle truncation. We create a stack to hold numbers and results. We process each token in order. If it's an operator, we apply it. We pop 2 operands. We compute the result using the operator map and push it back. If it's a number, we convert and push it. The final value on the stack is the answer. Time complexity, O(n), space, O(n). And that's how this algorithm works. A clean operator map plus a simple stack to evaluate RPN efficiently. Tokens equals 2, 1, plus 3. Let's test our function using this input, 2, 1, plus 3. These tokens represent an arithmetic expression written in reverse Polish notation, where each operator applies to the 2 most recent numbers on the stack. This expression corresponds to the calculation. Push 2. Push 1. Apply plus becomes 3. Push 3. Apply becomes 9. So mathematically, it's the same as 2 plus 1, 3. Here's why the solution works. Our operator map version handles this very cleanly. 2 not an operator push 2. 1 push 1. Plus operator pop 1 and 2 compute 2 plus 1 equals 3 push 3. 3 push 3. Operator pop 3 and 3 compute 3 times 3 equals 9 push 9. At the end, the stack contains exactly one value, the final result. 9, and that's exactly what our program outputs, 9. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully evaluates the reverse Polish notation expression using a clean operator map and a stack, efficient, accurate, and reliable. Ever feel like arithmetic expressions get messy with all the parentheses and operator rules? Evaluate reverse Polish notation flips that chaos into clarity. With one clean stack pass, everything falls neatly into place. No precedence worries, no nested confusion. We're given tokens representing a mathematical expression in postfix form, numbers and operators in sequence. Our goal is to evaluate it and return the final integer result, with division that truncates toward 0. Conceptually, it's about understanding how stacks mirror computation order in a structured, step-by-step way. The beauty of RPN lies in its simplicity. As we scan tokens left to right, numbers are pushed onto a stack. When we hit an operator, we pop the top 2 numbers, apply the operation, and push the result back. No need for parentheses or operator precedence tables. The key detail: ensure division behaves like real integer truncation toward 0. Here's the logical plan. Initialize an empty stack. For each token, if it's a number, push it. If it's an operator, pop 2 numbers, right then left, compute, and push the result. At the end, the single value left on the stack is the final answer. We followed that flow precisely. One stack, one pass. The operations handled correctly, especially division truncation. The code ran smoothly on LeetCode without any errors. We validated the logic across multiple test cases, from simple additions to chained multiplications and mixed divisions. Each case matched the expected output: consistent, correct, and efficient. The takeaway? Mastering stack-based evaluation isn't just about RPN, it's about learning to break problems into simple, repeatable actions. Once you see how order unfolds naturally through a stack, complex expressions become effortless to decode.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Have you ever stared at a weather app and wondered, how many days till it gets warmer? Daily Temperatures is a PatternMastery 100 favorite that silently checks your mastery of the monotonic stack, a pattern that powers dozens of array problems at FANG. We'll turn scattered temps into instant answers with a clean ON sweep using the basic framework. Let's go. We have an integer array temperatures. For each day I, we must return how many days you'd wait until a warmer temperature. If none exists, return 0 for that day. Output is an array the same length as input. Brute force is O(n) squared, checking forward from each day. Instead, use a monotonic decreasing stack of indices. As we scan from left to right, we'll pop cooler days when today is warmer and compute their wait lengths in O(1) each. Total runtime O(n), extra space O(n) for the stack and results. Plan. Create n's filled with zeros and an empty stack st for indices. Iterate days I from 0, n1, while stack not empty and temperatures I, greater than temperatures st-1, pop j equals st.pop and settings j, equals I, j, push I onto the stack. Leftover indices have no warmer day remain 0. Let's try to implement it using solution 1. We begin by defining a solution class. This is the usual container so platforms like LeetCode know where our method exists. This is our main function. It takes in temperatures, a list of daily temperatures, and our job is to figure out how many days you have to wait until a warmer temperature appears for each day. We store the length of the list in n. This helps us build our answer list and loop through the temperatures. It is super simple and constant time. We create a result list filled with zeros. Each position starts at 0, which means no warmer day has been found yet. We will update these values as we discover warmer days. Next, we create an empty stack. This will store indices of days whose warmer future temperature we have not found yet. We will use a monotonic decreasing stack, which means the temperatures at the indices inside the stack will always be in decreasing order as we go inward. Now we loop through each temperature using enumerate, so I is the current day index, and T is the temperature on that day. We will check whether today's temperature is warmer than previous days we are tracking. This is the core logic. While there are days in the stack, and today's temperature T is warmer than the temperature at the top of the stack, it means we have finally found a warmer day for the day stored at stack of index -1. We pop that index j from the stack, which means we found a warmer temperature for day j. That day is now resolved. We record how many days it took to reach a warmer temperature. That is today's day index minus the previous day index. For example, if day 2 gets popped while we are on day 5, then reset index 2 becomes 5 minus 2, which equals 3 days of waiting. After checking for matches, we push the current day I onto the stack. We have not yet found a warmer day for today, so it stays on the stack until a future temperature beats it. In the end, the res list contains the number of days each temperature needs to wait until a warmer one appears. If no warmer day exists, it stays as 0, which is exactly what we want. And that is how this algorithm works. It uses a monotonic stack to keep track of unresolved days, then updates them as soon as a warmer temperature appears. Efficient, simple, and elegant. Let us test our function using this input. These numbers represent the daily temperatures for 8 consecutive days, and our goal is to figure out how many days each temperature must wait until a warmer day arrives. What the input represents. Each number is the temperature of a day. For example, day 0 is 73. Day 1 is 74. Day 2 is 75. And so on. Some days will have a warmer day ahead, and some will not. That is exactly what the algorithm resolves using a monotonic stack. Here is why the solution works. Our stack-based algorithm walks through the temperatures and keeps track of days that have not yet found a warmer day. Let us look at a few key steps. On day 0, which is 73, no comparison yet, so the stack is 0. Day 1 is 74, which is warmer than day 0 at 73, so day 0 waited 1 day. Day 2 is 75, which is warmer than day 1 at 74, so day 1 waited 1 day. Day 3 is 71, which is cooler, so it stays in the stack. Day 4 is 69, and it also stays in the stack. Day 5 is 72, which is warmer than day 4 at 69, so day 4 waited 1 day. It is also warmer than day 3 at 71, so day 3 waited 2 days. Day 6 is 76, which is warmer than earlier days and resolves several positions in the stack. Day 7 is 73, which is not warmer than day 6 at 76, so the last 2 positions get a waiting time of 0. By the end, every index in the output array correctly represents the number of days until the next warmer temperature. And that is exactly what our program outputs. This matches the expected result perfectly. Our implementation is correct. The algorithm successfully computes the number of days until a warmer temperature using a monotonic stack. It is efficient, accurate, and reliable. Now let's try another implement approach using solution 2. We start by defining the solution class. This is just the standard wrapper so platforms like LeetCode know where to find our method. Here we define daily temperatures. It takes in temperatures, a list of daily temperatures, and we want to return, for each day, how many days to wait until a warmer temperature. If no warmer day exists, we leave it as 0. We store the length of the list in n. We will use this to loop from right to left and to check bounds. This is O of one time. We create a result array res filled with zeros. Res at index I will eventually hold the number of days you need to wait from day I to reach a warmer temperature. If it stays 0, that means there is no future warmer day for that index. Now we loop backwards from the second to last day, which is n-2, down to day 0. Why backwards? Because we use information we have already computed for days to the right to speed things up. This loop runs n-1 times, so it is O of n iterations. For each day I, we start by looking at the next day, I plus 1. We will try to find the next warmer day starting from there, potentially jumping ahead using the res array. This while loop says, as long as we are within the array, and the temperature at day j is not warmer than day I, meaning it is less than or equal, keep searching further ahead. So we stay in this loop while we have not found a warmer day yet for day I. Inside the loop, we first check whether res at index j equals 0. This means that from day j onward, there is no warmer day, because earlier we already computed that for j. So if j itself is not warmer than I, and res at j is 0, then there is no point going further. We already know it will not get warmer from there. In that situation, we set j equal to n. This is a neat trick. It forces the while loop condition j less than n to become false, which signals that no warmer day was found for day I via this path. We break out of the while loop early because we now know there is no warmer temperature in the future for day I through this route. If res at j is not 0, that means day j does know where its next warmer day is. It is exactly res at j days ahead. Instead of moving one day at a time, we jump forward by res at j days. This is the dynamic programming jumping idea. We reuse previously computed answers to skip over stretches of days that we already know are not warmer, which makes it faster than stepping one day at a time. After the while loop, if j is still within bounds, meaning j is less than n, it means we did find a warmer day for day I at index j. In that case, we set res at index I to the number of days between I and that warmer day j. So if I equals 2 and we found a warmer day at j equals 6, we store res at index 2 as 6 minus 2, which equals 4. Finally, we return the res array. Each entry tells us how many days to wait until a warmer temperature appears for that day, or 0 if no such day exists. And that is how this algorithm works. It walks backward to reuse already computed next warmer day distances, then uses those distances to jump ahead and quickly locate the next warmer temperature for each day. Efficient, simple, and elegant. Let us test our function using this input: 30, 40, 50, 60. These values represent the temperatures over 4 days. Since the temperatures rise every single day, each day except the last one has a warmer day immediately after it. What the input represents, each number is the temperature of that day. Because the pattern is strictly increasing, this is one of the simplest cases to analyze. Every day finds a warmer temperature the very next day, except the final day, which has no future days left. Here is why the solution works. Our algorithm moves from right to left, reusing results to quickly determine the wait time. Day 3 has temperature 60. There is no future day, so the result is 0. Day 2 has temperature 50. The next day, 60, is warmer, so the wait is 1 day. Day 1 has temperature 40. The next day, 50, is warmer, so the wait is 1 day. Day 0 has temperature 30. The next day, 40, is warmer, so the wait is 1 day. Because the temperatures rise consecutively, every day except the last one has a waiting time of exactly 1 day. And that is exactly what our program outputs. 1, 1, 0. The output matches the expected result perfectly. So our implementation is correct. The algorithm handles strictly increasing temperatures exactly as expected and returns the correct number of days to wait for each warmer day. Let's have a quick recap. Breakdown recap. The problem turns courses and prerequisites into a directed graph. Each rule take A after B becomes an edge. The real question, does the graph contain a cycle? If there is a cycle, you cannot finish the courses. If there is no cycle, all courses can be completed. Assess recap. 2 approaches solve it cleanly: DFS with state marking, or BFS using Kahn's algorithm with in-degree tracking. DFS is direct for cycle detection. Kahn's algorithm is equally effective for building a valid order. Important details include handling multiple valid orders, disconnected subgraphs, and trivial cases like having no prerequisites. Structure recap. The plan. Build an adjacency list. Track each node's state: unvisited, visiting, or visited. Run DFS on each course. If DFS ever revisits a node that is still in the visiting state, a cycle exists. Mark nodes as visited after exploring all neighbors. If no cycle is detected, the schedule is feasible. Implement recap. We built the graph, initialized a state array, and ran DFS across all nodes. We stopped early whenever a cycle appeared. The implementation ran correctly on LeetCode. Check recap. We tested successful chains, failing cycles, and edge cases such as empty prerequisite lists and disconnected components. The solution behaved correctly across all scenarios. Key insight. Dependency problems reduced to cycle detection. If you can model the graph, track node states, and reason through recursive exploration, you can solve any ordering problem with confidence.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Imagine you're updating a spreadsheet. If one cell is bad, the whole row and column must be wiped clean. Set matrix zeros is a PatternMastery 100 must-have, featured at Google, Meta, and Amazon to test your space optimization and matrix manipulation skills. Over 35% of candidates use extra space or miss subtle row/col edge cases. Master this and you'll be ready for any advanced in-place update problem.
Let's break down set matrix zeros using the basic approach, so you can tackle any in-place grid update question with confidence. Given an MXN matrix, if an element is 0, set its entire row and column to 0, in place. 2D list matrix, of size MXN. The matrix is updated in place. Imagine handling a data table where any bad sensor reading, 0, wipes out all readings in that row and column for analysis. Interviewers might ask, how do you update a matrix based on its own data, without using a lot of extra memory? What's tricky? Naive. Use extra arrays to mark all rows/cols with 0 OM plus N space. Optimal. Reuse the first row and first column of the matrix itself for markers, O1 space. Must handle the special case of first row and column carefully, as they're both data and markers. First, scan the first row and column to check if they need to be zeroed at the end, save 2 flags. For each cell, I, J, if it's 0, mark its row and column by setting matrix I0 equals 0 and matrix 0J equals 0. On a second pass, use the markers to set cells to 0, skip the first row and column for now. Finally, zero out the first row/column if needed, using your flags. Let's clarify. Markers in the first row/col allow you to track zeros without extra space. The first row and column are handled last to avoid overwriting markers early. Edge cases. All zeros, full matrix zeroed. No zeros, matrix stays as is. Only first row/col have zeros. Use 2 flags, first row 0, first col 0. Scan the matrix for zeros, set markers in first row/col. In a second pass, for cells I, J, accept first row/col, if matrix I0 equals 0 or matrix 0J equals 0, set matrix IJ equals 0. Zero out the first row/col if needed. 3 passes, 1 for flags/markers, 1 to update cells, 1 to update first row, col if needed. No extra arrays. Now let's solve solution 1, setting entire rows and columns to 0 in a matrix if any cell is 0, using extra sets. We'll see how to first record which rows and columns have zeros, and then update the matrix accordingly. Time complexity is OM times N, where M is the number of rows and N is the number of columns. We traverse the matrix twice, once to record zeros, once to update values. The idea: traverse the matrix once and record rows and columns that contain zeros using sets. Traverse again, and set any cell to 0 if it belongs to a recorded row or column. Think of it like marking rows and columns that need cleaning, then wiping them in a second pass. We define a class solution to contain our method. This function takes a 2D list matrix and updates it in place according to the 0 rules. Compute the number of rows M and columns N in the matrix. Initialize 2 sets to keep track of which rows and columns should be zeroed. Traverse each cell in the matrix. If a cell is 0, Add its row index to 0_rows and column index to 0_columns. Traverse the matrix again. If the current row or column is in the sets, set the cell to 0. This updates the matrix in place. And that's how this algorithm works. It first records which rows and columns contain zeros, then updates the matrix by setting all relevant cells to 0. Efficient, simple, and easy to understand. Time complexity, OM times n, 2 passes through the matrix. Space complexity, OM plus n, storing row and column indices in sets. Simple and intuitive solution using extra memory to track zeros.
We have a matrix where any 0 sets its entire row and column to 0. Input 111101111. The solution records which rows and columns have 0, then updates them. Output 1010000101. The function works correctly and efficiently.
This solution sets entire rows and columns to 0 if a 0 appears in the matrix. We use extra sets to remember which rows and columns need zeroing. It's simple and easy to understand. Time complexity is OM times n, where m is the number of rows and n is the number of columns. We traverse the matrix twice, once to record zeros, and once to update the matrix. Define a class solution and the function set zeros. Get the number of rows m and columns n in the matrix to help loop through every element. Create 2 empty sets to store the row indices and column indices that contain zeros. Loop through every cell. If a 0 is found, add the row index to 0_rows and the column index to 0_columns. Loop through the matrix again. If a cell is in a 0 row or 0 column, set it to 0. This approach uses OM plus n, extra space for the sets. Each cell is visited twice, giving OM times n time. It is easy to understand and implement.
We have a 3 times 4 matrix, 0 1 2 0 3 4 5 2 1 3 1 5. Every 0 sets its entire row and column to 0. The solution first records which rows and columns contain zeros, then updates the matrix accordingly. The output is 0000045003110. This confirms the function works correctly, efficiently updating all affected rows and columns.
Breakdown recap. Conceptually, whenever a cell is 0, its entire row and column must be set to 0. The challenge is to do this in place without using extra memory beyond a few variables. Assess recap. A naive approach uses additional arrays to track which rows and columns need zeroing, but that costs extra space. The optimal approach cleverly reuses the first row and first column as markers while keeping track of whether they themselves need zeroing. This reduces space complexity to 0.1 while maintaining clarity and correctness. Structure recap. Here's the plan. Use 2 flags for the first row and first column to know if they need zeroing. Scan the matrix. For each 0 found, mark its row and column in the first row and first column. In a second pass, update the cells based on these markers, excluding the first row and column. Finally, zero out the first row and first column if the flags indicate it's needed. Implement recap. We implemented 3 passes, first to set markers and flags, second to update the inner matrix, and third to handle the first row and column. Running this on LeetCode executes cleanly and efficiently without extra arrays. Check recap. We verified that the solution handles all edge cases, including matrices with all zeros, no zeros, or zeros in the first row/column. Time complexity is OMN, and space complexity is O1. Closing insight. The key takeaway? By cleverly using the matrix itself as markers and handling the first row and column last, you can update the grid in place efficiently and elegantly. This approach generalizes well to many in-place matrix update problems in interviews.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Have you ever tried reading a maze from the outside in, layer by layer? Spiral Matrix is a PatternMastery 100 classic and a frequent test at Google, Meta, and Amazon. Over 30% of candidates trip up on edge cases or lose track of their boundaries. Master this, and you'll ace any 2D traversal or matrix boundary manipulation question.
Let's break down Spiral Matrix using the basic approach, so you'll confidently handle any 2D matrix traversal in an interview. Given an MXN matrix, return all elements of the matrix in spiral order. 2D list matrix, of size MXN. List of integers, values in spiral order. Think of printing all the numbers in a Sudoku board from the outermost cells to the very center, like peeling an onion. An interviewer might ask, how would you read or process data from the edges inward in a 2D grid? What's tricky? Keeping track of the boundaries as you spiral inward. Handling non-square matrices, for example, 3x4, 4x3. Avoiding double counting elements at boundaries. Use 4 boundaries: top, bottom, left, right. At each step, traverse. Left to right, top row. Top to bottom, right column. Right to left, bottom row, if not revisited. Bottom to top, left column, if not revisited. After each traversal, shrink the corresponding boundary. Repeat until boundaries cross. Let's clarify. Check that after moving left/right or up/down, the other boundaries haven't already crossed. Careful handling when there's a single row or column left. Edge cases. Matrix is empty. Return. Matrix is just one row or column. Initialize top equals 0, bottom equals m1, left equals 0, right equals n1. While top less than equals bottom and left less than equals right. Traverse from left to right along top, increment top. Traverse from top to bottom along right, decrement right. If top less than equals bottom, traverse right to left along bottom, decrement bottom. If left less than equals right, traverse bottom to top along left, increment left. Collect all elements in a result list. Now let's solve solution 1, traversing a matrix in spiral order. We will see how to move layer by layer, adjusting the boundaries as we go. Time complexity is OM times N, where M is the number of rows and N is the number of columns. Each cell is visited exactly once we define a class solution to contain our method. The function spiral order takes a 2D matrix and returns a list of elements in spiral order. If the matrix is empty, return an empty list. Initialize an empty list res to store the spiral order. Set top equals 0, bottom equal number of rows -1, left equals 0 and right equal number of columns -1 to define the boundaries, while top less than or equal to bottom and left less than or equal to right. Traverse the top row from left to right and append each element to res. Then increment top. Traverse the rightmost column from top to bottom and append each element to res. Then decrement right. If top less than or equal to bottom, traverse the bottom row from right to left and append each element to res. Then decrement bottom. If left less than or equal to right, traverse the leftmost column from bottom to top and append each element to res. Then increment left. Return res containing all elements in spiral order. This algorithm works by initializing boundaries and then traversing layer by layer in 4 directions, adjusting the edges until all elements are collected. Time complexity is OM times N. Space complexity is O1 extra. Aside from the result list, it handles both rectangular and square matrices, and provides an intuitive layer by layer traversal using simple loops. Before checking the output, let's understand the problem. We are given a matrix, and the goal is to traverse it in spiral order. Start from the top left corner. Move right, down, left, up, shrinking the boundaries as you go. Continue until all elements are visited. Let's test our function with this matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. We want to traverse it in a spiral starting from the top left corner. Here's why the solution works. Set boundaries. Top equals 0, bottom equals 2, left equals 0, right equals 2. Spiral traversal. Step 1. Traverse top row, left to right. Add 1, 2, 3, then top plus equals 1. Step 2. Traverse right column, top to bottom. Add 6, 9, then right equals 1. Step 3. Traverse bottom row, right to left. Add 8, 7, then bottom equals 1. Step 4. Traverse left column, bottom to top. Add 4, then left plus equals 1. Step 5. Now only the center remains. Add 5. The final result becomes 1, 2, 3, 6, 9, 8, 7, 4, 5. And that is exactly what the program outputs. 1, 2, 3, 6, 9, 8, 7, 4, 5. This confirms that the spiral traversal is working correctly. So, our implementation is correct. It successfully traverses any matrix in spiral order. Accurate, clear, and reliable. Our implementation is correct. It correctly traverses the matrix in spiral order. It handles shrinking boundaries automatically. It works for matrices of any size or shape. This solution prints all elements of a matrix in a spiral order, moving from the top row, then the right column, bottom row, and left column, layer by layer. We track the current boundaries of the layers in place. Time complexity. OMN. M is the number of rows and N is the number of columns. Every element is visited exactly once. Maintain 4 pointers, top, bottom, left, and right to track the current layer. Move in 4 directions, left to right across the top row, top to bottom down the right column, right to left across the bottom row, bottom to top up the left column. After each pass, update the boundaries to avoid revisiting elements. Continue until all elements are added to the result list. First, check if the matrix is empty or has no columns. If it is empty, return an empty list. Create the result list and set 4 pointers for the current boundaries, top, bottom, left, and right. Keep looping while the top boundary is above the bottom boundary and the left boundary is before the right boundary. This ensures there are still layers left to traverse. Traverse the top row from left to right and add each element to the result. Then move the top boundary downward. Traverse the right column from top to bottom and add each element. Then move the right boundary to the left. If there are remaining rows, traverse the bottom row from right to left and add each element. Then move the bottom boundary upward. If there are remaining columns, traverse the left column from bottom to top and add each element. Then move the left boundary to the right. Return the result list containing all elements in spiral order. No extra sets or matrix copies are used. Each element is visited exactly once. This approach is simple and works efficiently for spiral traversal of matrices. Now that we've implemented our solution to traverse a matrix in spiral order, let's check how it works on an actual input. We'll see how the algorithm correctly follows the spiral path from the outer layer inward. This input is a 3x4 matrix. We want to collect the matrix elements in a spiral order, starting from the top left corner, moving right, then down, then left, and then up, continuing inward until all elements are traversed. Here's why the solution works. The algorithm maintains 4 pointers, top, bottom, left, and right to track the current edges of the remaining matrix. It traverses the top row from left to right, the right column from top to bottom, the bottom row from right to left, and the left column from bottom to top. After each full traversal of an edge, it moves the pointers inward to the next layer. Step by step for this input: traverse top row 1, 2, 3, 4, traverse right column 8, 12, traverse bottom row 11, 10, 9, traverse left column 5, traverse the remaining inner row 6, 7, and that's exactly what the program outputs. 1, 2, 3, 4, 8, 12, 11, 10, 9, 5, 6, 7. This confirms the algorithm correctly follows the spiral order for the given matrix. So, our implementation is correct. The algorithm successfully traverses any matrix in spiral order, systematic, accurate, and reliable. Breakdown recap. Conceptually, the goal is to return all elements of a matrix in spiral order. The challenge lies in carefully tracking boundaries and ensuring no element is visited twice. Assess recap. A naive approach risks revisiting cells or mishandling non-square matrices. The optimal approach uses 4 boundaries, top, bottom, left, right, and systematically traverses the matrix while shrinking these boundaries after each pass. This ensures every element is visited exactly once in order. Structure recap. The plan is straightforward. Initialize top, bottom, left, and right boundaries. Loop while top less than or equal to bottom and left less than or equal to right. Traverse left to right along the top row. Traverse top to bottom along the right column. Traverse right to left along the bottom row, if not revisited. Traverse bottom to top along the left column, if not revisited. Shrink the boundaries after each traversal. Implement recap. We implemented this with a simple loop, appending elements to a result list as we spiral inward. The code runs cleanly on LeetCode, handling all matrix shapes without error. Check recap. We verified edge cases such as empty matrices, single rows, and single columns. Every element is visited exactly once, giving OM times n, time and OM times n, space for the result. Closing insight. The key takeaway? By managing boundaries carefully and moving systematically, you can traverse any 2D matrix in spiral order efficiently and safely, a versatile skill for many matrix-based interview problems.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
How do you rotate a digital photo in place, with no extra space? Rotate image is a PatternMastery 100 favorite and a frequent question at Google, Amazon, and Facebook, designed to test your understanding of matrix manipulation. Over 35% of candidates either use extra space or get tangled in index math. Master this, and you'll ace matrix transformations in any interview. Let's break down rotate image using the basic approach, so you can confidently tackle any in-place matrix manipulation problem. Given an NXN 2D matrix representing an image, rotate the image by 90 degrees, clockwise, in place, i.e., don't use another matrix. Input. 2D list matrix, NXN integers output. The matrix is modified in place. Interviewer might ask, how would you rotate a digital image in place for real-time rendering? What's tricky? Must rotate in place, no extra space for another matrix. Need to move elements layer by layer, or use clever matrix transposition and row reversal. Index calculations for four-way swaps can trip you up. There are two classic approaches. Transpose and reverse. Transpose the matrix, swap rows and columns. Reverse each row. Layer by layer four-way swap. For each layer, move elements in groups of 4, rotating their positions. Let's clarify the transpose and reverse method. Transpose. For each cell, I, j, with I less than j, swap matrix ij, and matrix ji. Reverse. For each row, reverse its elements. Transpose the matrix. For I in 0 to n1. For j in I plus 1 to n1. Swap matrix ij, and matrix ji reverse each row. For each row in matrix. Reverse row in place. Now, let's break down the first Python solution for rotate image, a clean two-step strategy that flips the matrix and then reverses it to achieve a perfect 90-degree rotation. We start by defining the solution class. LeetCode looks inside this class to find the rotate function to run. This defines our rotate method. It receives the matrix we want to rotate 90 degrees clockwise. We take the size of the matrix. Since this is an n times n square grid, n tells us how many rows and columns we have. We begin our first loop, iterating through each row index I. Inside that, we loop through each column index j, starting from I plus 1. This ensures we only visit the upper right triangle of the matrix, avoiding unnecessary swaps. Here's the key operation. We swap the element at row I, column j with the element at row j, column I. This operation transposes the matrix, it flips the matrix over its diagonal. Since we touch each pair once, this transpose step contributes to the O(n) squared time complexity. Now we start a second loop over each row. We reverse the entire row in place. Reversing each row after transposing gives us the final 90-degree clockwise rotation. And that's how this algorithm works. It first transposes the matrix to swap rows and columns, then reverses each row to finish the rotation. Efficient, simple, and elegant. Test case check. Let's walk through it. Input matrix equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's test our function using this input matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. You can think of this as a 3 times 3 image, where each number is a pixel value. First row, 1, 2, 3. Second row, 4, 5, 6. Third row, 7, 8, 9. Our job is to rotate this image 90 degrees clockwise, in place. Quick logic check. After a 90 degrees clockwise rotation, the original bottom row, 7, 8, 9, becomes the new left column, 7, 4, 1. The middle column forms, 8, 5, 2. The original top row, 1, 2, 3, becomes the new right column, 9, 6, 3. So the rotated matrix should be 7, 4, 1, 8, 5, 2, 9, 6, 3. Output 7, 4, 1, 8, 5, 2, 9, 6, 3. And that's exactly what our program outputs, 7, 4, 1, 8, 5, 2, 9, 6, 3. It matches the expected result perfectly, which confirms that our in-place rotation logic is doing the right thing. So, our implementation is correct. The algorithm successfully rotates the matrix 90 degrees clockwise without using extra space, efficient and accurate. We begin by defining the solution class. This is the structure where LeetCode reads our rotate method from. This defines our function. It receives an n times n matrix and rotates it 90 degrees clockwise in place, meaning we must modify the original matrix without creating a new one. We store the size of the matrix, n. Because the input is always a square matrix, n gives us both the number of rows and the number of columns. We begin looping through each layer of the matrix. Think of the matrix like an onion. It has layers that we rotate one at a time. n/2 ensures we cover only the outer half, because rotating an outer layer also moves the inner layer. Inside each layer, we loop across the elements in that layer. J moves from the start of the layer to the end of that layer, avoiding corners being rotated more than once. We temporarily store the top left cell of the current rotation cycle. This is the first step of our four-way swap. We take the value from the left column and move it to the top row. This starts the clockwise rotation. Next, we take a value from the bottom row and move it into the left column. Now we move the right column value down into the bottom row spot. Line highlighted, matrix Jn, 1, I, equals temp. Finally, we place the original top left value, stored in temp, into the right column. This completes one full four-way rotation of the cycle. And that's how this algorithm works. It first identifies each layer of the matrix, then performs a four-way swap for every element in that layer to perform an in-place 90-degree rotation. Efficient, simple, and elegant. Let's test our function using this input. 5, 1, 9, 11, 2, 4, 8, 10, 13, 3, 6, 7, 15, 14, 12, 16. These numbers represent a 4 times 4 matrix, which you can think of like a square image or grid of values that we want to rotate 90 degrees clockwise. Here's why the solution works. The algorithm rotates the matrix in place so that the first column from the bottom becomes the first row in the new matrix. The next column from the bottom becomes the second row, and so on. For example, the original first column, top to bottom, is 5, 2, 13, 15. After rotation, these appear reversed as the top row, 15, 13, 2, 5. The original second column is 1, 4, 3, 14. After rotation, it becomes the second row, 14, 3, 4, 1. The original third column, 9, 8, 6, 12, becomes 12, 6, 8, 9. And the original fourth column, 11, 10, 7, 16, becomes 16, 7, 10, 11. So, the fully rotated matrix is 15, 13, 2, 5, 14, 3, 4, 1. 12, 6, 8, 9, 16, 7, 10, 11. And that's exactly what our program outputs. 15, 13, 2, 5, 14, 3, 4, 1, 12, 6, 8, 9, 16, 7, 10, 11. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully rotates the entire matrix 90 degrees clockwise in place, efficient, accurate, and reliable. So, let's wrap it up. The rotate image problem is one of those elegant matrix challenges that looks simple but quickly exposes whether you really understand in-place transformations. No shortcuts, no extra space. We started by restating the goal. Rotate an n by n matrix 90 degrees clockwise, directly in place. It's about repositioning every element exactly where it belongs, just like rotating a digital photo pixel by pixel, without creating a new copy. We compared two main strategies, the transpose and reverse method versus the layer-by-layer four-way swap. Both work, but the transpose and reverse approach is simpler, cleaner, and easier to explain in interviews. The key challenge? Managing indices correctly while staying truly in place. Our plan was straightforward. First transpose the matrix by swapping rows and columns, then reverse each row to complete the 90 degrees rotation. 2 simple passes, 0 extra space. We followed that logic precisely, ran the code on LeetCode, and it executed successfully. No errors, no extra memory used. We verified the results, and every test case passed exactly as expected, confirming that our rotation logic holds up perfectly for all matrix sizes. The big takeaway? Mastering in-place transformations like this builds your confidence with array and matrix manipulation, a skill that's essential not just for interviews, but for real-world data and graphics processing challenges.
Wake up. Work. Scroll jobs.
Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Ready for a grid search that trips up even the best? Word Search is a Pattern Mastery 100 classic and a go-to at Google, Amazon, and Microsoft for testing backtracking and matrix exploration skills. Over 35% of candidates make off by one or revisit bugs. If you can crack this, you're truly ready for matrix pathfinding in any interview. Let's break down word search with the basic approach, so you can confidently navigate tricky grids and recursion. Given a 2D grid of letters and a word, determine if the word exists in the grid. The word must be constructed from letters of sequentially adjacent cells, horizontally or vertically, and the same cell may not be used more than once. Input. 2D grid of characters, board. String word. Output. Boolean. True if word exists in the grid, false otherwise. Think about a mobile game where users swipe letters to form words. Your algorithm checks if a word can be formed with one continuous, legal swipe. An interviewer might ask, how would you design a feature for a crossword app to validate user input on the fly? What's tricky? Must track visited cells, can't revisit within a single search path. Need to try every possible starting point in the grid. Backtrack if a path doesn't lead to a solution. Loop through every cell in the grid. For each cell, use DFS, backtracking, to attempt to build the word. If the current cell matches the next letter, recursively check all four directions, up, down, left, right. Mark the cell as visited so it isn't reused in the current path. If you reach the end of the word, return true. If the path fails, backtrack, unmark the cell, and try other paths. If no path works, return false. Let's clarify. Use a temporary mark, like setting to hash, or a separate visited set to mark cells in the path. Restore the cell after recursion to allow reuse in other paths. Carefully handle boundaries to avoid index errors. Edge cases. Word longer than total grid cells, return false. Grid with only one cell. Grid with duplicate letters. Loop over each cell in the grid. For each cell, run DFS/backtrack. If out of bounds, wrong letter, or already visited, return false. If all letters matched, return true. Mark cell as visited. Recourse in four directions. Unmark cell after recursion. If any path returns true, the word exists. Now, let's break down the first Python solution for word search, a neat depth-first search with backtracking that checks whether we can trace the target word through the grid one letter at a time. We start by defining the solution class. This is the outer container where LeetCode will look for the exist function to run. This defines our main function, exist. It takes a board, a grid of letters, and a word, and answers a yes or no question. Can we trace this word on the board by moving up, down, left, or right? Here we grab the dimensions of the grid. M is the number of rows. N is the number of columns. We'll use these to stay inside the boundaries of the board. We create a 2D list called visited with the same size as the board. Each cell starts as false, meaning we haven't stepped on that cell yet. This helps us avoid reusing the same cell twice in a single path. Now we define a helper function DFS, short for depth first search. I and j are our current row and column on the board. K is the index of the character we're currently trying to match in the word. This checks if we've already matched all the characters in the word. If K has reached the word's length, that means we've successfully traced the entire word on the board. In that case, we return true to signal success. Here we handle all the bad situations in one line. If we go off the board, I or j out of bounds. Or if we try to reuse a cell we've already visited in this path. Or if the letter in the current cell doesn't match the kth character of the word, then this path is invalid. So if any of those conditions are true, we stop and say, this root does not form the word. Now we mark the current cell as visited, like placing a temporary footprint so we don't step on it again while exploring this path. This is where the exploring happens. From the current cell, we try moving in four directions. Down, I plus 1, j up, I, 1, j right, I, j plus 1, left, I, j, 1 for each move, we advance to the next character in the word, k plus 1. If any of these four recursive calls returns true, then res becomes true. Because we branch up to 4 ways at each character, this contributes to the time complexity of about om middle.n middle.4 to the power of k, in the worst case, where k is the word length. After exploring from this cell, we undo the footprint, we mark it as not visited again. This unmarking is the backtracking step. It allows other paths to reuse this cell later. We return whether any of the 4 directions led to a successful match of the word. Back in the main function, we start a loop over every row I of the board. And inside that, we loop over every column j. Together, these two loops visit every cell in the grid as a possible starting point. For each cell, we first check if its letter matches the first character of the word. If it does, we call DFS I, j, 0, to see if we can build the entire word starting from that cell. If DFS returns true, we found a valid path. In that case, we immediately return true, because we only need to find the word once somewhere on the board. If we finish checking all cells and none of them conform the word, we return false. That means the word does not exist on the board. And that's how this algorithm works. It first sets up tracking for visited cells and a DFS helper, then tries to build the word starting from each cell, exploring in all four directions with backtracking. Efficient, simple, and elegant. Test case check. Let's walk through it. Input board equals A, B, C, E, S, F, C, S, A, D, E, E. Word equals A, B, C, C, E, D. Let's test our function using this 2D board of letters and the target word A, B, C, C, E, D. The board represents a grid where we can move up, down, left, or right, and the challenge is to determine whether we can trace the word by moving through adjacent cells without reusing any cell. Quick logic check. To form the word A, B, C, C, E, D, start at the top left, the first letter A matches. Move right to B. Move right again to C. Then move down to the next C. Move left to E. Move down to D. Every letter is found in order, and each cell is used only once, a valid continuous path. Output true. And that's exactly what our program outputs, true. This matches the expected result, confirming that the depth-first search logic is correctly exploring all valid paths. So, our implementation is correct. The algorithm successfully navigates the grid, checking each path efficiently, accurate, thorough, and fully validated by the test case. We begin by defining the solution class, the structure where LeetCode will look for our exist method. This declares our main function. It receives a grid of letters, board, and a target string, word, that we need to locate by moving up, down, left, or right. We check whether the board is empty or invalid. If so, there's no way to find any word. In that case, we immediately return false. We store the grid's dimensions. M rows. N columns will use these values to stay within the boundaries of the board. Now we define a helper function called DFS, short for depth-first search. This is where the real exploration happens. We check whether word K can be matched starting from cell I, J. If K has reached the length of the word, that means we matched every character successfully. So we return true to signal that the word has been found. This line blocks invalid moves. Moving outside the board. Or stepping on a cell whose letter doesn't match what we need at position K. If any of those conditions fail, this path cannot form the word. We temporarily store the current cell's letter so we can restore it later. We mark this cell as visited by overwriting it with a placeholder. This prevents revisiting the same cell during the current search path. This line explores four possible directions from I, J, down, up, right, and left. If any direction returns true, then the word continues correctly in that path. This branching leads to the worst-case time complexity of OMN middle.4k. After exploring, we restore the original character. This is the key backtracking step that makes the board reusable for other starting positions. We return whether any of the four directions successfully match the entire word. We now loop through all rows of the board. And for each row, we loop through all columns, checking every cell as a potential starting point. For each cell, we attempt to match the word starting at index 0. If any DFS call returns true, we're done. If any path yields success, we return true immediately. If we finish scanning the entire grid without finding the word, we return false. And that's how this algorithm works. It first checks that the board is valid, then uses depth-first search with in-place marking to explore all possible paths for the word. Efficient, simple, and elegant. Let's test our function using this input. Board equals A, B, C, E, S, F, C, S, A, D, E, E, and word equals C. This 2D array represents a letter grid, and our goal is to check whether we can trace the word C by moving horizontally or vertically through adjacent cells. Quick logic check. Here's why the solution works. We're trying to see if the word C can be found in order on the board. For example, we can start at the second row, last column where we find an S. From there, we move down to the third row, last column which contains E. Then, we move left to the cell right next to it, another E. This gives us the exact sequence SEE without revisiting cells, which satisfies the word search rules. And that's exactly what our program outputs, true. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully finds the target word by exploring valid paths in the grid, efficient, accurate, and reliable. Let's wrap it up. The word search problem is one of those interview classics that blends logic, recursion, and precision. It's the ultimate test of how well you handle grid traversal without getting lost in the details, or revisiting the same cell twice. We began by understanding the challenge. Given a grid of letters and a word, we need to check if that word can be formed by moving through adjacent cells, horizontally or vertically, without reusing any cell along the way. It's about exploring every valid path to see if the word can be built in sequence. We compared approaches and quickly saw that brute force isn't practical. Checking every possible path without structure would explode in complexity. The elegant solution is backtracking with depth-first search, trying each starting point and exploring all possible directions while marking visited cells to avoid repeats. Our plan was clear. Loop through each cell in the grid, start a DFS whenever the first letter matches, move recursively in all four directions, mark cells as visited during the search, and backtrack afterward. If we ever reach the end of the word, we know it exists in the grid. We implemented the DFS with careful boundary checks and visited tracking, ran it on LeetCode, and everything executed flawlessly, no errors, no infinite loops. After testing across multiple grids and edge cases, every run produced the expected results, confirming that our backtracking approach is both correct and efficient. The takeaway? Backtracking isn't just about recursion, it's about control. Knowing when to explore, when to back out, and how to track state cleanly is what makes this pattern so powerful. Master this, and any matrix or pathfinding problem will start to feel like second nature.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Stuck doing nested BFS from every cell? O1 matrix is the perfect test of multi-source BFS thinking. It shows up often in Phong screens because a brute force approach explodes, while the optimal solution is beautifully simple. Start from all zeros at once and ripple outward. Let's crush it with basics so you can narrate it confidently. We're given an MXN grid of zeros and ones. For every cell, return the distance to the nearest zero using 4 directional moves. Distances are shortest path lengths in an unweighted grid. Brute force, running BFS from each one, is O, MN2. Instead, think backwards. The nearest 0 to a 1 is discovered if we start BFS from all zeros simultaneously. That's multi-source BFS. Push all 0 positions into the queue with distance 0, mark ones as, or unvisited, then relax neighbors. Complexity, OMN time and OMN space. Alternative, 2 pass DP sweeping top left bottom right then reverse. High-level steps, initialize a dist grid. Put every 0 into a queue with distance 0. Set every 1 to inf, BFS. Pop a cell, try 4 neighbors. If dist near NC, greater than dist RC, +1, update an in queue. When the queue drains, dist holds the nearest 0 distance for every cell. Solution 1, multi-source BFS. We import deck to use an efficient queue for BFS. We define the solution class that will contain the method. This function returns the distance of each cell to the nearest 0. We store the number of rows and columns. We initialize a distance matrix filled with none to mark unvisited cells. We create a queue to perform BFS. We loop through all rows. We loop through all columns. If the current cell contains a 0, it becomes a BFS starting point. We mark its distance as 0 immediately. We add this 0 cell to the queue. We begin BFS, processing cells level by level. We take the next cell whose distance is already known. We explore the 4 possible directions. We compute the neighbor's coordinates. We check that the neighbor is inside the grid and hasn't been assigned a distance yet. We assign the neighbor the shortest possible distance, 1 more than the current cell. We add this neighbor to the queue so BFS can continue spreading. Finally, we return the fully populated distance matrix. Here the grid has zeros everywhere except the center cell, which is 1. We want each cell's distance to the nearest 0. All the edge cells are already 0, so their distance is 0. The middle cell is directly adjacent to zeros on all 4 sides, so its nearest distance to a 0 is 1. The output matrix matches the expected distances exactly, so our update matrix implementation is working correctly for this test case. Solution 2. Dynamic programming. 2 passes. This function computes the distance from each cell to the nearest 0. We store the number of rows and columns. We create a distance matrix filled with infinity, meaning distances are unknown. First pass, top left bottom right, we loop through each row. We loop through each column. If the cell is a 0, its distance is 0 immediately. If it's a 1, we try updating using neighbors we've already visited. We check the top neighbor. Distance may improve using the top cell. We check the left neighbor. Distance may also improve using the left cell. Second pass, bottom right top left. Now we go backwards through the rows, and backwards through the columns. We check the bottom neighbor. Distance may improve using the bottom cell. We check the right neighbor. Distance may improve using the right cell. We return the completed distance matrix. Our multi-source BFS pushes all zeros into the queue. BFS expands outward. 0 stays 0. Center 1 checks neighbors, finds a 0 distance 1. Final distances fill in perfectly. The algorithm correctly computes the shortest distance from each cell to the nearest 0, efficient, accurate, and reliable. Here the grid has zeros in the top 2 rows and a full row of 1s at the bottom. We're computing how far each one is from the nearest 0. The first 2 rows already contain zeros, so their distances remain 0. The bottom left one touches a 0 above it, distance 1. The bottom middle one also touches a 0 above it, distance 1. The bottom right one is 2 steps away from the nearest 0, distance 2. The result matches perfectly. The DP passes correctly compute the minimum distances for all cells. Center 1 closest 0 above, distance 1. Bottom one's closest 0 either directly above or diagonally, distances 1 or 2. Final distance matrix: 0, 0, 0, 0, 0, 1, 0, 1, 2, 1. The program outputs 0, 0, 0, 0, 0, 1, 0, 1, 2, 1, matching the expected result. The algorithm efficiently computes the shortest distance to the nearest 0 using multi-source BFS, accurate and reliable. Let's have a quick recap. Breakdown recap. We need the distance of each cell to the nearest 0 in a grid using 4 directional moves. It's all about finding shortest paths in an unweighted matrix. Assess recap. Instead of BFS from every 1, mn squared, use multi-source BFS, in-queue all zeros with distance 0 and expand outward. Everyone gets its nearest 0 naturally in OMN. Structure recap: initialize a distance grid. Add all zeros to the queue with distance 0. BFS outward. If a neighbor's distance can improve, update and in-queue it. Implement recap useDeck for fast queue ops. Ran the multi-source BFS once. Clean, efficient, error-free on LeetCode. Check recap: all test cases passed. Distances matched expected results. Think in reverse. Start from known points and spread out. That's the power of multi-source BFS.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
This one looks like a toy grid, until your loops explode. Rotting Oranges is a PatternMastery 100 classic that reveals whether you can recognize multi-source BFS and reason in minutes, not hours. Interviewers love it because the brute force is tempting, but the optimal approach is one elegant flood from all rotten oranges at once. Let's master it with basics. Let's break this down. We have a grid where 0 equals empty, 1 equals fresh, 2 equals rotten. Every minute, a rotten orange makes its 4 directional neighbors rotten. Return the minutes to rot all fresh, or -1 if impossible. If there are no fresh to begin with, return 0. Now let's assess it. Running BFS from each fresh cell would be mn squared. Instead, flip the perspective. All currently rotten oranges are sources with time 0. We push them all into a queue and perform a multi-source BFS. Each time we rot a fresh neighbor, we in-queue it with time t+1. Track the count of fresh. If any remain at the end, return -1. Here is the structure. Plan. Scan grid once, count fresh and in-queue all, R, C, 0, for cells with 2. BFS. Pop, R, C, T, try 4 neighbors. When we see a 1, turn it to 2. Decrement fresh, push, near, NC, T+1, and update minutes. When queue drains, if fresh equals 0, return minutes, else -1. Line highlighted, M equals len grid, N equals len grid 0. We store the number of rows and columns for easy boundary checks. Line highlighted, fresh _ count equals 0. Q equals, we track how many fresh oranges exist, and prepare a queue for rotten ones. Line highlighted, for I in range M, for J in range N, we scan the whole grid once. Line highlighted, if grid ij equals 1, Count every fresh orange. Line highlighted. Elif grid ij equals 2. Add every rotten orange to the queue. These are our BFS starting points. Line highlighted. If fresh underscore count equals 0. If there are no fresh oranges, no time is needed, return 0. Line highlighted. Directions equals 1, 0, 1, 0, 0, 1, 0, -1. These are the 4 directions where rot can spread. Line highlighted. While queue, we run BFS until no more oranges can rot. Line highlighted. Size equals len queue. Each layer of BFS represents 1 minute. Line highlighted. j equals q.pop 0. We process each rotten orange for the current minute. Line highlighted. If grid ni nj equals 1, a fresh orange becomes rotten. Line highlighted. Fresh underscore count equals 1. We update the count of fresh oranges left. Line highlighted. q.append ni nj. The newly rotten orange will spread rot in the next minute. Line highlighted. Time plus equals 1. We increase the time after finishing each BFS level. Line highlighted. If fresh underscore count equals 0, break. If all oranges are rotten, we stop early. Line highlighted. Return time if fresh underscore count equals 0 else -1. If all fresh oranges were reached, return the total minutes, otherwise, return -1. Highlight input box. Grid equals 2, 1, 1, 1, 1, 0, 0, 1, 1. Here, the rotten orange at the top left, value 2, starts spreading rot to all adjacent fresh oranges, value 1. Each minute, rot spreads outward in 4 directions. Explain briefly, minute by minute. Minute 1, the 2 fresh oranges next to the rotten one turn rotten. Minute 2, their neighbors rot. Minute 3, rot continues spreading downward. Minute 4, the final fresh orange becomes rotten. At that point, no fresh oranges remain. Highlight output box, 4, and that matches the expected result. It takes 4 minutes for every fresh orange in the grid to rot. So the BFS simulation works correctly and returns the exact time needed for full infection. Line highlighted. Class solution. We start by defining a solution class to hold our method. Pause. Line highlighted. Def oranges rotting self, grid. This function calculates how long it takes for all fresh oranges to rot, or returns -1 if it's impossible. Pause. Line highlighted. M equals len grid. N equals len grid 0. We save the number of rows, M and columns, N, for boundary checks. Pause. Line highlighted. Q equals, fresh underscore count equals 0. We create a queue for BFS and a counter for every fresh orange we find. Pause. Line highlighted. For I in range M, for J in range N, we scan the grid cell by cell. Pause. Line highlighted. If grid ij equals 1, fresh underscore count plus equals 1. When we find a fresh orange, we increment the counter. Pause. Line highlighted. Elif grid ij equals 2. q.append I, j, 0. When we find a rotten orange, we add it to the BFS queue with time 0, meaning it's rotten at the start. Pause. Line highlighted. If fresh underscore count equals 0, return 0. If there are no fresh oranges at all, everything is already rotten. Time required is 0. Pause. Line highlighted. Directions equals 1, 0, 1, 0, 0, 1, 0, -1. These are the 4 directional moves. Down, up, right, left. Pause. Line highlighted. Max underscore time equals 0. We track the maximum time it takes for the rot to spread. Pause. Line highlighted. While Q, we perform a BFS, processing rotten oranges one at a time. Time complexity. OM middle.n since we may visit each cell. Pause. Line highlighted. I, j, time equals q.pop 0. We pull out the next rotten orange, with the time it turned rotten. Pause. Line highlighted. Max underscore time equals time. We update the latest time. This always stays at the furthest minute reached. Pause. Line highlighted. For dx, die in directions. We explore all 4 neighboring cells. Pause. Line highlighted. Ni, nj equals I plus dx, j plus die. We compute the neighbor's coordinates. Pause. Line highlighted. If 0 less than equals ni less than m, and 0 less than equals nj, less than n and grid ni nj, equals 1, if the neighbor is inside the grid and is a fresh orange, it now becomes rotten. Pause. Line highlighted. Grid ni nj equals 2. Fresh underscore count equals 1. We mark it as rotten and decrease the fresh orange count. Pause. Line highlighted, q.append ni, nj, time +1. We add this newly rotten orange to the queue with time increased by 1 minute. Pause. Line highlighted, return max_time if fresh_count equals 0 else -1. If all fresh oranges are gone, we return the total time it took. If some are unreachable and remain fresh, we return -1. Pause. Final wrap-up. And that's how this algorithm works. It first collects all rotten and fresh oranges, then uses BFS to spread rot minute by minute, finally returning the required time or -1 if some oranges can never rot. Efficient, simple, and elegant. Highlight input box. Grid equals 2, 1, 1, 1, 1, 0, 0, 1, 1. Here, the rotten orange at the top left, value 2. Start spreading rot to all adjacent fresh oranges, value 1. Each minute, rot spreads outward in 4 directions. Explain briefly, minute by minute. Minute 1. The 2 fresh oranges next to the rotten one turn rotten. Minute 2. Their neighbors rot. Minute 3. Rot continues spreading downward. Minute 4. The final fresh orange becomes rotten. At that point, no fresh oranges remain. Highlight output box. 4. And that matches the expected result. It takes 4 minutes for every fresh orange in the grid to rot. So the BFS simulation works correctly and returns the exact time needed for full infection. At first glance, it's just a small grid, but rotting oranges can blow up fast if you don't think in waves. This problem tests whether you can recognize a multi-source BFS and reason through spreading processes efficiently. Let's do a recap. We're working with a grid where 0 means empty, 1 is a fresh orange, and 2 is rotten. Every minute, rotten ones infect their 4 neighbors. The goal is to find how many minutes it takes for all to rot, or return -1 if some never can. Running BFS from each orange separately is too slow. The trick is flipping the view. Start from all rotten oranges at once. This creates a synchronized BFS wave that spreads rot in minimal time while tracking each minute naturally through the queue. The plan. Scan the grid to count fresh oranges and enqueue all rotten ones with time 0. Run BFS in 4 directions. When a fresh orange turns rotten, push it to the queue with time +1. Track minutes until the queue is empty. If any fresh remain, return -1. We gathered every rotten orange as a starting point, ran 1 clean BFS across the grid, and verified the solution on LeetCode without any errors. All test cases passed. The timing and BFS propagation worked perfectly across all grids. Bullseye emoji. The key takeaway: think in waves, not steps. Multi-source BFS turns what looks like chaos into one elegant flood that models real-time spread precisely and efficiently.
LeetCode says medium. Your nervous system says boss fight. That is your sign you need pattern training. PatternMastery.com.
Flood fill is considered easy, but it's essential for mastering graph traversal and grids. It builds on efficiently coloring connected regions. This problem focuses on filling all connected cells of the same color starting from a given cell, handling edge cases with already filled cells, traversing in 4 directions, returning the updated grid. A naive approach might recurse blindly without bounds, risking stack overflow. The optimized solution. Use DFS or BFS to traverse connected same color cells. Change color upon visiting. Continue traversal to all neighbors. Single traversal ensures O of m times n time and uses O of m times n space for recursion stack or queue. The key idea is that controlled traversal efficiently fills the connected area. Let's break it down step by step. Ever clicked a paint bucket and watched color spread perfectly through a region? That's flood fill, a PatternMastery 100 staple that tests if you can control recursion/iteration, guard edge cases, and traverse grids cleanly. Interviewers love it because one tiny bug creates infinite loops. Today, we'll nail it with basics so your solution is fast and bulletproof. Let's break it down. We're given an image grid, a starting cell, SR, SC, and a new color. We must recolor all 4 directionally connected cells that share the starting cell's original color. If the original color equals new color, nothing changes. Return the image. Now let's assess it. This is a classic graph traversal on a grid. Use DFS or BFS. Watch 2 pitfalls. If new color equals old color, early return to avoid infinite revisits. Stay inbounds and only traverse cells with the old color. Complexity is OM middle.n time, OM middle.n space worst case, stack/queue, for an m times n grid. Here's the structure. Plan with BFS, Iterative and interview friendly. Read old equals image srsc. If old equals new color, return. Push sr.sc into a queue and recolor it immediately. While queue not empty, pop rc for each neighbor, near, nc, in 4 durs, if inbounds and image near nc equals old, recolor and in queue. We grab the original color at the starting pixel. This tells us what region needs filling. If the pixel is already the target color, we skip everything and return the image. These store the number of rows and columns so we can check bounds easily. This defines the 4 directions: up, down, left, right. We'll explore. We start our BFS queue with the starting cell. The starting pixel is recolored immediately as the first change. We process cells until no more connected pixels of the old color remain. Take the next pixel from the queue to explore its neighbors. We try each of the 4 directions from the current pixel. Only valid and same colored neighbors qualify for recoloring. We recolor the neighboring pixel and add it to the queue so its neighbors can be checked as well. Finally, we return the fully flood-filled image. Highlight input box. Image equals 1, 1, 1, 1, 1, 0, 1, 0, 1, SR equals 1, SC equals 1, color equals 2. Here, we start flood fill at position 1, which currently has the value 1. Our job is to recolor this pixel, and any connected pixels with the same value, to 2. Explain briefly. The pixel at 1, 1 connects to a whole block of ones around it. Up, down, left, and right. All of these connected ones get changed to 2. Pixels that are diagonal or blocked by a different number, like the zeros, are untouched. Highlight output box. 2, 2, 2, 2, 2, 0, 2, 0, 1, and that's exactly the result. All connected ones were replaced with 2, matching the expected output. So the flood fill works correctly, spreading outward from 1, 1, and recoloring only the valid connected region. We define a solution class to hold our method. This function performs a flood fill, changing connected cells of the same color to a new color. We grab the starting pixel's original color. If the starting pixel is already the target color, we don't need to change anything. We store the number of rows, m, and columns, n, for boundary checking. We define a DFS helper to explore all valid connected cells. If the cell is out of bounds or not the original color, we stop exploring. We paint the current cell with a new color. We recursively fill neighbors in all 4 directions. Time complexity, middle.n in the worst case, since we may visit all cells. We start the flood fill from the given starting pixel. We return the updated image. And that's how this algorithm works. It first checks for unnecessary work, then uses DFS to recolor all connected cells matching the original color. Efficient, simple, and elegant. Highlight input box. Image equals 1, 1, 1, 1, 1, 0, 1, 0, 1, SR equals 1, SC equals 1, color equals 2. Ever clicked a paint bucket and watched color spread instantly across a region? That's flood fill, a perfect test of clean grid traversal, recursion control, and edge handling. Let's do a recap. We're given an image grid, a start cell, and a new color. The task: recolor all connected cells, up, down, left, right, that share the starting color. If the starting color already matches the new one, we simply return the image as is. It's a classic graph traversal disguised as painting. We can use BFS or DFS, both work. The main pitfalls? Avoid infinite recursion when the color doesn't change, and stay inside bounds at all times. The plan: record the starting color. If it's already the new color, stop early. Use a queue, BFS, to recolor the start cell and expand to 4 directional neighbors with the same color. Continue until no connected cells remain. We executed this BFS plan, handled edge checks, recolored properly, and ran it on LeetCode with 0 errors. All test cases passed. Traversal and recoloring behaved exactly as expected. The big lesson: flood fill isn't just about color, it's about control. Managing boundaries and revisits cleanly proves you understand traversal flow from start to finish.
The interviewer smiled. Not because you were right, because they knew you were lost. Learn to spot the pattern before they spot the panic. PatternMastery.com
Did you know that maximum depth of binary tree is one of the most common binary tree questions at Google and Facebook interviews? This PatternMastery 100 staple is deceptively simple. But over 25% of candidates get tripped up on recursive logic or base cases. Get this right, and you'll breeze through a whole family of tree questions. Let's solve maximum depth of binary tree using the basic method, helping you analyze, reason, and implement like a pro. Let's break this down. You're given the root node of a binary tree. Your goal is to return its maximum depth, that is, the number of nodes along the longest path from root down to the farthest leaf node. Input, binary tree root node. Output, integer representing the tree's max depth. Here's a real-world example for this question. Imagine you're building a company org chart, and you need to find the maximum number of management layers between the CEO and any employee. An interviewer might ask, how would you determine the longest dependency chain in a workflow tree? Let's assess it. What's tricky? The tree can be perfectly balanced, skewed to one side, or even empty. You need to account for every possible branch. Recursion is perfect here. At each node, the maximum depth is 1 plus the larger of the left or right subtree's depth. Think step by step. For a null or empty node, depth is 0, base case. For each node, recursively compute the depth of the left and right children. The depth at the current node is 1 plus the max of the left and right subtree depths. The recursion bubbles up, calculating and combining results as it returns. Let's add more clarity. Each time you call the function on a child node, you're asking, how deep is this subtree? The maximum is always determined by the deepest path from root to a leaf node, regardless of how lopsided the tree may be. Edge cases. Empty tree, should return 0. Single node, should return 1. Deeply skewed tree, function should handle without Stack Overflow, unless tree is extremely deep. Here is the structure. If root is null, return 0. Recursively compute max depth of left subtree. Recursively compute max depth of right subtree. Return 1 plus max left, right. Let's try to implement it using solution 1. This defines our function max depth, which takes in the root of a binary tree and returns the greatest depth, basically how tall the tree is. Here we check if the root is empty. If the tree doesn't exist or we've reached a leaf's child, this condition becomes true. If we hit an empty node, we return 0 because an empty subtree has depth 0. This is our base case. Time complexity note. Base case is 01. Now we explore the entire left subtree. We call max depth again. This is recursion. We ask, how deep is the left side? This recursive call will keep going until it reaches the bottom of the left branch. Time complexity. Worst case, we visit every node ON. We calculate the depth of the right side by making another recursive call. Finally, we combine everything. We take the deeper of the two subtrees, left or right, and add 1 for the current node. This builds the height of the tree from the bottom up, one level at a time. And that's how this algorithm works. It first checks for the empty base case, then recursively measures the depth of the left and right subtrees and returns the larger one, plus 1 level for the current node. Efficient, simple, and elegant. Highlight input box. Root equals 3, 9, 20, null, null, 15, 7. Let's run our function using this tree input. 3, 9, 20, null, null, 15, 7. This array represents a binary tree in level order form. 3 is the root. Its children are 9, left, and 20, right. 20 then has 2 children, 15 and 7. Explain the logic briefly. Our algorithm calculates the maximum depth of the tree, essentially the longest path from the root down to a leaf node. Following the deepest branch here, 3, 20, 15 or 3, 27, we count 3 levels. Output, 3, expected, 3, and that's exactly the result we get. 3, perfectly matching the expected output. The test passes smoothly. So, our implementation is correct. The algorithm successfully computes the tree's maximum depth using a clean recursive approach, straightforward and reliable. Now let's try another implement approach using solution 2. We begin by defining a class called solution. This simply gives us a place to store our method. This defines a function called maxDepth, whose job is to calculate how deep a binary tree goes, how many levels it has from top to bottom. Here we check if the tree is empty. If there's no root, there are no levels to count. In that case, we return 0 because the maximum depth of an empty tree is 0. Time complexity. Base case is 01. We create a queue, starting with a single entry containing the root node and its depth, which is 1. Think of this queue as a line of people waiting to be processed level by level. We store each node alongside its depth so we always know how far down the tree we are. Data structure. This is BFS. Breadth first search. Space complexity. In the worst case, the queue can hold a full level of nodes on. We track the deepest level we've seen so far using max_depth. This loop keeps running as long as there are nodes waiting in the queue. We're exploring the tree level by level, from top to bottom. Time complexity. Each node enters and exits the queue once on. We pop the first item from the queue, the next node to process, and its current depth. This is BFS's characteristic behavior. First in, first out. We update our max_depth by comparing the current depth with the deepest level we've recorded so far. If this node is further down the tree, we update the maximum left. We check whether the node has a left child. 1. If it does, we add that left child to the queue, and label its depth as 1 more than the current nodes. This ensures the BFS continues expanding outward level by level. Right. We also check if a right child exists. If so, we add the right child to the queue with its depth increased by 1. This guarantees that both left and right branches are explored even. Finally, after we've processed all nodes, max_depth will hold the deepest level in the tree, so we return. And that's how this algorithm works. It first initializes a BFS queue with the root node, then explores the tree level by level while keeping track of the depth of each node. Efficient, simple, and elegant. Highlight input box. Root equals 3, 9, 20, null, null, 15, 7. Let's run our function using this tree input. 3, 9, 20, null, null, 15, 7. This array represents a binary tree in level order form. 3 is the root. Its children are 9, left, and 20, right. 20 then has 2 children, 15 and 7. Explain the logic briefly. Our algorithm calculates the maximum depth of the tree, essentially the longest path from the root down to a leaf node. Following the deepest branch here, 32015 or 327, we count 3 levels. Output, 3, expected, 3, and that's exactly the result we get. 3, perfectly matching the expected output. The test passes smoothly. So, our implementation is correct. The algorithm successfully computes the tree's maximum depth using a clean recursive approach, straightforward and reliable. Wrap up our discussion on maximum depth of binary tree, one of those deceptively simple interview classics that test how well you truly understand recursion and base cases. The problem asked us to find the longest path from the root to a leaf, in other words, how deep the tree goes. It's a direct measure of how many levels or layers exist in the structure. We saw that recursion fits perfectly. Each node's depth depends on the depths of its left and right children. The key is handling the base case, when the node is null, and correctly returning 1 plus max left, right. Our plan was clean. If the node is null, return 0. Otherwise, recursively compute both sides and add 1 for the current level. We turned that plan into a short, efficient function and ran it successfully on LeetCode without any errors. When we tested it, the logic held up. The function correctly returned 3 for the sample tree, and 0 for an empty one. All test cases passed. The big takeaway? Recursion in trees always starts with the base case and builds upward. Once you master this pattern, problems like minimum depth, balanced binary tree, and diameter of binary tree become much easier to handle.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Let's master same tree using the basic approach, breaking down the problem, analyzing, structuring a solution, and checking all edge cases. Let's break it down. Given the roots of 2 binary trees, return true if they're structurally identical and all their nodes have the same value. Otherwise, return false. Input: 2 binary tree root nodes, P and Q. Output: Boolean. True if the trees are the same, false otherwise. Real-world example. Suppose you're building a cloud backup system, and you need to verify if a backup is a true replica of the original tree structure and content. Interviewers might ask, how would you compare 2 hierarchical document models for structural and content equality? Let's assess. What's tricky? You have to check both the structure and the values at every node. Recursion is the natural fit. You need to handle all the cases where one tree might branch when the other doesn't, or values don't match. Think step by step. If both nodes are null, they're the same at this branch, return true. If only one is null, the trees differ, return false. If both nodes exist, check if their values match. If not, return false. If yes, recursively check their left and right children. The answer is only true if all these checks succeed for every node. Let's add more. Be sure to check both left and right subtrees. Missing one is a classic pitfall. Order of checks matters. Avoid null pointer errors by checking for null before accessing values. Edge cases. Both trees empty should return true. Trees with same shape but different values should return false. Trees with different shapes should return false. Here is the structure. If both P and Q are null, return true. If only one is null, return false. If both exist, compare their values. If not equal, return false. Otherwise, recursively check left and right children. Return true only if both left and right subtrees are also the same. Let's try to implement it using solution 1. We begin by defining a class called solution. This is simply where we'll store our function. This line defines our function as SameTree, which takes two tree nodes, P and Q, and decides whether the two trees are exactly the same in both structure and values. Here we check the simplest possible case, if both nodes are empty. If both trees hit an empty spot at the same time, that part is considered identical. When both nodes are empty, we return true because matching nothing with nothing means the trees still match perfectly. Time complexity note. Base cases are 01. This checks another scenario. What if one node is empty, but the other isn't? That means the trees don't match structurally. If exactly one side is missing, we immediately return false, the trees differ. And now we get to the main logic. First, we compare the values stored in the two nodes. If the values differ, the trees are definitely not the same. Left, and this line recursively checks whether the left subtrees of both nodes are identical. It dives down the left branches of both trees in parallel. Time complexity. In the worst case, we visit every node ON, right, and then we do the same with the right subtrees, comparing them recursively as well. For the entire tree to be the same, all three conditions must be true. Values match, left subtrees match, and right subtrees match. And that's how this algorithm works. It first checks the simple base cases for empty nodes, then recursively compares the values and structure of the left and right subtrees, ensuring every part of both trees matches. Efficient, simple, and elegant. Highlight input box. P equals 1, 2, 3, Q equals 1, 2, 3. Let's test our function with these two binary trees represented in level order form. P equals 1, 2, 3 and Q equals 1, 2, 3. Both describe the exact same structure. 1 is the root. 2 is the left child. 3 is the right child. Explain the logic briefly. Our algorithm checks if the two trees are identical, meaning same structure and same node values. Since every corresponding node matches perfectly, the trees are indeed identical. Highlight output box. Output, true, expected, true, and that's exactly what we get. True, matching the expected value. The test case passes cleanly. So, our implementation is correct. The algorithm correctly verifies the structural and value-based equality of both trees. Simple, accurate, and reliable. Now let's try another implement approach using solution 2. We start by defining a class called solution, which simply groups our method together. Checks whether two binary trees are exactly identical, same structure, same values, same layout. Instead of recursion, we use an explicit stack. We begin by pushing a pair, the root of tree P and the root of tree Q. We'll compare the two trees node by node using an iterative DFS, depth first search. Space complexity. Up to ON for storing nodes. This loop runs as long as there are node pairs to compare. Every iteration pops one pair from the stack and checks if they match. Time complexity. Each node is pushed and popped once ON. We pop the last pair from the stack. This is DFS behavior. Last in, first out. These two nodes are the ones we'll compare next. If both nodes are empty, that means both trees reach the end of a branch at the same time. That's perfectly fine. We just continue. We skip any further checks for this pair and move on to the next one in the stack. This checks for mismatch structure. If one node is empty and the other isn't, the trees differ. In that case, we immediately return false because the trees are not the same. Here we compare the actual values stored in the two nodes. If the values aren't equal, the trees don't match. Any mismatch in node values means the trees are not identical, so we return false right away. We push the left children of both nodes onto the stack. These pairs will be compared later, right? And we push the right children as well. This ensures we compare the entire structure of both trees, branch by branch. True. If we finish the entire loop without finding any mismatches, the trees are identical, so we return true. And that's how this algorithm works. It first initializes a stack with both root nodes, then iteratively compares each pair of nodes while pushing their children for further comparison. Efficient, simple, and elegant. Highlight input box. P equals 1, 2, 3, Q equals 1, 2, 3. Let's test our function with these two binary trees represented in level order form. P equals 1, 2, 3 and Q equals 1, 2, 3. Both describe the exact same structure. 1 is the root. 2 is the left child. 3 is the right child. Explain the logic briefly. Our algorithm checks if the two trees are identical, meaning same structure and same node values. Since every corresponding node matches perfectly, the trees are indeed identical. Highlight output box. Output, true, expected, true, and that's exactly what we get. True, matching the expected value. The test case passes cleanly. So, our implementation is correct. The algorithm correctly verifies the structural and value-based equality of both trees. Simple, accurate, and reliable. Quick recap on same tree. It looks simple, but it's a brilliant test of your recursion fundamentals and your eye for structural detail, exactly why top companies love it. We framed the task as a pure comparison problem. 2 roots n, and we return true only if both trees match in structure and in every value. We highlighted why recursion is the natural fit and called out the easy-to-miss cases. Both null is true, one null is false, and any value mismatch fails, plus the reminder to check both left and right subtrees. Our plan was a tight sequence. Handle the null checks first, compare values when both nodes exist, then recursively verify left and right. Both sides must agree for the overall result to be true. We translated that plan directly and ran it on LeetCode, clean execution with no errors. We validated with examples. Identical trees returned true, and differences in shape or values returned false. Test cases passed as expected. The big lesson: recursion succeeds when base cases are exact and comparisons are symmetrical. Nail this pattern, and you're set up for problems like symmetric tree, subtree checks, and beyond.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Let's approach invert binary tree with a basic method, breaking down the process, analyzing key steps, and ensuring you understand every pointer twist. Let's break it down. Given the root of a binary tree, invert it, meaning swap the left and right child of every node in the tree. Input: binary tree root node. Output: the same tree, but with every left and right subtree swapped. Real-world example. Imagine an image editing app with a mirror filter. To flip an image horizontally, you need to swap every left and right pixel or object. Similarly, inverting a tree mirrors its structure. Interviewers may ask, how would you design a function to mirror a decision tree, or flip a UI layout that's stored in a binary tree structure? Let's assess it. What's tricky? Recursion is the natural fit for trees, but you need to ensure you swap every subtree, not just the first level. You can use DFS, depth first traversal, pre-order, post-order, or BFS, level order, but recursion is clearest and most popular in interviews. Think step by step. If the current node is null, do nothing, base case. Otherwise, swap its left and right children. Recursively call the invert function on both children. You'll process every node exactly once, flipping the tree from the top down. Let's go deeper. If you prefer iteration, you can use a queue, BFS, but recursion matches how we mentally walk through a tree. Be careful to process null nodes and leaf nodes. These are your base cases. Here's some edge cases. Empty tree should return null. Single node should return the node itself. Skewed trees, only left or right children. Here's the structure. If root is null, return null. Swap roots left and right children, recursively invert the left child. Recursively invert the right child, return the root. Let's try to implement it using solution 1. We begin by defining a class called solution, just a place to store our function. This function is named invertTree, and its job is to flip a binary tree left to right, like holding it up to a mirror. Here we check whether the current node is empty. If there's nothing here, we have nothing to invert. When the node is empty, we return none. This acts as our base case for the recursion. Time complexity note. Base case is 01. This comment tells us the main operation. We swap whatever is on the left and whatever is on the right. This line does the actual swap. Imagine taking the left child and right child of the node and flipping them. One clean line does it all. This comment explains that after swapping, we still need to invert deeper levels of the tree, which used to be on the right before the swap. We keep going deeper until we reach leaves. Time complexity. Every node is visited once, giving us ON, recursively inverting everything beneath it. Finally, after the entire subtree under this node has been inverted, we return the root so the inverted tree can rebuild itself as the recursion unwinds. And that's how this algorithm works. It first checks for an empty node, then swaps the left and right children, and finally recursively inverts each subtree until the entire tree becomes a mirror image. Efficient, simple, and elegant. Highlight input box. Root equals 4, 2, 7, 1, 3, 6, 9. Let's run our function on this binary tree. 4, 2, 7, 1, 3, 6, 9. This array represents a level-ordered traversal of the tree. 4 is the root, 2 and 7 are its children. 1 and 3 belong under 2, while 6 and 9 belong under 7. Explain the logic briefly. Our algorithm inverts the entire binary tree, meaning every left child swaps with the right child at every node. After inversion, 2 and 7 swap places under the root, then 1 swaps with 3, and 6 swaps with 9. Performing a traversal after this swap gives us 4, 7, 2, 9, 6, 3, 1. Highlight output box. Output, 4, 7, 2, 9, 6, 3, 1. Expected, 4, 7, 2, 9, 6, 3, 1. And that's exactly the result we see. The output perfectly matches the expected output. The test case passes with flying colors. So, our implementation is correct. The algorithm successfully inverts the binary tree and returns the correct transform structure, clear, efficient, and accurate. Now let's try another implement approach using solution 2. We start by defining a class called solution, just a container to hold our method. This function, invert tree, flips a binary tree left to right, like holding the tree up to a mirror. We check whether the root is empty. If there's no tree, there's nothing to invert. In that case, we return none because the inversion of an empty tree is still empty. Time complexity. Base case is 01. We create a queue starting with just the root. This queue allows us to explore the tree level by level using BFS, breadth first search. Space complexity. Can reach up to ON in the worst case if the tree is wide. This loop keeps running as long as we still have nodes to process. Every iteration handles one node from the front of the queue. Time complexity. We process each node exactly once ON. We pop the first node from the queue. This is BFS behavior. First in, first out. This is the node whose children we're about to swap. Pause. Line highlighted, hash swap left and right children. This comment previews the main operation we're about to perform, flipping the children of the current node. This single line swaps the current node's left and right children. It's like flipping the branches of the tree on this node. Clean, simple, and powerful. This comment tells us that after swapping, we need to continue the process down the tree. We check whether there is a left child after the swap. If so, we add it to the queue so it will be processed and swapped later. We also check whether there is a right child. Well, this ensures we eventually swap every node's children in the entire tree. Root. After all nodes have been processed and swapped, we return the original root, now representing the fully inverted, mirrored tree. And that's how this algorithm works. It first performs a quick base case check, then uses a BFS queue to visit each node, swap its children, and continue level by level. Efficient, simple, and elegant. Highlight input box. Root equals 4, 2, 7, 1, 3, 6, 9. Let's run our function on this binary tree. 4, 2, 7, 1, 3, 6, 9. This array represents a level-ordered traversal of the tree. 4 is the root, 2 and 7 are its children. 1 and 3 belong under 2, while 6 and 9 belong under 7. Explain the logic briefly. Our algorithm inverts the entire binary tree, meaning every left child swaps with the right child at every node. After inversion, 2 and 7 swap places under the root, then 1 swaps with 3, and 6 swaps with 9. Performing a traversal after this swap gives us 4, 7, 2, 9, 6, 3, 1. Highlight output box. Output, 4, 7, 2, 9, 6, 3, 1. Expected, 4, 7, 2, 9, 6, 3, 1. And that's exactly the result we see. The output perfectly matches the expected output. The test case passes with flying colors. So, our implementation is correct. The algorithm successfully inverts the binary tree and returns the correct transform structure, clear, efficient, and accurate. Alright, quick recap on invert binary tree, the so-called hello world of binary tree problems. It's simple in theory but powerful for mastering recursion and traversal fundamentals. The task was to flip a binary tree by swapping every left and right child, essentially mirroring its structure while keeping all node values the same. We explored recursion as the clearest solution, noting that each node must be swapped and then its subtrees inverted. DFS and BFS can both work, but recursion keeps the logic clean and intuitive. Our plan was short and sharp: handle the null base case, swap the children, recursively invert the left and right, and finally return the root. We followed that plan in code, ran it on LeetCode, and it executed successfully with no errors. We walked through examples, confirming each node swapped correctly and all test cases passed as expected. The key takeaway? Recursion is about trusting the process. Solve for one node, let the function handle the rest. Mastering this mirror logic makes tackling more complex tree problems far easier.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Ready for a tree problem that trips up even experienced candidates? Binary tree maximum path sum is a PatternMastery 100 power question, and a favorite at Google, Facebook, and Microsoft for its tricky recursion and edge cases. Over 40% of interviewees make a mistake handling negative values or path splits. Let's ensure you ace it by breaking it down step by step. Let's master binary tree maximum path sum with the basic approach, ensuring you catch every tricky detail and never lose track of the recursion. Let's break this down. You're given the root of a non-empty binary tree. Find the maximum path sum, where a path can start and end at any node, and must contain at least one node. Paths can bend at a node, from left through parent to right, but cannot revisit nodes. Input: root node of a binary tree. Values can be negative or positive. Output: integer representing the maximum path sum. Here's a real-world example. Imagine a decision tree where each node's value represents profit/loss, and you want to find the richest sequence of decisions, even if that path bends through a parent. Interviewers might ask, what's the most valuable branch in a hierarchical project plan? Let's assess. What's tricky? Paths can go through a parent, taking both left and right children, but only at one split. Each recursion must return the single-sided max path, either left or right plus node, but must also update a global best if the whole V-shaped path through the current node is better. Negative values. Sometimes it's better to cut off a bad child by treating its max as 0. Think step by step. Traverse the tree with a post-order DFS. For each node, recursively get the max sum from the left child, ignore negatives by taking max with 0. Recursively get the max sum from the right child, also ignoring negatives. The maximum path through the node is node.val plus left_max plus right_max. Update a global max if this path is better than any seen before. For the recursion, return node.val plus max left_max, right_max, the best one-sided path to use further up the tree. The global max may be at any node, not just the root. Let's clarify. Always take the larger of 0 in each child's path sum, so you don't decrease the path by including negative numbers. Update the global max at every node, as the best path may bend through it. Edge cases. All negative nodes must still return the least negative, biggest, value. Skewed or one-sided trees should work identically. Single node trees must handle correctly. Here is the structure. Initialize a global variable, for example, max_sum equals inf. Write a recursive DFS function. If node is null, return 0. Compute left and right max paths, max 0, recurse left, etc. Calculate path sum through current node. Update global max if necessary. Return node.val plus max left_max right_max for parent recursion. After traversal, return the global max. Let's try to implement it using solution 1. We begin by defining a class called solution, which is simply the container where our functions will live. This defines our main function maxPathSum, which calculates the maximum possible sum of any path in a binary tree. The path can start and end anywhere, as long as it's connected. Here we create a variable called max_sum and set it to -infinity. This gives us a starting point that's guaranteed to be lower than any real path sum, so the first real value will replace it. This line kicks off a helper function called max_gain, which recursively evaluates the maximum gain from each node. It helps us build up the best possible path. After all recursive work is finished, we return the highest path sum found anywhere in the tree. Now the helper function. The max_gain function evaluates how much value a node can contribute upward to its parent. It's the engine that powers the logic. We first check if the node is empty, meaning we've hit a leaf's child. If the node doesn't exist, it contributes nothing to a path, so we return 0. Time complexity. Base case is 01. Hash compute max path sum with node as highest node, only one child side. This comment explains the next section. We're calculating the maximum gain that can come from each child, but only if that gain is positive. We recursively compute the gain from the left subtree. But if the left side gives a negative total, we replace it with 0, because adding a negative value would only make the path worse. Time complexity. Each node is processed once on 0, and we do the same for the right subtree. We only take positive contributions, negative paths get ignored. This comment tells us the next step evaluates a complete path passing through this node as the highest point. This line calculates the full path sum if the path goes left child this node right child. It uses both sides plus the current node's value. Here we compare the best path we've seen so far with the new path that includes both children. If this path is better, it becomes the new global maximum. This comment tells us the final value returned will only go upward to the parent, so we must choose one branch, not both. This returns the maximum gain the parent can use, the current node's value plus whichever side gives the highest gain. A parent can only extend the path through one child, not both. That's why we choose the larger of left or right. And that's how this algorithm works. It first initializes a global max, then computes the best gain from each subtree while checking every possible complete path through each node. By comparing every path and returning only the allowed upward contribution, we find the single highest path sum in the entire tree. Efficient, simple, and elegant. Highlight input box. Root equals 1, 2, 3. Let's run our function using this binary tree. 1, 2, 3. This level order representation describes a simple tree. 1 is the root, 2 is the left child, 3 is the right child. Explain the logic briefly. Our algorithm computes the sum of all node values in the tree. So we simply add them up. 1 plus 2 plus 3 equals 6. No branches, no complications, just a clean traversal and accumulation. Highlight output box. Output, 6, expected, 6, and the output we get is 6, exactly matching the expected result. The test passes perfectly. So, our implementation is correct. The algorithm efficiently traverses the tree and computes the total sum, straightforward and accurate. Now let's try another implement approach using solution 2. We begin by defining a class named solution, which simply organizes our function. This function, maxPathSum, computes the maximum path sum anywhere in a binary tree. A path can start and end at any node, as long as it's connected. #useList to allow modification in nested function. We create a list called max_sum with a single value, -infinity. Why a list? Because inner functions can't modify outer variables unless they're mutable, so the list allows updates from inside the helper function. This will track the highest path sum we find. We define a nested function called max_gain, whose job is to compute the maximum gain a node can contribute upward to its parent. This function is the core of the entire algorithm. We check if the node is empty. If we reach a null pointer, there's no value to return. When the node is empty, we return 0, meaning it contributes nothing to a path. Time complexity. Base case is 01. Ignore negative contributions. This comment explains the next lines. We're calculating the gain coming from each child, but we ignore negative values because they would decrease our path sum. 0 We recursively compute the maximum gain from the left subtree. If the left subtree is negative, we replace it with 0 so it doesn't drag our sum down. Time complexity. Each node is processed once on. We do the same for the right subtree. Only positive contributions matter for building the best path. This comment signals that we're now computing the best complete path that passes through this node. This calculates the full path sum if this node becomes the peak of the path, connecting its left and right gains. This path includes the node's own value, the best left path, the best right path. This may be the global maximum. We update our global maximum. If the path through this node is larger than anything we've seen before, it becomes the new maximum. This comment explains the return value. A parent cannot take both children, that would create a split. So we must pick only one branch to extend upward. We return the node's value plus the larger of the two gains. This represents the best possible path that can be continued by the node's parent. We trigger the recursion starting from the root. This computes all gains and updates the global maximum along the way. After processing the entire tree, max_sum 0 contains the maximum path sum anywhere in the tree, so we return it. And that's how this algorithm works. It first tracks the global maximum using a mutable list, then computes the max gain from each node while updating that global path sum through the node that connects both sides. Efficient, simple, and elegant. Highlight input box, root equals 1, 2, 3. Let's run our function using this binary tree. 1, 2, 3. This level order representation describes a simple tree. 1 is the root, 2 is the left child, 3 is the right child. Explain the logic briefly. Our algorithm computes the sum of all node values in the tree. So we simply add them up. 1 plus 2 plus 3 equals 6. No branches, no complications, just a clean traversal and accumulation. Highlight output box. Output, 6, expected, 6, and the output we get is 6, exactly matching the expected result. The test passes perfectly. So, our implementation is correct. The algorithm efficiently traverses the tree and computes the total sum, straightforward and accurate. Quick wrap-up on binary tree maximum path sum, a classic that exposes gaps in recursion, handling negatives, and path splits. We define the goal as finding the highest sum path anywhere in the tree. A path can start and end at any node, may bend through a parent once, and must include at least one node. We highlighted the two key ideas. 1. Each recursion returns a single-sided best path to its parent, and 2. At every node we also consider a V-shaped path using both children to potentially update a global best. Handling negatives by zeroing them out prevents bad branches from dragging down the sum. Our plan: post-order DFS. For each node, compute the best gain from left and right, never below 0. Consider the full bend-through sum at the node to update a global maximum, and return the node's value plus the larger single-sided gain to the parent. We followed that plan end-to-end and ran it on LeetCode without errors. In tests, the approach captured both straight and bending paths correctly, handled all negative trees by choosing the least negative node, and passed the edge cases. The takeaway: separate the value you return upward, single side, from the value you use to update the global best, possible split. Master that distinction and the hardest tree DP-style problems get much easier.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
Ever wonder how Google and Apple autocomplete searches so quickly? Implement Try, Prefix Tree, is a PatternMastery 100 staple, and a favorite at top tech interviews for testing your ability to design efficient string data structures. Over 30% of candidates struggle to code correct insert, search, and prefix logic under pressure. Master the Try, and you'll ace not just interviews, but also real-world search systems. Let's break down Implement Try, Prefix Tree, with the basic framework, a powerful way to design and implement complex structures in interviews. You're asked to build a data structure that supports 3 operations. Insert, word, adds a word to the try. Search, word, returns true if the word is in the try. Starts with prefix, returns true if there's any word in the try that starts with the given prefix, input/output. Insert and query words/prefixes, all lowercase English letters. Try supports OL time per operation, where L is the length of the word/prefix. Picture a search engine's autocomplete, or a phone book lookup that instantly finds all contacts by prefix. Interviewers might ask, how would you optimize prefix queries in a massive dictionary or suggest words in a typing app? What's tricky? You need efficient insert/search/prefix checks, all in OL time. The structure must handle a dynamic set of words with overlapping prefixes. Avoid confusion between a node being a prefix and being the end of a valid word. Think step by step. Represent the try as a tree where each node is a letter, and paths from the root to nodes spell words/prefixes. Each node contains a mapping from characters to child nodes, usually a fixed-size array for 26 letters, or a hash map. A Boolean flag indicating if a word ends at this node is _end. For insert, word. Start at the root for each character, create or move to the child node. After the last character, mark is _end true. For search, word. Walk down the tree per character. After the last, return true if is _end is set. For starts with, prefix. Same as search, but return true as long as you reach the last prefix character. Let's clarify. Insert and search both use the same traversal logic. Only difference, search checks is _end. Starts with doesn't. Try saves huge space on repeated prefixes compared to storing all possible words. Edge cases. Empty string insert/search. Prefixes that are full words versus partial prefixes. Define a try node class. Children, mapping for 26 letters, array or dictionary is _end. Boolean for word end. Try class. Root node, empty methods. Insert, search, starts with. For each operation, loop character by character, branching through the tree. Now let's implement the dictionary-based try, storing each node's children in a hash map for flexible and clean prefix operations. We start by defining a try node. Each node represents one character in a word. In the nodes constructor, we set up two things. Children, a dictionary mapping letters to the next try node. Is_end, a flag marking whether this node ends a complete word. This dictionary will store all child characters branching from this node. It grows dynamically as we insert more words. Initially, the node does not represent the end of a word. We flip this later when a word finishes here. Next, we define the main try class, the structure that manages the whole tree. The try starts with a single root node. It doesn't store any character, it's simply the starting point. We initialize that root node right here. Let's define how to insert a new word into the try. This operation runs in OM time, one step per character. We begin at the root. We'll walk down the try character by character. We loop through each character of the word we want to insert. If the current character does not exist as a child, we need to create a new path for it. We create a brand new try node for this new character branch. We then move into that child node, walking down the try like following a trail of breadcrumbs. When we finish processing every character, we mark the final node as the end of a valid word. This function checks if a full word exists in the try. Again, time complexity, OM. We start at the root. We walk through each character of the target word. If any character is missing in the try, the word cannot exist, so we return false. If the character exists, we follow it to the next node. After processing all characters, we return whether the final node marks the end of a word, which ensures we're not mistaking prefixes for whole words. This function checks if any word in the try begins with the given prefix. Just like before, we start at the root. We scan each character of the prefix. If a character is missing, no word in the try can start with this prefix. So we return false. Otherwise, we follow the path deeper into the try. If we make it through every character, then yes, the prefix exists in the try. And that's how this algorithm works. It first uses a dynamic dictionary-based node system to build flexible word paths, then lets us search full words or prefixes in linear time. Efficient, simple, and elegant. Let's check. These operations describe how we interact with our try. Try create a new empty try. Insert Apple search app starts with app insert app search app, again. With the Dictionary of Children implementation, each node stores a map like char, child node, and a flag is end to mark the end of a word. Let's walk through the sequence. Try just initializes the data structure returns null. Insert Apple we create nodes for apple if they don't exist and mark the last node as end of word. Return null. Search Apple. We traverse character by character. A, P, P, L, E. We land on the node for E and it's marked as a complete word return true. Search app we follow app. That node exists, it's a prefix, but we haven't marked app as a full word yet return false. Starts with app same traversal as above, app. We only need the prefix to exist, not the full word return true. Insert app. We go to the existing node for app and now mark it as a complete word. Return null. Search app follow app again. This time, the app node is marked as end of word return true. So our result list becomes null, null, true, false, true, null, true, and that's exactly what our implementation produces. Every operation's result lines up with the expected behavior. So, our implementation is correct. The dictionary-based try handles inserts, exact searches, and prefix checks in OM time per operation and passes this test case perfectly. Now let's implement the array-based try, using a fixed 26-slot structure at every node for fast, index-driven character access. We start by defining a try node. Each node represents a single character but, unlike solution 1, this node has exactly 26 slots, one for each lowercase letter. Here we create a fixed size array of 26 elements. Each position corresponds to a letter. Index 0 for A, 1 for B, all the way to 25 for Z. This makes accessing a child node extremely fast, constant time, 01. We mark whether this node represents the end of a valid word. At creation, it does not. Now we define the main try structure that uses these nodes. Every try starts with a root node. It doesn't store a letter, it's simply the entry point. This method inserts a word character by character into the try. Because we handle each character once, the time complexity is OM. We begin at the root and will walk downward as we process each letter. We loop through each character of the input word. Here's the key difference with solution 2. We convert the character into a number between 0 and 25 by subtracting A from that character's ASCII code. This gives us the correct slot in the children array. If there's no child node for this character yet, we create one, building the try branch as needed. We initialize a brand new node at that index. We then move down into that node and continue adding letters. When we finish processing the final character, we mark the node as the end of a complete word. This method checks whether a full word exists in the try. Again, time complexity. OM. We begin from the root. We inspect each character of the word. We convert the letter into an array index. If the needed branch is missing, then the word cannot exist, return false. Otherwise, we move deeper into the try. At the end of the word, we return whether this node actually marks a valid word end. This function checks if any stored word begins with the given prefix. Also runs in OM. Start at the root. Loop through each character of the prefix. Convert the character into the appropriate index. If a character path is missing, this prefix doesn't exist in the try, return false. Otherwise, keep following the prefix downward. If we survive the entire prefix, that means at least one word starts with it. And that's how this algorithm works. It first sets up a fast, fixed-size array of child nodes, then uses that structure to insert, search, and check prefixes in linear time. Efficient, simple, and elegant. Let's check. We'll run the exact same sequence of operations, but this time using a try where each node has a fixed array of 26 children, one slot per lowercase letter az. In this version, instead of a dictionary, each node holds an array like children 26 and an isEnd flag. The character C maps to index C, A. Walking through the operations. Try creates an empty root node with all children set to null, returns null. Insert apple for each character. A index 0. P index 15. P index 15. L index 11. E index 4. We create nodes along this path and mark the E node as isEnd equals true. Return null. Search apple follow the same indexes for apple. We reach the E node and see isEnd equals true, return true. Search app traverse indices for a P. The node for app exists, but isEnd is still false at this moment, return false. Starts with app again, traverse app. We only need the path to exist, not isEnd, return true. Insert app. We go back down to the app node and set isEnd equals true. Return null. Search app traverse app once more. Now isEnd is true at this node, return true. So the final output is null, null, true, false, true, null, true. And that's exactly what we see from the program. The output matches the expected result step by step. So, our implementation is correct. The fixed array try mirrors the behavior of the dictionary-based try, still running each operation in OM time, and it cleanly passes this test case too. Autocomplete isn't magic, it's structure. Implement try, prefix tree, turns fast prefix lookups into a simple, repeatable pattern. Nail this, and you're designing the backbone of search suggestions and instant lookups. Let's do a recap. We built a data structure that supports 3 core operations. Insert a word, check if a full word exists, and check if any word starts with a given prefix. Each operation works in OL time, where L is the length of the input word or prefix. The main challenges were keeping operations efficient, sharing overlapping prefixes to save space, and clearly distinguishing between this path exists and this path is a complete word. That last point, marking word ends, is where many implementations go wrong. Conceptually, the try is a rooted tree where each edge represents a character. Every node stores a set of outgoing character links to children, a Boolean flag indicating whether a complete word ends at that node. Insert, search, and starts with all walk the same path character by character. The only difference is whether we require that end of word flag at the finish. We followed that plan precisely, traversed from the root, created nodes as needed on insert, checked for missing links during queries, and relied on the end of word flag to distinguish full matches from mere prefixes. We ran the solution on LeetCode, no errors. Our tests confirmed the behavior. After inserting apple, a full word search for apple returned true, app returned false until we inserted it, and starts with app, correctly returned true the whole time. Edge cases like empty strings and missing prefixes behaved as expected and passed the LeetCode checks. The big takeaway: the try turns repeated work into shared structure. By separating path exists from word ends here, you get fast, reliable prefix queries, exactly what high-performance search features need.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Want to ace tree questions at Google, Amazon, or Apple? Binary tree level order traversal is a classic Pattern Mastery 100 question. and over 25% of candidates mess up the queue logic or output formatting. Nail this one, and you'll be ready for everything from graph traversals to real-world scheduling challenges. Let's level up your skills together. Let's solve binary tree level order traversal with the basic method, so you build rock-solid, interview-ready solutions every time. Let's break this down. Given the root of a binary tree, return its values level by level, that is nodes at each depth together in a list. Input, root node of a binary tree. Output, list of lists. Each inner list contains all node values at that tree level. Here is an example. Input. Output, 3, 9, 20, 15, 7. Here is a real-world example. Suppose you're managing a project with tasks organized in dependency levels. You want to group tasks by which ones can be started at each phase. An interviewer might ask, how would you organize a company's org chart into management levels for communication planning? Now let's assess it. What's tricky? This is a classic breadth-first search, BFS. You need to process the tree layer by layer. You need a queue to keep track of which nodes to process next. The result must be grouped per level, not just a flat list. Think step by step. If the root is null, return an empty list. Initialize a queue with the root node. While the queue isn't empty, track the number of nodes at the current level. Queue size at start of a loop. For each node at this level, pop from the queue, add its value to a temporary list. Add its left/right children to the queue for the next level. After finishing this level, append the temporary list to the final result. Repeat until all levels are processed. Let's add more detail. Why track the queue size at each loop? It ensures that you process exactly the nodes at the current level, so your output matches the level grouping. Forgetting this step is a classic source of bugs. Some edge cases. Empty tree. Return. Single node. Return. Val. Deeply skewed or unbalanced trees should still work. Here is the structure. If root is null, return. Initialize a result list and a queue with root. While queue not empty, get current level size. For each node at this level, pop, save value, in queue children. Add this level's binary tree level order traversal. Let's try to implement it using solution 1. We begin by defining a class called solution, just a container for our function. This defines our function level order, which performs a level order traversal of a binary tree, meaning we visit the tree level by level, from top to bottom. We check whether the tree is empty. If there's no root, there's nothing to traverse. If the tree is empty, we return an empty list because there are no levels to report. Time complexity note. This check is 01. This initializes an empty list called result, which will eventually hold all levels of the tree as separate lists. This queue will help us process nodes in first in first out order, perfect for level order traversal. Each iteration processes one full level of the tree. Time complexity. Every node enters and leaves the queue once on. These nodes represent all the nodes on the current level of the tree. We create an empty list to collect the values of the nodes at the current level. This loop runs exactly once for each node in the current level. We'll process them one by one. This gives us the next node to process. Note, popping index 0 is on, but since the total work still involves processing each node once, we treat total complexity as on. We add the node's value to the current levels list. This is what we'll eventually store in the final result. We check whether the node has a left child. If it does, we add that left child to the queue so it gets processed in the next level. We also check whether the node has a right child. We add the right child to the queue as well. This ensures both children will be included in the next wave of nodes. After processing all nodes in the current level, we add the entire levels list into result. Each iteration of the while loop produces one row of the tree. Finally, after all levels have been processed and the queue is empty, we return the full list of lists representing the entire level order traversal. And that's how this algorithm works. It first checks for an empty tree, then uses a queue to process nodes level by level, collecting values into separate lists for each level. Efficient, simple, and elegant. Highlight input box. Root equals 3, 9, 20, null, null, 15, 7. Let's test our level order traversal function using this binary tree. 3, 9, 20, null, null, 15, 7. This level order array describes the tree as follows. 3 is the root. 9 is its left child. 20 is its right child. And under 20 we have 15, left, and 7, right. Explain the logic briefly. Our algorithm processes the tree level by level, collecting the node values at each depth into their own list. So the traversal looks like this. Level 1, 3 level 2, 9, 20 level 3, 15, 7. These groups are exactly what a correct breadth-first traversal should produce. Highlight output box. Output 3, 9, 20, 15, 7, expected 3, 9, 20, 15, 7, and the result matches perfectly. The output aligns exactly with the expected value. The test case is accepted. So, our implementation is correct. The algorithm walks through the tree level by level and gathers nodes cleanly and accurately, efficient and spot on. Now let's try another implement approach using solution 2. We begin by defining a class named solution, which simply organizes the method we're about to write. This function, level order, performs a level order traversal of a binary tree, but instead of BFS, we'll do it using DFS with level tracking. We start with a simple check. If the tree is empty, there are no levels to traverse. In that case, we return an empty list because the output should contain no levels. Time complexity. Base case is 01. We create an empty list called result. This will eventually store multiple lists, one list for each tree level. We define a helper function named DFS, which stands for depth first search. It takes two arguments, the current node, and the level we're currently exploring. This DFS will collect nodes by their depth level. If the node is empty, we stop immediately, no work needed. This simply exits the current DFS branch. If this is the first node at this level, create a new list. This comment explains the next piece. If it's our first time reaching this depth, we need to set up a list to hold nodes from this level. This checks whether the number of levels recorded so far matches the current level. If they're equal, it means this level has not been created yet. And, if so, we add a new empty list to represent this new level. This ensures each level has its own list. A comment reminding us that now we place the node's value into the correct level. We add the current node's value to the list corresponding to the current level. This organizes values exactly as level order traversal expects. This comment explains that we now move deeper into the tree. We recursively call DFS on the left child, but notice we pass level +1. This means we're going one level deeper into the tree. We do the same with the right child. Together, these two recursive calls ensure the entire tree is explored depth first. Time complexity. DFS visits every node once on. Space complexity. OH for recursion stack, where H is tree height. We start the DFS from the root at level 0, the top of the tree. Finally, we return the complete result list, which now contains one list per level, filled in with node values exactly like a level order traversal. And that's how this algorithm works. It first initializes an empty result and a DFS helper, then recursively collects nodes by their depth level using a depth-first traversal. Efficient, simple, and elegant. Highlight input box. Root equals 3, 9, 20, null, null, 15, 7. Let's test our level order traversal function using this binary tree. 3, 9, 20, null, null, 15, 7. This level order array describes the tree as follows. 3 is the root. 9 is its left child. 20 is its right child. And under 20 we have 15, left, and 7, right. Explain the logic briefly. Our algorithm processes the tree level by level, collecting the node values at each depth into their own list. So the traversal looks like this. Level 1, 3 level 2, 9, 20 level 3, 15, 7. These groups are exactly what a correct breadth-first traversal should produce. Highlight output box. Output, 3, 9, 20, 15, 7, expected, 3, 9, 20, 15, 7, and the result matches perfectly. The output aligns exactly with the expected value. The test case is accepted. So, our implementation is correct. The algorithm walks through the tree level by level and gathers nodes cleanly and accurately, efficient and spot on. Let's quickly recap binary tree level order traversal, a must-know interview question that tests your understanding of queues and BFS traversal. The goal was simple. Traverse a binary tree level by level, grouping nodes at the same depth together into lists. Essentially, we built a layer-by-layer view of the tree. We recognize that breadth-first search is the perfect fit, using a queue to process nodes in order, one level at a time. The key challenge was keeping track of the queue size each round, so we only process nodes from the current level. Our plan: check for an empty tree, initialize a queue with the root, loop until it's empty, collect values for each level, and in-queue child nodes for the next round. We wrote this logic step by step, using a clean BFS loop and a result list, and it ran smoothly on LeetCode without any errors. We verified the output, each level printed correctly, from top to bottom. 3, 9, 20, 15, 7. Edge cases like empty or single node trees worked perfectly. The big takeaway? Queue-based BFS isn't just for trees, It's the backbone of level order logic in graphs, scheduling systems, and even social network distance calculations.
This is not another random playlist. It is a roadmap, patterns, structure, repetition. The stuff that actually sticks. PatternMastery.com.
Want to master a problem that appears in system design and algorithm interviews at Google and Meta? Serialize and deserialize binary tree is a PatternMastery 100 favorite, testing recursion, edge cases, and even real-world network reliability. Over 40% of candidates get tripped up by nulls or mismatched node orders. Get this right, and you'll unlock the secrets behind saving and restoring complex data structures. Let's tackle serialize and deserialize binary tree using the basic method, a systematic approach that ensures your code is both correct and robust. Let's break this down. Given the root of a binary tree, design an algorithm to serialize, convert into a string, and deserialize, rebuild from string, the tree so that it can be perfectly reconstructed later. Input: root node of a binary tree. Output: serialize root returns a string. Deserialize data reconstructs the tree from that string. Here is a real-world example. Think of saving a user's game progress, or syncing a complex org chart between servers. You need to turn the tree into a format you can store or transmit, then reliably rebuild it on the other side. An interviewer might ask, how would you persist a configuration tree for backup and recovery? Now let's assess. What's tricky? You must record the structure, not just the values. Null nodes matter. Skipping them loses information. Order matters. Children must appear in the right place. Recursive traversal, pre-order or level order, is common. Think step by step. For serialization, traverse the tree, usually pre-order. For each node, record its value. For null children, record a sentinel value, like hash or null. Join values into a string, commas, spaces, etc. For deserialization, split the string into a list. Use recursion to rebuild the tree, reading values in the same order. When you encounter the sentinel, return null for that child. Let's clarify. Why record nulls? Without them, you can't tell if a node had a missing left or right child. Matching the order, pre-order for both serialize and deserialize, keeps logic clear. Edge cases. Empty tree should serialize as an empty string or sentinel. Tree with only left/right children must handle all arrangements. Here is the structure. Serialize. Use a recursive helper to pre-order traverse. Append values to a result list. For null, append sentinel. Join the result list into a string. Deserialize. Split the string into a queue/list. Use a recursive helper that pops values. If sentinel, return null. Else, build node. Recurse for. Let's try to implement it using solution 1. This class handles both converting a tree into a string and turning that string back into the original tree. This function serializes a binary tree, meaning it converts the entire structure into a single readable string. A simple docstring explaining the purpose of the function. We first check if the root is empty. An empty tree has nothing to serialize. This acts as our placeholder for missing nodes when we reconstruct the tree later. Time complexity. Base case is 01. This is the key serialization step. We do 3 things. Convert the current node's value to a string. Recursively serialize the left subtree. Recursively serialize the right subtree. We join all 3 with commas. This creates a pre-order traversal string, root left right. Time complexity. We visit every node once on. This function deserializes the string, meaning it rebuilds the original binary tree from the encoded data. Decodes your encoded data to tree, a docstring explaining what this function does. We define a nested function called helper that reconstructs the tree one value at a time. We take the next value from our list iterator. This moves through the serialized string one token at a time. This checks whether the current token represents an empty node. If the token is null, we return none, meaning this branch of the tree doesn't exist. Otherwise, we create a new tree node with the integer value we just read. This becomes the root of the current subtree. Because we serialized in preorder, the next value in the sequence is always the left child. Preorder ensures the structure is reconstructed correctly. Time complexity. Each value is processed once on, which now includes its left and right children. We take the serialized string, split it by commas, and turn it into an iterator. The helper function will consume this iterator step by step. We pass the iterator to our helper, which rebuilds the entire tree and returns the root. And that's how this algorithm works. It first converts the tree into a preorder string using recursion, then walks through that string to rebuild the tree node by node. Efficient, simple, and elegant. Highlight input box. Root equals 1, 2, 3, null, null, 4, 5. Let's test our function on this binary tree. 1, 2, 3, null, null, 4, 5. This level order representation describes the structure like this. 1 is the root. 2 is the left child. 3 is the right child. And under 3, we have 4, left, and 5, right. The two null values simply indicate that node 2 has no children. Explain the logic briefly. Our algorithm serializes, or processes, the tree in the required order and builds the output array representing the same structure. Since the tree already matches the expected layout, and there are no inversions, transformations, or deletions happening, the output should look exactly like the input. Highlight output box. Output: 1, 2, 3, null, null, 4, 5 expected. 1, 2, 3, null, null, 4, 5. And that's exactly what we see. The output matches the expected result perfectly, so the test case is accepted. So, our implementation is correct. The algorithm successfully processes and returns the tree structure exactly as intended, consistent, accurate, and reliable. Now let's try another implement approach using solution 2. We begin by defining a class named codec, which contains both the serialize and deserialize functions. This method converts a binary tree into a single string, using BFS, or level order traversal. A simple docstring that describes the approach. We check if the tree is empty. If there's no root, there's nothing to encode. In that case, we return an empty string. Time complexity. Base case is 01. We create an empty list called result, which will hold string representations of each node's value, or null for missing nodes. We initialize a queue containing only the root. This queue allows us to explore the tree level by level using BFS. Space complexity. Up to ON for storing nodes. This loop continues as long as there are nodes to process. Every iteration handles one node from the queue. Time complexity. We visit each node exactly once ON. We pop the first node from the queue, BFS style, first in, first out, pause. Line highlighted. If node, we check if the node is real, not null. We add the node's value, converted to a string, to our result list. We push the left child, even if it's null, into the queue. We also push the right child. This ensures that null nodes are included, preserving the exact structure of the tree. This branch handles null nodes. We append the string null for missing nodes. This maintains the correct position information for reconstruction. This comment explains the cleanup step. LeetCode doesn't want unnecessary nulls at the end. This loop checks if the last item in the result is null. We repeat until we reach a non-null value or the list is empty. We join everything with commas to create the final serialized string. This is the output representation of the entire tree. Deserialization. Convert string tree line highlighted. Def deserialize self. Data. This method does the opposite. It takes the encoded string and reconstructs the original tree using BFS, a docstring describing this method. We check if the input string is empty. If it is empty, we return an empty tree. We split the string by commas to get a list of node values, or null. The first value represents the root node. We create a new tree node using that number. We initialize a queue with the root node, just like in BFS. We will reconstruct the tree level by level. We set a pointer I to index 1, the next value in the list. This loop runs as long as there are nodes to attach children to, and we still have values left to process. Pause. We pop the next node from the queue, the one whose children we're about to assign. Pause. A comment explaining the next section. Pause. We check if the next value is real or null. Pause. If it isn't null, we create a node for the left child. Pause. We add that child to the queue so its children can be processed later. Pause. We move to the next value. Pause. Next, we do the same thing for the right child. Pause. Again, check whether it's a real node. Pause. If so, create the right child. Pause. And push it into the queue to process later. Pause. Advance the pointer again. Pause. Finally, when all values have been processed, we return the root of the fully reconstructed tree. Pause. And that's how this algorithm works. It first serializes the tree using BFS to capture its level structure, then rebuilds that structure during deserialization using the same BFS logic. Efficient, simple, and elegant. Highlight input box. Root equals 1, 2, 3, null, null, 4, 5. Let's test our function on this binary tree. 1, 2, 3, null, null, 4, 5. This level order representation describes the structure like this. 1 is the root. 2 is the left child. 3 is the right child. And under 3, we have 4, left, and 5, right. The two null values simply indicate that node 2 has no children. Explain the logic briefly. Our algorithm serializes, or processes, the tree in the required order and builds the output array representing the same structure. Since the tree already matches the expected layout, and there are no inversions, transformations, or deletions happening, the output should look exactly like the input. Highlight output box. Output: 1, 2, 3, null, null, 4, 5 expected. 1, 2, 3, null, null, 4, 5. And that's exactly what we see. The output matches the expected result perfectly, so the test case is accepted. So, our implementation is correct. The algorithm successfully processes and returns the tree structure exactly as intended, consistent, accurate, and reliable. Quick recap of serialize and deserialize binary tree. This problem is the bridge between interview algorithms and real-world persistence. Save a tree as text, then rebuild it exactly, nulls and all. We needed two operations: turn a tree into a string, serialize, and reconstruct the identical tree from that string, deserialize. The core requirement was preserving both values and structure, which means null nodes had to be explicitly recorded. We called out the common traps: forgetting nulls, mixing traversal orders, or losing child positions. A consistent traversal, like preorder, plus a sentinel for nulls prevents ambiguity and guarantees a perfect round trip. Our plan, during serialization, perform a preorder walk and append either the node's value or a sentinel, for example hash, to the output sequence. During deserialization, read the sequence in the same order, creating nodes for values and returning null at sentinels, recursing left, then right. We followed that plan end-to-end and ran the solution on LeetCode, clean execution, no errors. In tests, strings like 1, 2, hash, 3, 4, hash, 5, hash reconstructed the exact original tree, and edge cases, like an empty tree, were handled correctly. All test cases passed. The takeaway: structure must be encoded, not inferred. Pair a fixed traversal order with explicit null markers, and you'll reliably serialize complex trees in interviews and production systems alike.
Quiet room. Shared screen. One question. No clue. That silence is expensive. PatternMastery.com.
Want to prove you really understand recursion and tree structure? Subtree of another tree is a PatternMastery 100 favorite, and a classic test at Google and Amazon for algorithmic reasoning and code reuse. Over 30% of candidates miss a subtle check or edge case. If you can solve this confidently, you'll show you can handle complex recursive comparisons and tree pattern matching. Let's crack subtree of another tree using the basic method, so you always stay systematic and interview-proof. Now let's break this down. You're given two binary trees, root and subroot. Determine if subroot is a subtree of root. In other words, if there's a node in root where the tree rooted at that node is identical to subroot. Input: two binary tree root nodes, root and subroot. Output: Boolean: true if subroot is a subtree of root, false otherwise. Here is real-world example. Imagine you're managing file systems or XML or HTML documents as trees, and you need to check if a particular snippet, subtree, exists within a larger structure, without flattening them. An interviewer might ask, how would you check if a certain configuration or code block is present within a larger config tree? Now let's assess it. What's tricky? You need to traverse the main tree, root, and, at each node, check if the subtree starting there is identical to subroot. Reuse same tree logic for equality check. Recursion is your friend, but you must remember to check at every possible starting node. Let's think step by step. If root is null, there's no tree to match, return false. At each node, check: is the tree starting here the same as subroot? Use a helper function: is same tree. If not, recursively check both left and right subtrees of root. The answer is true if any check succeeds. Let's go deeper. Is same tree recursively compares node values and structure, so it's a perfect subroutine. You have to check every node in root, not just where the values match at the top. Here are some edge cases. Both trees empty, should return true. Subroot is larger than root, should return false. Subroot not present anywhere in root, should return false. Here is the structure. If root is null, return false. If is same tree root, subroot, returns true, return true. Recursively check subtree of left and subtree of right. Return true if any check passes. Now let's implement the DFS plus tree comparison approach, where we explore each node of the main tree and recursively verify structural matches. Here we begin our solution class, which holds both helper functions. This function decides whether subroot appears somewhere inside the larger tree root. We check if root is empty. If we've reached a null node, then there's nowhere else to look, so we return false immediately. Next, we compare the subtree starting exactly at this node with subroot, using the helper function as same. If they match perfectly, we found our answer, return true. If the subtree at this node isn't a match, we recursively check the left and right children of root. If either side returns true, the whole function returns true. Time complexity note. Each node in root may trigger a full tree comparison with up to n nodes, leading to a worst-case complexity of big O of m times n. Helper function is same. This helper checks whether two subtrees are identical in structure and values. If both nodes are none at the same time, that means we've matched all the way down on both sides. So we return true, this branch matches perfectly. If only one of them is none, or their values don't match, then the trees differ right here. And we return false immediately. If the values match, we recursively compare. Left child to left child. Right child to right child. Both must match, so we use and. And that's how this algorithm works. It first walks through the main tree using DFS, and at each node, checks whether the subtree matches exactly using a full structural comparison. Efficient, simple, and elegant. Now let's check. Let's run our DFS plus tree comparison solution on this test case. The first list describes the main binary tree, root, and the second list describes the smaller tree, subroot, that we want to check as a potential subtree. Our DFS walks through the root tree node by node. We start at 3. This doesn't match subroot's root value 4, so we keep going. We move to the node with value 4 in the main tree. Now the values match, so we trigger a full tree comparison here. We compare. 4 with 4 is match. Left child, 1 with 1 is match. Right child, 2 with 2 is match. The structure and values all line up perfectly. That means the subtree rooted at this 4 in the main tree is exactly the same as subroot. And that's exactly what our function returns, true, which matches the expected result. So, our implementation is correct. Even though the worst-case time complexity is OM times NOM / times NOM times N, for this test the DFS quickly finds the matching subtree and confirms it with a clean node-by-node comparison. Now let's implement the pre-order serialization method, transforming both trees into strings so we can quickly check for a subtree using substring search. We start defining the solution class that contains our subtree checker. This function determines whether subroot exists somewhere within root, but instead of comparing trees directly, it uses serialization to convert them into strings. We define a helper function inside as subtree called serialize. This takes a node and turns the entire subtree into a string representation. When the node is empty, none, we still need a placeholder. So we return X to clearly mark missing nodes. This prevents collisions like confusing one null 2 with one 2. This line performs a pre-order traversal and builds a string. Hash marks the start of a real value. strnode.val stores the number. Then we serialize the left subtree. Then the right subtree. Spaces separate entries so numbers don't merge incorrectly. And this is the entire trick. We serialize both trees into strings. Then check if the serialization of subroot appears inside the serialization of root. If yes, then subroot is a subtree. If no, then it isn't. Time complexity note. Serialization produces two strings of size m and n, and substring searching, in Python, is optimized, giving us an average runtime of big O of m plus n. And that's how this algorithm works. It first serializes both trees using preorder, marking null so the structure stays intact, then checks for a substring match. Efficient, simple, and elegant. Let's test our preorder serialization solution on this input. The root array represents the main binary tree, and subroot is the smaller tree we're checking as a potential subtree. With plain values, it looks like 4, 1, 2 appears inside the main tree. But the catch is in the structure. In root, the node 2 actually has an extra child, 0. In subroot, the node 2 is a leaf node. It has no children. When we serialize both trees using preorder with null markers, for missing children, the main tree's serialization includes that extra 0 and the correct null markers. The subroot serialization shows 2 with both children as null. Because of this structural mismatch, the subroot string does not appear as a clean substring in the main tree's serialization. That's exactly what we want. We're not just matching values, we're matching the entire shape of the subtree. And that's exactly what our program outputs, false, which matches the expected result. So, our implementation is correct. The pre-order serialization plus substring approach correctly rejects this as a subtree, while still running in OM plus N, OM plus N, OM plus N time on average, efficient, and structurally accurate. So, that's subtree of another tree, a deceptively simple question that really tests how well you understand recursion and structural comparison in binary trees. Let's do a recap. At its core, this problem asks, can we find a smaller tree, subroot, perfectly nested somewhere inside a larger tree, root? Conceptually, it's like checking if a certain pattern or section exists within a much bigger hierarchy, without flattening or simplifying anything. We explored how the challenge isn't just comparing values, it's about comparing entire structures. We reuse the logic from the same tree problem, but the key twist is that we must perform that comparison at every node of the main tree until we find a match. The plan was straightforward. If the main root is null, return false. Otherwise, check if the subtree starting at this node matches subroot using the helper function. If not, move down to the left and right subtrees and repeat the process. It's a clean, recursive structure that ensures every possible subtree gets checked. We put that logic into code, recursively traversing the main tree, using the helper to verify structural and value equality, and ensuring no node was skipped. Finally, we ran the solution through LeetCode. It handled all the test cases, true when subroot existed, false when it didn't, and accurate even on edge cases like empty trees. Everything executed without errors. The key takeaway? Recursion shines when the problem mirrors itself at smaller levels. By breaking the comparison into smaller identical checks, you prove not just coding skill, but deep understanding of how trees think.
LeetCode says medium. Your nervous system says boss fight. That is your sign you need pattern training. PatternMastery.com.
Can you rebuild a tree from just its travel diaries? Construct binary tree from pre-order and in-order traversal is a PatternMastery 100 cornerstone, regularly asked at Amazon, Apple, and Google to test your deep understanding of recursion and tree building. Over 35% of candidates miss subtle index bugs or don't manage recursion boundaries right. Let's break it down so you don't. We'll use the basic method to solve construct binary tree from pre-order and in-order traversal, giving you a powerful template for any tree reconstruction problem. Let's break this down. Given two arrays representing the pre-order and in-order traversals of a binary tree, with no duplicates, reconstruct the original binary tree. Input: pre-order. Nodes visited as root, left, right. In order. Node is visited as left, root, right. Output: root of the reconstructed binary tree. Here is a real-world example. Imagine restoring a company's org chart from two different reports, one listing employees as visited in order of management, pre-order, the other listing them by their department or hierarchy, in order. Interviewers might ask, how would you reconstruct a configuration or parse tree if you only had two traversals? Let's assess. What's tricky? You must know how pre-order and in-order traversals uniquely determine a tree. The first value in pre-order is always the root. In an order, everything to the left of the root is the left subtree. Everything to the right is the right subtree. Think step by step. Use a pointer or index to track the current root in pre-order. Use a hash map to quickly find root positions in an order, to split left and right. Recursively, pick root from pre-order. Find its index in an order. Recursively build the left subtree, from an order left split. Recursively build the right subtree, from an order right split. Advance the pre-order pointer at each recursive call. Let's clarify. Always slice the in-order array to define subtrees. Pre-order's root pointer moves forward every time you build a new node. Base case: if there's nothing left to build, left index greater than right, return null. Edge cases: empty lists should return null. Single node builds a leaf. Deeply skewed trees, for example, all left or all right children. Here is the structure. Build a hash map of value index for in order for O1 lookups. Create a recursive function with left/right boundaries for in order. At each call, use the current pre-order index for the root value. Increment pre-order index for the next call. Recursively build left subtree, in order left split. Recursively build right subtree, in order right split. Return the constructed node. Now let's implement the recursive construction using an in-order index map, allowing us to rebuild the tree efficiently in linear time. We begin our solution class, which contains the tree building logic. This method reconstructs the entire binary tree using pre-order and in-order traversal lists. If the pre-order list is empty, there's no tree to build. So we simply return none, an empty tree. We create a dictionary that maps each value in the in-order list to its index. This means we can instantly find the root's position in the in-order traversal instead of searching linearly. This optimization is why the entire solution runs in ON. This inner function builds a subtree using only index boundaries, no slicing lists, just moving pointers. If our pre-order or in-order range becomes invalid, it means there are no nodes left to construct in this subtree. So we return none. The subtree is empty here. In pre-order, the first element in any valid range is always the root. We create a new tree node using that value. We quickly find the root's index in the in-order list to determine how many nodes belong to the left subtree. The number of nodes in the left subtree is everything between the in-order left boundary and the root's index. We recursively build the left subtree by shifting pre-order to the next element, taking exactly left_size nodes, using the corresponding in-order left range. Then we build the right subtree by jumping ahead in pre-order past the left subtree, using the remaining pre-order range. Using the in-order range to the right of the root index, we return the constructed root node, now connected to its left and right subtrees. We start by passing the full pre-order and in-order ranges so the entire tree is built from the top down. And that's how this algorithm works. It first creates a fast index map to locate roots instantly, then recursively partitions pre-order and in-order ranges to rebuild the left and right subtrees. Efficient, simple, and elegant. Let's test our recursive solution with these traversals. The pre-order array tells us the order in which nodes are visited as root left right. The in-order array tells us how nodes appear as left root right. From pre-order, the first value 3 is the root of the entire tree. In the in-order array, 3 splits the list into left side, 9. This is the left subtree. Right side, 15, 20, 7. This is the right subtree. Using the in-order index map, we can quickly find where each root appears. For the left subtree, pre-order gives us 9 next that becomes the left child of 3. For the right subtree, 20 becomes the root from pre-order, and 15 and 7 become its left and right children respectively based on the in-order split, 15, 27. Putting it all together, the tree we reconstruct is root, 3. Left child, 9. Right child, 20. Left child, 15. Right child, 7. Which corresponds to the level order output, 3, 9, 20, null, null, 15, 7, and that's exactly what our function returns. The reconstructed tree matches the expected structure perfectly. So, our implementation is correct. The recursion plus in-order index map rebuilds the tree in linear time and passes this test case smoothly. Now let's implement the iterative stack-based method, reconstructing the tree step by step while maintaining pre-order-driven structure. We begin our solution class containing the iterative tree building logic. This function reconstructs the binary tree using iteration and a stack. If pre-order is empty, the tree has no nodes. So we return none immediately. The very first value in pre-order is always the root, so we create a node for it. We place this root node onto a stack. This stack keeps track of the path of parents as we construct left and right children. This pointer walks through the in-order array to determine when we should stop building left children and start attaching right children. We iterate starting from the second pre-order value since the first one made the root. For each new pre-order value, we create a new tree node. Here's the key idea. If the top of the stack does not match the current in-order value, that means we are still going down the left subtree. So we attach this new node as a left child of the current stack top. And we push this new node onto the stack because future nodes may attach beneath it. Otherwise, the top of the stack equals the in-order value, meaning we finished building that left subtree and must start attaching right children. We repeatedly pop from the stack while its top matches the current in-order value. We store the pop node in last. This is the node that will receive the right child. We move forward in order since we've used up this node's in-order position. Once we stop popping, we know the new node must be the right child of the most recently popped node. We push the new node onto the stack so future nodes can attach beneath it. Finally, we return the root node, representing the fully reconstructed binary tree. And that's how this algorithm works. It first uses pre-order to decide the creation order of nodes, then uses a stack and in-order pointer to determine when to attach left children and when to switch to right children. Efficient, iterative, and elegant. Now let's test our iterative stack-based solution with the simplest possible tree. Both traversals contain just one value, -1, which represents a single node tree. In the iterative method, we start with the first value of pre-order, which is -1. This becomes the root node. We push this node onto the stack. We also track an index into the in-order array. Since in-order 0 is also -1, it confirms that this root has no left or right children, it's just a single node. No additional nodes are processed, no extra attachments are needed. The final tree is simply a root with value -1. This corresponds to the output, -1, and that's exactly what our program outputs, -1, perfectly matching the expected result. So, our implementation is correct. The stack-based approach cleanly handles even this minimal case, confirming the logic works for single-node trees as well as larger ones. Rebuilding a tree from its travel diaries sounds tricky, but with pre-order and in-order you've got a perfect roadmap. This is a classic interview favorite because it exposes whether you truly understand recursion, boundaries, and tree structure. Let's do a recap. We're given two traversals of the same binary tree: pre-order, root, left, right, and in-order, left, root, right. The goal is to reconstruct the original tree. Think of it like restoring an org chart from two reports, one in visit order, one in hierarchical order. We leaned on two core truths. The first item in pre-order is always the root, and in in-order, everything left of that root is the left subtree and everything right is the right subtree. The main pitfalls? Mismanaging indices and not respecting subtree boundaries as recursion unfolds. Our plan: create a fast lookup from value to its position in the in-order list. Use a moving position in pre-order to pick the next root. Then, with left/right bounds in the in-order range, recursively build the left subtree from the left side of the split and the right subtree from the right side. Stop when the current in-order window is empty. We followed that blueprint, advancing the pre-order position each time we formed a new node and using the in-order boundaries to keep each recursive call in its lane. No extra slicing work, just clean boundary management. We ran the solution on LeetCode. It constructed the sample tree correctly, handled empty input as null, built a single node tree for the one-element case, and coped with skewed trees. All tests passed without errors and the logic behaved exactly as expected. The big lesson: tree reconstruction is all about disciplined boundaries. Anchor each step on pre-order's next root, let in-order define the left/right regions, and let recursion do the assembly. Get the indices right, and the entire tree falls perfectly into place.
The interviewer smiled. Not because you were right, because they knew you were lost. Learn to spot the pattern before they spot the panic. PatternMastery.com.
Think you know your trees? Validate Binary Search Tree is a PatternMastery 100 essential and a classic filter in Google, Amazon, and Microsoft interviews. Nearly 1 in 3 candidates get tripped up by subtle edge cases or misuse of recursion. Master this, and you'll be ready for any problem that tests understanding of tree invariants and value constraints. Let's use the basic approach to tackle Validate Binary Search Tree so you'll never miss a hidden bug or boundary case. Let's break it down. Given the root of a binary tree, determine if it's a valid binary search tree, BST. For every node, all values in its left subtree must be less than the node's value, and all values in its right subtree must be greater than the node's value. Input: root node of a binary tree. Output: Boolean. True if the tree is a valid BST, otherwise false. Here is a real-world example. Suppose you're maintaining a database index tree. If the tree violates BST rules, searches become incorrect or inefficient. An interviewer might ask, how would you validate a config tree to ensure proper ordering for efficient range queries? Let's assess. What's tricky? A common mistake is to just compare each node with its immediate children, but BST rules require every value in the left subtree to be less than the current node, and every value in the right subtree to be greater, all the way down. Think step by step. Use recursion with value boundaries. Each time you descend left, update the upper bound, current node's value. Each time you descend right, update the lower bound. If any node violates these constraints, the tree isn't a BST. Let's go deeper. Start with the full possible value range. Example: from -infinity to +infinity. At every node, if the value isn't strictly within min, max, return false. Recursively validate left and right subtrees, passing updated bounds. Edge cases: duplicate values are not allowed in a BST, must be strictly less/greater. An empty tree is a valid BST. Subtle violations deep in the tree. Example is a right child of a left subtree is greater than root, must be caught. Here is the structure. Write a helper function with node, min, and max parameters. If node is null, return true. If node's value not in min, max, return false. Recursively validate left subtree, max equals node's value. Recursively validate right subtree, min equals node's value. Return true only if both subtrees are valid. Now let's implement the in-order traversal approach, verifying that the values appear in strictly increasing order to confirm BST validity. Here we begin by defining a class called solution. Think of it as a container that holds our algorithm. This line defines a function named as validBest that takes a tree's root node as input. This is the main function we'll call to check if the tree is a valid binary search tree. We create an empty list called stack. We'll use it to keep track of nodes as we explore the tree, like putting bookmarks while reading so we can come back later. This sets prev_val to -infinity. It acts as a baseline, the smallest possible value. So the first real node we read will always be bigger. This matters because BST values must always be increasing during an in-order traversal. We start our traversal at the root of the tree. This loop keeps running as long as there are nodes still to process or nodes stored in our stack. It ensures we visit every node once, which is why the time complexity is O(n). This inner loop walks all the way down the left side of the tree, just like following someone down a long hallway until it ends. We push the current node onto the stack so we can come back to it later. Think of it as placing a bookmark. When we reach the end of the left branch, we pop the top item from the stack. This is like opening the last bookmark we placed, returning to a previous node. This line checks the key BST condition. Every new value must be strictly greater than the previous value seen. If not, the BST rule is broken, so we immediately return false. If the rule is violated, we stop right away. The tree is not a valid BST. We update prev_val to the current node's value. This is like saying, okay, this value is now the new benchmark for the rest of the traversal. Next, we move to the node's right child, which in a BST contains larger values. The algorithm then repeats the same process. If we finish the entire traversal without breaking the BST rule, then everything was in strictly increasing order, meaning the tree is a valid BST. And that's how this algorithm works. It first uses a stack to simulate an in-order traversal setup, then checks values one by one to ensure they strictly increase. Efficient, simple, and elegant. Let's validate our BST using this input. 2, 1, 3. This represents a tree where 2 is the root, 1 is the left child, and 3 is the right child. In a valid binary search tree, if we perform an in-order traversal, left to root to right, the values should come out in strictly increasing order. Visit left subtree, then we get 1. Visit root, then we get 2. Visit right subtree, then we get 3. So the in-order sequence is 1, 2, 3. It's strictly increasing, with no duplicates and no violations of the BST rule. All left less than root less than right. That means the tree is a valid BST. And that's exactly what our function returns, true, matching the expected result. So, our implementation is correct. The in-order traversal check correctly identifies this tree as a valid BST. Now let's implement the recursion with bounds method, ensuring every node's value stays within its valid range as we traverse the tree. We begin by defining a class named solution. This class will hold our recursive BST checking method. This defines the main function as validBest, which takes the root of our tree. This is where our algorithm starts. We define a nested function called helper. Think of this as a specialist worker whose job is to check one part of the tree at a time. It receives node, the current spot we're inspecting. Low, the minimum value this node is allowed to have. High, the maximum value this node is allowed to have. If the node is empty, meaning we've reached past a leaf, that's perfectly fine. An empty subtree is always valid. We return true because reaching null means no BST rule was broken. Now we check the most important BST rule. Every node's value must fall strictly between low and high. This condition ensures that values remain ordered correctly across the entire tree, not just locally. If the node's value breaks that allowed range, the tree is not a valid BST, so we return false immediately. This is the heart of the recursion. We check both sides of the tree by shrinking the allowed boundaries. For the left child, the maximum allowed value becomes node.val. For the right child, the minimum allowed value becomes node.val. Think of it like giving each child its own stricter rulebook. Both sides must return true for the entire subtree to be valid. This recursive structure touches each node once, giving us O(n) time complexity. Finally, we call our helper function on the root node. We start with the widest possible boundaries, -infinity to +infinity, meaning the root can have any value. From there, the boundaries tighten as we go down the tree. And that's how this algorithm works. It first sets global lower and upper bounds for the root, then recursively tightens those bounds as it checks each subtree. Efficient, simple, and elegant. Now let's test the bounds-based recursive solution on this tree. 5, 1, 4, null, null, 3, 6. Here, 5 is the root, 1 is on the left, and 4 is on the right, with 3 and 6 as children under 4. The idea of the bounds approach is simple. Every node must lie within a valid range, min, max. For the left child, the max becomes the parent's value. For the right child, the min becomes the parent's value. Walking through. Start at 5 with bounds, negative infinity, positive infinity, that's valid. Go left to 1 with bounds, negative infinity, 5, then 1 is valid. Go right to 4 with bounds, 5, positive infinity. Here's the problem. 4 is not greater than 5, so this already violates the BST rule for the right subtree. Even deeper, 3 is in the right subtree of 5 through 4, so it would also be constrained to be less than 5, but 3 is clearly less than 5. The structure doesn't satisfy the global BST property. And that's exactly what our function returns, false, which matches the expected result. So, our implementation is correct. The recursion with bounds method successfully catches the violation in the right subtree and correctly rejects this tree as an invalid BST. So, how do you really know if a tree is behaving like a proper binary search tree? Validate binary search tree is the perfect check of whether you understand how recursion and constraints flow through a tree's structure. Let's do a recap. The problem asks us to confirm if a given binary tree follows BST rules, meaning every node's left subtree has smaller values, and every right subtree has larger values. Conceptually, it's about keeping the entire structure ordered, not just comparing neighbors. We discussed how many people slip by only checking parent-child pairs. The trick is realizing that each subtree inherits boundaries from its ancestors. As we move down, we must update those value limits, shrinking the valid range for each recursive call. Our logic was simple but powerful. Start with a wide range, say from negative to positive infinity. For each node, verify it fits within that range. Then, move left with an updated upper bound and move right with an updated lower bound. The recursion ends cleanly when all nodes fit their limits. We coded this recursive check, starting from the root and passing updated boundaries as we traversed. The function neatly returned true or false depending on whether every node respected its constraints. Running the solution on LeetCode confirmed it works perfectly. Valid BSTs passed as true. Invalid ones returned false, and tricky edge cases, like deep violations or empty trees, were all handled correctly without errors. The key takeaway: a valid BST isn't about direct neighbors, it's about inherited rules. Mastering that recursive boundary mindset ensures you won't miss hidden violations buried deep in the tree.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Did you know KTH smallest element in a BST is a PatternMastery 100 essential and a go-to question at Google, Facebook, and Amazon to test your mastery of binary search tree properties and tree traversal? Over 30% of candidates stumble on this, either by missing the in-order pattern or handling K incorrectly. Nail this problem, and you'll be ready for everything from ranking queries to real-time analytics. Let's use the basic framework to tackle Keith's smallest element in a BST step by step, so you'll be confident and clear in every interview. Let's break it down. Given the root of a binary search tree, BST, and an integer k, find the Keith's smallest value, 1 indexed, in the tree. Input: root node of a BST, integer k. Output: integer value of the KTH smallest element. Here is a real-world example. Imagine managing a leaderboard where you need to find the Keith top performer. Or, in a scheduling app, finding the Keith earliest event among time slots stored in a BST. An interviewer might ask, how would you efficiently find the median or percentile rank in a huge, dynamically changing dataset? Let's assess. What's tricky? A BST's in-order traversal, left root right, produces sorted values. The challenge is to traverse efficiently and stop exactly at the Keith value. Think step by step. Perform an in-order traversal of the BST. Use a counter to keep track of how many nodes you've visited. Once the counter reaches k, record the node's value and stop. Be careful. Do not keep traversing after finding the Keith node. Let's clarify. You can do this recursively or iteratively, using a stack. If the tree is very large and k is small, the traversal short-circuits early. Edge cases. K is 1, smallest, k is tree size, largest. Here is the structure. Initialize a counter, starting at 0, and a variable to store the result. Traverse the tree in an order, left root right. At each node, increment the counter. If counter equals k, record the node's value and return immediately. Return the result. Now let's implement the in-order traversal method, Leveraging the BST sorted property to retrieve the kth smallest element, we begin by defining a solution class. This just organizes our method neatly. This function will return the kth smallest value in a binary search tree. Thanks to BST properties, an in-order traversal gives us values in sorted order. Time complexity, O(n) in the worst case. We create an empty stack list. This will help us perform a manual in-order traversal, going left as far as possible before stepping back. We set a pointer node to the root so we can walk through the tree. We'll use count to track how many nodes we visited in sorted order. Once count hits k, we found the answer. This loop keeps running as long as we still have nodes to explore, or we have nodes stored in the stack. This ensures we traverse the entire left root right order. When we see a node, we always go left first, just like reading a sorted list from smallest to biggest. We push the current node onto the stack. Think of this like dropping breadcrumbs so we can return after exploring the left child. Then we move left. And we keep doing this until we can't go further, reaching the leftmost node. When the left path ends, we pop from the stack. This gives us the next smallest node in the entire tree. We've officially visited one more node in sorted order, so we increase our count by 1. We check if this is the kth node we visited. If it is, we found the answer. We return the node's value, the kth smallest element in the BST. If this wasn't the kth node, we move right and continue the in-order traversal. This keeps the sorted order going. And that's how this algorithm works. It first sets up a stack and pointer, then in order walks the BST, counting nodes until it lands on the kth one. Efficient, simple, and elegant. Let's test our in-order-based solution using this tree. 3, 1, 4, null, 2, with k equals 1. This represents a binary search tree where 3 is the root. 1 is the left child of 3. 4 is the right child of 3. 2 is the right child of 1. Because it's a BST, an in-order traversal, left root right, we'll visit the nodes in sorted order, performing in-order traversal. Go left from 3 visit subtree rooted at 1. Left of 1 is null, so we visit 1. Then go right to 2 visit 2. Then visit root 3. Then visit right child 4. So the in-order sequence becomes 1, 2, 3, 4. Now, k equals 1, which means we're looking for the first smallest element in the BST. In this sorted list, the first element is clearly 1. That's our answer. And that's exactly what our function returns, 1, which matches the expected result. So, our implementation is correct. The in-order traversal collects the nodes in sorted order and picks the kth element precisely, giving us the correct smallest value. Now let's implement the min-heap approach, collecting values and extracting the kth smallest using heap operations. We start by importing Python's heap-epi module. This gives us a min-heap, a data structure that always keeps the smallest element at the top. We define our solution class, which simply organizes our method. This method will find the kth smallest value in the binary search tree. Unlike the in-order approach, this solution collects all values and uses a heap. Time complexity, O(n) plus k log n. Because pushing all nodes is O(n), and popping k times from a heap costs k log n. We initialize an empty list called heap. This will become our min heap of all node values. We define a helper function traverse to walk through the whole tree. This will push every node's value into the heap. This is our base case. If we hit a null node, we stop exploring that branch. Here we push the current node's value into the min heap. The heap automatically keeps the smallest values at the top, like sorting, but done progressively. We move to the left child and continue the traversal. Then we explore the right child. Overall, this step gathers all values from the BST. We kick off the traversal starting from the root. After this line finishes, the heap contains every value in the tree. We now pop the smallest values from the heap until we reach the kth one. We pop k 1 times, leaving the kth smallest at the top. This removes one element from the heap. Each pop gives us the next smallest value. This happens k 1 times. And finally, the next pop gives us exactly the kth smallest value. That's our answer. And that's how this algorithm works. It first collects all values in a minute heap, then removes the smallest values until the kth1 surfaces. Efficient, simple, and elegant. Now we'll test the min-heap approach with this input tree. 5, 3, 6, 2. This tree represents a BST where 5 is the root, 3 is the left child, 6 is the right child. Under 3, 2, left, and 4, right under 2, 1, left child, the goal is to find the third smallest value in this BST. With the min-heap strategy, we Traverse the tree and push all node values into a min heap. The heap automatically keeps the smallest element at the top. We then pop from the heap k times. The element we get on the kth pop is the kth smallest value. If we look at the BST values in sorted order, they are 1, 2, 3, 4, 5, 6 first smallest 1. Second smallest 2. Third smallest 3. So after popping 3 times from the min heap, we should end up with 3. And that's exactly what our program outputs, 3, matching the expected answer. So, our implementation is correct. The min heap approach successfully pulls out the kth smallest value, and even though it's slightly heavier than pure in order when you just need k, it still works efficiently and accurately for this test case. Finding the kth smallest element in a BST is one of those problems that looks simple, until you realize how much it reveals about your grasp of tree structure and traversal. This one tests whether you truly understand how BST ordering naturally connects to an order traversal. Let's do a recap. Conceptually, the problem is about ranking within a tree. We're given a BST and a number k, and we need the kth smallest value. Because a BST's in-order traversal visits nodes in sorted order, our goal becomes, traverse in order, and stop at the kth step. The key insight here is that you don't need to sort anything manually. The BST structure does that for you. The challenge is controlling traversal flow and counting visits correctly. Whether you choose recursion or a stack-based approach, stopping at exactly the right moment is what keeps the solution efficient. We built the plan like this. Start an in-order traversal, move left first, visit the node, then move right. Keep a running counter of visited nodes. When the counter equals k, capture that value and stop traversing. That's the entire sorted order distilled into one clean recursive flow. We implemented that logic using either recursion or an iterative stack. Each node visit increased the count, and when the count matched k, we returned the node's value immediately. No unnecessary traversal or extra data structures were needed. Testing on LeetCode confirmed the method's precision. For k equals 3, the traversal sequence, 1, 2, 3, 4, 5, 6 correctly returned 3. Edge cases, like k equals 1 or k equals number of nodes, also worked flawlessly, proving that counter logic and traversal control were solid. The big takeaway? The in-order traversal is your built-in sorted list for BSTs. By combining it with precise counting, you can extract ranked elements directly from structure. No sorting, no arrays, just pure logic.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Ever wondered what makes tree interviews both tricky and fun? Lowest common ancestor of a binary search tree is a PatternMastery 100 favorite, routinely used by Google, Facebook, and Amazon to test how well you exploit BST properties. More than 30% of candidates overcomplicate it or miss the power of BST traversal. Let's make sure you're not one of them. Let's solve lowest common ancestor of a BST using the basic framework, a stepwise guide that ensures you never miss an optimization or edge case. Now let's break this down. You're given the root of a binary search tree, BST, and 2 nodes, P and Q. Your task? Find their lowest common ancestor, LCA, the deepest node in the tree that has both P and Q as descendants. Input, root node of a BST, and 2 node references P and Q. Output, the node representing their lowest common ancestor. Here is a real-world example. Imagine managing folder permissions in a company's shared drive. To find the closest shared folder for 2 users' files, you need the LCA. Or, in a genealogy tree, to find the nearest shared ancestor between 2 people. Let's assess it. What's tricky? With a normal binary tree, you'd need to search both subtrees recursively. But in a BST, every node's left children are smaller, and right children are larger, so you can leverage value comparisons to avoid unnecessary work. Now let's think step by step. Start at the root. If both P and Q are less than root, both nodes are in the left subtree, go left. If both P and Q are greater than root, both nodes are in the right subtree, go right. Otherwise, root is between P and Q, or equals one of them, that's the split point, and the LCA. Let's clarify. You don't need to visit every node. BST ordering lets you home in on the ancestor in OH time, where H is tree height. Edge cases. One node is ancestor of the other. Nodes are on different sides of root. Root is LCA. Here is the structure. Start at root. While root is not null, If both p and q are less than root, go left. If both are greater than root, go right. Else, root is the LCA, return it. If root becomes null, shouldn't happen for valid input, return null. Now let's implement the iterative BST property approach, walking down the tree until we reach the split point between the two nodes. We start by defining our solution class, just a container for the method we're about to write. This function finds the lowest common ancestor, or LCA, of two nodes p and q specifically in a binary search tree. Because it's a BST, values guide the path, making it very efficient. Time complexity, OH, where h is the tree height. We create a pointer cur starting at the root. We'll use this to walk down the tree following BST rules. We keep looping as long as our pointer hasn't wandered off the tree. Each loop narrows down the search for the LCA. Here's the key BST insight. If both p and q have values smaller than cur, that means both nodes are somewhere in the left subtree. So we simply move left. We shift our pointer to the left child and continue our search. Now we check the opposite direction. If both values are greater than cur, that means their LCA must live in the right subtree. So we move right. We slide the cur pointer down one level to the right. If neither of the previous conditions is true, it means something important. P and Q are now on different sides of the current node, or one of them is the current node. In all those cases, we've reached the lowest common ancestor. We return the node sitting in cur, because it's the one closest to both P and Q without going past them. That's our LCA. And that's how this algorithm works. It first starts from the root, then uses BST rules to steer left or right until the moment where the two nodes split paths. Efficient, simple, and elegant. Let's test our iterative BST-based solution using this input. This array represents a binary search tree where 6 is the root. Left subtree of 6, 2 with its children 0 and 4 has children 3 and 5. Right subtree of 6, 8 with children 7 and 9. We're asked to find the lowest common ancestor, LCA, of the nodes with values 2 and 8. In a BST, all values in the left subtree are smaller than the root, and all values in the right subtree are greater. We can use this property directly. Start at root 6. We check p equals 2 and q equals 8. One value, 2, is less than 6, and the other value, 8, is greater than 6. As soon as we see that p and q lie on different sides of 6, we know 6 is the split point, and that makes 6 the lowest common ancestor. We don't even need to go deeper. And that's exactly what our function returns, 6, matching the expected result. So, our implementation is correct. The iterative BST property solution quickly finds the LCA by just walking down the tree and stopping at the split point. Simple, efficient, and spot on. Now let's implement the recursive BST property method, narrowing the search by moving left or right until the lowest common ancestor is found. We begin by defining our solution class, which simply groups our method nicely. This function finds the lowest common ancestor of nodes p and q in a BST. This approach works by recording the path from the root to each node, and then finding the last shared node. Time complexity, OH, where h is the height of the tree. We define a helper function called findPath. Its job is to walk down the BST and record each step until it reaches the target node. We create an empty list called path. This will store every node we visit on the journey to our target. As long as we haven't run out of tree, we keep exploring downward. We add the current node to the path, sort of like dropping breadcrumbs along our route. If the target value is smaller than the current node's value, we know, thanks to the BST rules, that the target must be in the left subtree. So we move left and continue the search. If the target value is larger than the current node's value, then it must live somewhere in the right subtree. So we move right. If neither condition applies, we've arrived at the target. We break out of the loop. The completed path, from root all the way to the target, is returned. We compute the full path from the root to node P, and we do the same for node Q. Now we have two lists representing their roots through the BST. We initialize LAK, which will eventually hold the lowest common ancestor. We loop through both paths together, comparing nodes at the same positions. This works because paths start at the root and diverge only when P and Q split. If the nodes match at this position, that means both P and Q share this ancestor. We update LCA. We store this node as the newest shared ancestor seen so far. As soon as the paths disagree, the shared ancestry stops, so we break. We return the last node they had in common, which is exactly the lowest common ancestor. And that's how this algorithm works. It first records the paths from the root to each target node, then compares the paths to find the deepest shared node. Efficient, simple, and elegant. Now let's check. This tree represents a simple BST. 2 is the root. 1 is the left child of 2. We want the lowest common ancestor, LCA, of the nodes with values 2 and 1. With the find paths and compare approach, we find the path from the root to P, find the path from the root to Q, compare the two paths from the start and track the last common node. Let's write the paths. Path to P equals 2. Start at root 2. We're already at the target path is path underscore P equals 2. Path to Q equals 1. Start at root 2. Since 1 less than 2, go left to 1. Reach target path is path underscore Q equals 2, 1. Now compare the paths element by element. First element, 2, from path underscore P, and 2 from path underscore Q, match. Path underscore P ends here, while path underscore Q continues to 1. The last common node between the two paths is 2. That means the lowest common ancestor of 2 and 1 is node 2. And that's exactly what the program returns. So, our implementation is correct. The path-based method correctly identifies the root 2 as the lowest common ancestor in this small BST. If BST questions ever felt abstract, this one makes them click. The lowest common ancestor of a BST shows how a tiny ordering rule can guide you straight to the answer without searching everything. Let's do a recap. We're given a BST plus 2 nodes, P and Q. The goal is to return the lowest common ancestor, the deepest node that has both P and Q in its subtree. In plain terms, the closest shared parent in a value-ordered tree. The key advantage is the BST property. Left subtree values are smaller, right subtree values are larger. Instead of exploring both sides like a general tree, we compare P and Q against the current node's value to decide which single direction to go, or to stop at the exact split point. Start at root and loop, or recurse, with 3 simple checks. If P and Q are both smaller than the current node, go left. If both are larger, go right. Otherwise, you've hit the split, or matched one of the nodes, and that current node is the LCA. We followed that plan directly, using straightforward comparisons at each step. No extra data structures, no exhaustive search, just clean movement left or right until the split point appears. We ran it on LeetCode and verified the logic. When P and Q sit on opposite sides, the root at the split is returned. When one is an ancestor of the other, that ancestor is the answer. Edge cases like the root being one of the targets and tiny trees behaved exactly as expected, and everything executed without errors. The takeaway, in a BST, order is a compass. Let value comparisons guide your traversal, and the LCA reveals itself in OH time. No backtracking, no fuss.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
What happens when you need Google-level search plus support for wildcards? Design, add, and search words data structure is a PatternMastery 100 favorite and a must-know at top tech interviews, blending try-design with recursive search logic. Over 35% of candidates fumble the wildcard or get stuck on recursion. Let's make sure you're ready to shine. Let's break down design, add, and search words data structure using the basic approach, step by step, to cover all the nuances of both try operations and pattern matching. Build a data structure that supports. Add word. Adds a word into the data structure. Search word. Returns true if the word exists. Where. Can represent any letter. Wildcard. Input/output. Supports any lowercase word. Search may include. As a wildcard. Needs to handle both standard word lookups and pattern matches efficiently. Imagine a code search tool that must find variables or function names with partial information, like foo.bar matching foobar and foobar. An interviewer might ask, how would you design a dictionary with fast wildcard search for autocomplete or spell checking? What's tricky? Standard try can handle prefix search, but now you need to support period wildcards, which can match any character at a position. Recursive, DFS, search is required. When you hit period, you must explore all child nodes at that level. Must distinguish between matching a word's full length, is _end, and just matching a prefix. Think step by step. Use a try-node class, children, letter node, and is _end boolean. Add word. Same as regular try insert, follow/create nodes for each letter, set is _end at the end. Search, word. Walk down the try for each character. If current char is not period, follow the child node as usual. If current char is period, recursively try all children at this node. At the end of the word, return true only if the is_end is set. Use recursion to handle branching at period efficiently. Let's clarify. The wildcard search will branch out at each period, but prunes quickly if a child doesn't exist. The structure is the same as a standard try, but search must explore all possible matching paths when wildcards are present. Edge cases. Multiple wildcards, for example. A. E. Empty string, should only match if empty word was added. Search for word longer than any added, should return false. Try node. Children, dictionary for each letter is _end. Boolean word dictionary. Root node, try node add word, standard insert search word, recursive DFS with branching on. Now let's implement the length bucket strategy, grouping words by size so searches only compare against candidates of matching length. We start by defining the word dictionary class. This structure lets us store words and search them, even with wildcards. In the constructor, we create something simple but powerful. A dictionary called buckets. We'll group words by their lengths. This dictionary maps length list of words with that length. This helps optimize wildcard searches later. We define the method to add a new word to our dictionary. This line does two things at once. It ensures there's a list for the word's length. It appends the new word into that list. This way, we always store words grouped by size. This method checks whether a given word, possibly containing dots, exists in the dictionary. Time complexity, on middle.m. Because we compare against all words with the same length, we calculate the length of the input word. This determines which bucket we need to search in. If we don't even have words of this length, there's no chance the word exists, wildcard or not. So we return false. If there is no wildcard in the word, we can do a simple, fast membership check. We return whether the exact word appears in our bucket. No fancy logic needed here. For wildcard searches, we must compare the input word against every stored word of the same length. We begin by assuming the candidate could be a match. We may disprove that shortly. We compare the stored word, A, and the input word, B, character by character. If the input character isn't a dot and it doesn't match the candidate character, then this candidate is not a match. We mark it as not matching. And we break early because there's no point checking the rest. If after all comparisons the match flag is still true, then we found a valid match, return true immediately. And if none of the candidates matched, we return false to indicate the word doesn't exist. And that's how this algorithm works. It first groups words by their lengths, then checks only relevant buckets, comparing letters while respecting wildcards. Efficient, simple, and elegant. Let's check. These operations describe how we interact with our word dictionary. Word dictionary create the data structure. Add word bad add word dad add word mad search pad search bad search, add search b. In the bucket by length solution, we group words by their length. So all three words, bad, dad, and mad, go into the same bucket for length 3. Now let's walk through the searches. Search pad, we look into the length 3 bucket, bad, dad, mad. Compare each character. Pad versus bad p does not equal b no match. Pad versus dad p does not equal d no match. Pad versus mad p does not equal m no match. No word with exact pattern pad return false. Search bad same bucket, length 3. Bad versus bad all characters match return true. Search, add dot, is a wildcard that can match any single character. Compare against bad. Dot, matches b. A matches a. D matches D full match return true. We don't even need to check the rest. Search B. First char must be B. Next two can be anything. Compare with bad. B matches B. Matches A. Matches D match return true. Putting all results together. Null, 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 null. False, true, true, true. And that's exactly what we see from the program. Every search behaves as expected. So, our implementation is correct. The bucket by length approach handles exact matches and wildcard patterns correctly by only scanning words of the same length, simple, organized, and working as intended. Now let's implement the try with DFS, allowing us to explore branching paths and handle wildcard characters smoothly during searches. We begin with a word dictionary class. This structure stores words in a special tree called a try. This try lets us search with wildcards efficiently. Our constructor sets up an empty dictionary that will act as the root of our try. This empty dictionary will grow into a nested tree structure like B, A, T, $, true. Each level represents a character in stored words. This method inserts a new word into the try, one character at a time. We start at the root of the try. We walk through each character in the word we're adding. This line does something powerful. If the character key exists, go into it. If it doesn't, create a new dictionary and go into that. This builds the try branch automatically. We mark the end of the word by storing a special symbol, $. This lets us distinguish full words from prefixes. The search function uses a depth-first search to handle both normal characters and wildcards. Worst case time complexity. OM middle. 26k, because every can branch into all 26 letters. We define a recursive DFS function that matches characters one by one. Node is the current position in the try, I is the current index in the search word. If we've reached the end of the search word, we return whether this try node marks a complete word. This prevents treating prefixes like full words. We read the current character we're trying to match. If the character is a wildcard dot, we must try every possible child node at this level. We iterate over each child character in the try node. For each character branch, except the end marker $, we recursively try to match the rest of the word. If any branch succeeds, we return true. If none of the branches matched, in case of a wildcard, then this path is invalid, return false. For a normal character, if the try branch doesn't exist, there's no possible match, return false. If the branch exists, continue the search by diving into the next character. Finally, we start the DFS from the root, beginning at index 0. The recursion handles all wildcard and character logic cleanly. And that's how this algorithm works. It first builds a try structure, then uses depth-first search to explore all matching possibilities, handling wildcards with elegant branching. Efficient, powerful, and elegant. Let's check. In this version, we use a try where each node represents a character, and we perform DFS when we encounter wildcard stuff. We insert the same 3 words. Bad dad. Mad. Each word becomes a path in the try from the root to an end of word node. Now we run the same series of search calls, but using DFS. Search paths start at root follow P. There is no P child at the first level. We only have B, D, and M. Search fails immediately return false. Search bad follow B a D in the try. We land exactly on a node marked as end of word return true. Search, add at the first character, we branch, try every child of the root, B, D, M. For each path. Take B then check add a then D exist as children we reach an end of word node return true. Because DFS finds at least one valid path, the search succeeds. Search B, first character B we go down the B branch. Next character is, so we can go to any child of B, which is A. Next character is another, so from A we go to any child D. We reach the node for bad which is marked as a word return true. So, once again, our sequence is, null, 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 false, true, true, true. And that's exactly what the program outputs. A perfect match with the expected results. So, our implementation is correct. The try plus DFS approach fully supports wildcard searches by exploring all possible branches when needed, while still answering all these queries accurately. Wildcard search at Google speed isn't magic, it's design. In this problem, we blended a try with smart recursion so pattern matches with feel instant and reliable. Let's do a recap. The goal was simple. Build a structure that can add words and search them, where can stand in for any single letter. Conceptually, we're storing shared prefixes once and answering both exact and wildcard queries in OL time. The tricky part is the wildcard. A plain try handles exact matches and prefixes, but forces branching. We solve this by exploring all children at the wildcard position, while still enforcing that a full word must end at the final node, not just a prefix. We organized everything around a try node with character links and an is_end flag. The plan. Add word walks or creates nodes per character, then marks the end. Search scans character by character. On letters we follow the link, and on. We recursively try each child. Success only counts if we land on a node marked as a complete word. We followed that blueprint exactly. Standard insert for adds, depth first branching on. For searches, and kept the logic tight to avoid unnecessary paths. The solution ran cleanly without errors. We verified on LeetCode. After adding bad, dad, mad, searches like pad returned false, bad returned true, and patterns such as add and B returned true. Edge cases behaved as expected, and tests passed. The takeaway: combine try sharing for prefixes with precise DFS at wildcard spots. Respect the is_end check, branch only when you see, and you'll get fast, correct pattern matches every time.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
What if you had to search hundreds of words in a giant grid, instantly? Word Search 2 is a PatternMastery 100 Super Challenge and a favorite at Google and Amazon for testing your ability to combine tries with grid backtracking. Over 40% of candidates either time out or overcomplicate their solution. If you ace this, you can handle big data search and optimization. Let's break down Word Search 2 using the basic method, so you can attack even the hardest grid search questions with confidence. Given a 2D board of letters and a list of words, return all words that can be formed in the board by sequentially adjacent letters, horizontally or vertically. The same cell can't be reused in a single word. Input: 2D grid of letters, board. List of words, words. Output: list of strings. All words found in the board. Think about an app that suggests all possible words you can swipe in a Boggle or Scrabble game board. An interviewer might ask, how would you optimize a word search engine that checks for all valid dictionary words in a large letter grid? What's tricky? Checking every word individually with DFS is too slow, needs try optimization. Must prune searches early if the prefix isn't in any word. Handle duplicate word discoveries and overlapping paths. Must manage visited cells and efficiently mark words as found. Think step by step. Build a try with all words. This allows O1 prefix checks, making it fast to abandon dead-end searches for every cell in the board. Start DFS/backtracking to search for words. At each step, follow the try based on the current board letter. If you reach a try node with a word, add to results. Mark cells as visited, for example, temp set to hash, then restore after recursion, backtrack. If no further try child exists for the path, stop the search immediately. To avoid duplicates, set the found word to none or remove it from try after it's found. Let's clarify. The try enables prefix pruning. Never explore if the prefix isn't possible. Backtracking manages cell visits per word path. Only need to explore directions, up, down, left, right. Edge cases. Board or word list empty. Return. Square brackets. Overlapping word paths. Duplicates in input words should only report found once. Build a try from words. Loop over each board cell. For each cell, run DFS. If try has no matching child for letter, return. If try node's word exists, add to result and set to none. Avoid repeats. Mark cell as visited. Hash, recurse in 4 directions. Backtrack, restore cell. Collect and return results. Now let's implement the brute force backtracking approach, checking each word individually by exploring the board in all 4 directions. We start by defining our solution class. Nothing special yet. Just organizing our method. This method will search the entire board for all words from the input list. It uses heavy backtracking, so expect exponential behavior for long words. We immediately check if the board is empty. If there is no grid to search, we return an empty list. We capture the number of rows, m, and columns, n, for easy use later. This will store all words we successfully find on the board. We define an inner function that checks whether a single word exists on the board. We'll run this for every word in the input. We store the word's length. This helps us know when we found all characters. This DFS attempts to match the word starting from the board position, R, C, and matching character index I. Visited keeps track of used cells so we don't reuse them. If we've matched all characters of the word, that means we've successfully found it. We return true, signaling success. This bounds check prevents stepping outside the grid. If we've already used this cell, or the letter here doesn't match the needed character, this path is invalid, return false. We mark this cell as used to avoid revisiting it. We try all 4 directions, up, down, left, right, to continue matching the next character. This branching creates up to 4 recursive calls each time. This is where the exponential time complexity comes from. After exploring all paths from this cell, we unmark it so other paths may use it. This is classic backtracking. Return whether any branch successfully matched the remaining characters. We iterate over every row of the board, and every column, trying each cell as a potential starting point. We launch a DFS from this cell to see if the word can be built starting here. If any starting cell works, the word exists on the board. Otherwise, after trying all cells, the word isn't present. We loop through each unique word. Using set removes duplicates and saves work. We check whether that word can be formed on the board. If yes, we add it to our result list. Finally, we return all words that were successfully found. And that's how this algorithm works. It first checks each word individually, then uses DFS backtracking from every cell to see if that word can be built. It's simple to understand, brute force in nature, and elegant in how it explores all possible paths. Let's test our pure backtracking solution on this board and word list. The board is a 2D grid of characters, and each word in words has to be formed by moving up, down, left, or right, without reusing the same cell in a single word. Our backtracking algorithm tries to start each word from every cell that matches its first letter, then explores all 4 directions recursively. Let's see why the found words make sense. For oath, start at O at position 0, 0. From O, move to A at 0, 1. From A, move down to T at 1, 1. From T, move down again to H at 2, 1. We've successfully traced O at TH in adjacent cells with no reuse. Oath is valid. For eat, start at E at 1, 0, or 1, 3, but the successful path is E at 1, 3, A at 1, 2, T at 1, 1. This gives the path EAT. Again, using valid neighbors, eat is valid. For P, we try to start from any P on the board, but there is no P at all, so backtracking never finds this word. P is not in the result. For rain, we look for a R and try to build rain from it. Even starting from R at 2, 3, we can't chain to a I, N in the required order through adjacent cells without breaking the rules. So rain is also not found. So the only words that can be formed on the board are oath, eat, and that's exactly what our program returns. So, our implementation is correct. The backtracking search explores valid paths on the grid, respects the adjacency and no reuse rules, and correctly picks out only the words that can actually be formed. Now let's implement the try-powered backtracking method, pruning paths early and collecting valid words efficiently using a shared prefix structure. We begin by defining our solution class. This simply wraps everything we're about to build. This function tries to find as many words as possible from the list, using the grid provided. First, we check whether the board is empty. If it is, there's nothing to search, so we return an empty result right away. We create a dictionary that will act as our try, a fast prefix tree for searching word patterns. We loop over every word that we want to look for, starting at the root of the try for each new word. We walk through each character of the word. If the character path already exists, we follow it. If it doesn't, we create a new branch. It's like building a map of prefixes. When we reach the end of the word, we mark that with a special hash key and store the full word. This lets us recover the word later when we find it in the grid. We store the number of rows and columns so we can stay inside the boundaries. This list will hold all the words we successfully discover on the board. We define a DFS function that will try to match characters starting from cell, R, C, and the current try node. We get the current character from the board so we know what we're working with. If this character doesn't exist in the try path, we stop. This path can't form any word. We move deeper into the try, following the branch for this character. This is a clever trick. If this try node has a completed word, hash, we remove it and store the word in res. Removing it prevents duplicates in the result. If we found a finished word, we add it to our results. We temporarily mark this cell as visited by turning it into a dot. This prevents reusing the same cell in the same word path. Each of the following lines checks boundaries and ensures the next cell isn't already visited. We explore upward if it's safe. We explore downward. We explore left. We explore right. This branch exploration creates the 4 middle. 3t time complexity pattern. After the first move, each next step has at most 3 directions to explore. We restore the original character so future DFS calls can use this cell again. That's classic backtracking. If the current try branch has no more children after exploring, we prune it. This optimization makes searching faster by removing dead branches. We iterate through every row and every column. Each cell is a potential starting point for a word. For each cell, we call DFS to explore all word possibilities starting there. At the very end, we return all the distinct words we discovered on the board. And that's how this algorithm works. It first builds a try to efficiently store all words, then performs DFS from each cell to explore possible paths, pruning the try as words are found. This turns an expensive brute force problem into something far more efficient, elegant, optimized, and surprisingly clean. Now we test the optimized version that uses a try plus backtracking plus a hash set to avoid duplicates. The board is a small 2x2 grid, and we only have one word to look for. ABBB. With the try-based approach, we insert ABB to the try. Then, we start backtracking from each cell in the board, following try nodes as we go. Let's see if ABCB is even possible. Start at A at 0, 0, matches the first letter A. Next we need B. The adjacent cells to 0, 0, are 0, 1, B, black check mark emoji. 1, 0, C, multiplication sign emoji. So we move to B at 0, 1. Now our path is AB. Next we need C. From B at 0, 1, the neighbors are 0, 0, A, already used in this path, can't reuse 1, 1, D, multiplication sign emoji. There is no valid C reachable without reusing a cell, so this path fails. Even if we try other starting positions, like B, C, or D, we can't form ABB because the word needs B twice, and the grid is too small and too constrained to visit a second B without reusing a cell, which is not allowed. So no valid path in the board matches ABB under the word search rules. The set of found words is therefore. And that's exactly what our program returns, an empty list. So, our implementation is correct. The try plus backtracking solution efficiently prunes impossible paths and correctly determines that no words from the list can be formed on this board. Big grid, huge dictionary, and we still want instant results. That's the challenge of word search 2. This problem tests whether you can fuse a try with disciplined backtracking to stay fast and avoid dead ends. Let's do a recap. We're given a letter board and a list of words. We need to find every word that can be formed by walking adjacent cells. No reusing the same cell within a single word. The output is all valid words we can actually trace on the board. Brute forcing each word with DFS is too slow. The key is a try for prefix checks. It lets us abandon paths early when the current letters can't lead to any word. We also have to manage revisits, overlapping paths, and prevent duplicates once a word is found. Our plan. Build a try from all words to enable O1 style prefix pruning. Start a DFS from every cell, following the try as we move. If we land on a try node that holds a complete word, record it and mark it so we don't report it twice. Use visited marking while exploring, then backtrack cleanly to restore the board. We executed that blueprint. Try for fast prefix checks, DFS from each cell, prune immediately when there's no matching child, mark cells during the path, and backtrack to continue exploring. The code ran smoothly without errors. On LeetCode, the solution returned exactly the words present in the board. In the example, it found oath and eat, skipped entries that aren't present, handled duplicates correctly, and passed the test cases as expected. The takeaway: performance comes from pruning. Pairing a try with careful backtracking turns a massive search space into a set of focused paths, fast, accurate, and interview-ready.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Word ladder. This is the graph problem interviewers love. Word ladder. It looks like a toy puzzle. Change one letter at a time, but secretly tests BFS instincts, hashing, and pre-processing. This PatternMastery 100 favorite appears at Meta/Amazon screens because many candidates brute force neighbors and time out. We'll blitz it with basic and finish in clean ON_L², or better with bidirectional BFS. We're given begin word, end word, and a word list. Each step you can change exactly one letter, and the new word must exist in the list. Return the length of the shortest transformation sequence from begin word to end word, counting both ends. If impossible, return 0. Shortest number of steps in an unweighted graph? That's BFS. But we can't build edges naively, too slow. Instead, pre-process using generic patterns. For each word, replace each position with two form keys like HT or IT. Words sharing a key are one edit apart. Then BFS from begin word using this pattern map. Complexity. Build map in ON_L keys and traverse neighbors in ON_L² worst case. For extra speed, we can run bidirectional BFS from both ends. If end word not in the list, return 0. Put all words into a set. Ensure begin word is included for pattern generation. Build patterns. Dict str, list str, by replacing each position with standard BFS, Q holds, word, distance. For each popped word, iterate its patterns and neighbors, in queue unvisited neighbors at dist +1. Mark visited as soon as in queued. Let's wrap up the word ladder problem. Now let's solve solution 1. We're walking through the word ladder problem using a single direction BFS approach. I'll break everything down line by line, explain it in simple language, and guide you through how the algorithm works step by step. Time complexity is ONM26, where N is the number of words in the word list, M is the length of each word, and 26 is the number of possible letter substitutions we try at each position. The idea of BFS for word ladder: treat each word as a node in a graph. Two words are connected if they differ by exactly one letter. Use BFS to explore level by level. As soon as we reach the target word, that level count is the shortest transformation length. The goal is to change one letter at a time until you reach the end word. Line-by-line explanation of the code. First, we import deck. This gives us a fast queue structure that lets us pop from the front quickly, perfect for BFS. We create a class called solution. This is the standard format when submitting problems to LeetCode. This defines our function. It will compute the shortest transformation steps from the starting word to the target word. We convert the list of words into a set. This makes checking if a word exists super fast. Instead of searching through a list, we just ask the set. We check if the end word is even reachable. If the end word isn't inside the list, then there's no way to transform into it. We return 0 immediately, meaning no possible transformation. We create our BFS queue and start with the beginning word. This is the first word in our search path. We track words we've already visited so we don't repeat and cause loops. We set the starting level to 1. The begin word already counts as the first step. As long as there are words in the queue to explore, we keep going. That's the core of BFS. We process all words in the current level before moving deeper. This is how we count transformation steps correctly. We take the next word from the queue. This is the word we'll try transforming. If this word is already the target, we're done. We return the number of steps taken to get here. BFS ensures this is the shortest path. We look at each position of the word, preparing to replace one letter at a time. We test all 26 possible letters for that position. This simulates every allowed single step change. We build the new word by swapping the character at position I with the letter C. We check if this new word is part of the allowed dictionary and if we have visited it already. If it's valid and new, we can explore it. We mark this new word as visited so we don't process it again. We add it to the BFS queue for the next level of exploration. When we finish exploring all words in the current level, we increment the step count before moving to the next. If we finish the entire BFS without finding the target, we return 0, meaning no valid transformation path exists. And that's how this algorithm works. It first builds the BFS setup, then explores all possible one-letter transformations level by level until it reaches the target. It's clean, predictable, and efficiently finds the shortest path. BFS guarantees the shortest transformation sequence. Each word can branch into up to 26 times word_length possible neighbors. Using a set ensures fast lookups. Worst case time complexity is ONM 26. Now that we've implemented our BFS solution for the word ladder problem, it's time to test it with an actual input. This step shows how the algorithm behaves in practice and ensures that our logic produces the correct result. We will walk through the input, observe how the solution processes it, and confirm that the output matches what we expect. Let's test our function using this input. We have a starting word hit, a target word cog, and a dictionary of words that we can use to transform hit step by step into cog. Here's why the solution works. The algorithm uses a breadth-first search to explore all possible single-letter transformations from hit. It keeps track of visited words to avoid repetition. Step by step, it finds the shortest sequence of transformations leading to cog. For example, the chain hit hot.dog gives a total of 5 steps, which is the shortest path. And that is exactly what the program outputs, 5. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully finds the shortest transformation sequence between the start and end words. It handles the given input correctly and produces the expected output. BFS ensures efficiency, avoids unnecessary repetitions, and guarantees the minimal path. This is solution 2, finding the shortest transformation sequence between two words using bidirectional BFS. We expand from both the start and end words simultaneously, checking for overlaps. Time complexity is ONM, faster in practice, where N is the number of words in the list and M is the length of each word. Bidirectional BFS reduces the number of levels explored compared to standard BFS. We import deck to efficiently perform queue operations for BFS. We define a class solution to hold our method. The function ladder length computes the length of the shortest transformation sequence from begin word to end word. Convert the list of words into a set for O1 lookups. If the target word isn't in the list, return 0. Initialize sets for BFS from both ends. Begin_set containing begin word, end_set containing end word. Initialize a visited set with begin word and set length equals 2 to start counting the sequence. While both frontiers are non-empty, always expand the smaller frontier to reduce the number of iterations. Swap begin underscore set and end underscore set if necessary. Initialize an empty set next underscore set for the next level. For each word in the current frontier, for each character position, try replacing it with letters A to Z to form new potential words. If the new word exists in the opposite frontier, the searches have met. Return the current length. If the new word is in word set and not visited, mark it visited and add it to next underscore set. Replace begin underscore set with next underscore set and increment length by 1. If BFS completes without meeting the two ends, return 0, no valid transformation exists. Bidirectional BFS reduces levels explored compared to standard BFS. Each word generates 26 length transformations at each step. Worst case complexity is O&M, but it is practically faster due to reduced search space. Before checking the output, let's understand the problem. We are given begin word equals hit end word equals cog word list equals hot.dog lot log. The goal is to find the shortest transformation sequence from begin word to end word, changing one letter at a time, using only words in the list. If no path exists, the function should return 0. Let's test our function with this input. Here, cog is not reachable from hit using the given words. Here's why the solution works. Bidirectional BFS. Start from both begin word and end word to expand towards each other. Always expand the smaller frontier to optimize search. Generate neighbors. For each word in the current frontier, try changing each letter from A to Z. Only add new words if they are in the word list and not visited. Check for meeting point. If a new word appears in the other frontier, a path is found, return the current length. If no path is found after exploring all possibilities, return 0. Step by step with this input. Hit hot, possible, hot dot or lot dot dog lot log, but cog is missing in word list, so the frontiers never meet. The function correctly returns 0. And that is exactly what the program outputs, 0. This confirms that the code handles cases where no transformation path exists. So, our implementation is correct. It successfully identifies when a word ladder is impossible, efficient, accurate, and reliable. Our implementation is correct. It correctly identifies when no path exists. It efficiently searches using bidirectional BFS. It returns the correct shortest length when a path is possible, or 0 if impossible. Let's wrap up the word ladder problem. At first glance, it seems like a simple word game, changing one letter at a time, but underneath, it's a classic graph challenge that really tests your BFS intuition. Breakdown recap. We started with the idea of transforming a begin word into an end word, step by step, where every new word must exist in the list. Our goal was to find the shortest path from start to finish, and if it wasn't possible, we'd return 0. Assess recap. To solve it efficiently, we recognized that this was a shortest path problem in an unweighted graph, perfect for BFS. Instead of brute forcing every word connection, we optimized using pattern preprocessing, where we replaced each letter with a wildcard, creating keys LeetCode or it to group words that differ by just one letter. Structure recap. From there, we structured our approach. First, check if the end word exists in the list. Then, build all pattern mappings and perform BFS to explore word connections layer by layer, counting each transformation step until we reach the target. Implement recap. After implementing it, we ran the code on LeetCode, no errors, smooth execution. Check recap. When we tested it with multiple cases, the outputs matched perfectly, confirming our logic worked as expected. The big takeaway? Word ladder isn't just about words, it's about recognizing graph patterns and using BFS smartly. Once you see that connection, the path to the solution becomes crystal clear.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Ever been asked, is this tree height balanced? This PatternMastery 100 classic screens your recursion chops and big O instincts. Many candidates compute height twice and time out. Today we'll solve balanced binary tree in a single post-order traversal, clean, linear, and interview ready, using the basic framework. We're given a binary tree root. A tree is balanced if, for every node, the absolute difference between the heights of its left and right subtrees is no more than 1. We must return true or false. A naive approach calls height for every node, making ON squared in the worst case. Instead, do one post-order DFS that returns two things at once, whether the subtree is balanced and its height. As soon as any subtree is unbalanced, bubble that up to stop extra work. Time ON, space OH for recursion depth, worst case ON, average O log N. Plan the helper DFS node. If node is none, return true, 0. Recurse left, then right. If either side is unbalanced, return false, 0. Compute balanced equals abs HL hour, less than equals 1 and height equals 1 plus max HL, hour. Return balanced, height. The top calls balanced is the answer. Empty trees are balanced with height 0. Compute left and right. If either is unbalanced, stop early. Current node is balanced if the height diff less than or equal to 1. Compute height in the same pass. For a perfectly full tree, left and right heights always differ by 0 or 1 returns true. For a chain, linked list like 1 2 3 4, one side's height grows while the other stays 0. A node will have diff greater than or equal to 2 returns false. Each node visited once ON. Recursion stack OH. Here's the final complete solution for balanced binary tree. We do a single post-order DFS that returns balanced height from each node and short circuits on the first violation. Simple, linear, and interview ready. Level up your tree recursion by practicing diameter of binary tree, returns height while tracking the best path, maximum depth of binary tree, pure height computation, same tree, symmetric tree, paired DFS comparisons, lowest common ancestor of a BST/binary tree, propagate matches upward like our Boolean, and validate binary search tree, carry min/max bounds during DFS. These reinforce post-order reasoning, short-circuiting, and bundling multiple pieces of info in one traversal. Now, let's break down the first Python solution for balanced binary tree, a simple, clear approach to checking if a tree is balanced. Here we're defining a class called solution. LeetCode uses this structure so it knows where to find your method. Think of it as the container that holds our function. This line defines the main function, is balanced. It takes the root of a binary tree and returns true or false depending on whether that tree is height balanced. This is the function LeetCode calls for each test. Inside our main function, we define a helper called height. This helper will calculate how tall a subtree is. It's like measuring how many levels deep a branch of the tree goes. We start by checking if the node is empty. An empty node has no height at all. So if the node doesn't exist, we simply return 0, meaning the height is 0. If the node does exist, we compute the height of both the left and right subtrees. Then we take the bigger one, because the height of a tree is determined by its longest path. Adding 1 counts the current node. This height calculation is repeated many times throughout the tree, which is why this brute force approach can take ON squared time in the worst case. Now back in the main function, if the entire tree is empty, we consider it balanced automatically. So if there's no root, we return true. Here we calculate the height of the left and right subtrees and compare them. If the height difference is more than 1, the tree becomes visually lopsided, meaning it's not balanced. Notice that we call height again here, and each call recurses down the entire subtree. This repeated scanning is what contributes to the ON squared runtime. If that imbalance is detected, we immediately return false. If the current node is balanced, we still need to ensure that both the left and right subtrees are also balanced. So we recursively call is balanced on each side. Only if both return true do we confirm the tree is fully balanced. And that's how this algorithm works. It first measures the height of each subtree, then checks whether every node stays within the allowed height difference. Efficient, simple, and elegant. Test case check. Let's walk through it. Input root equals 3 9 20 null null 15 7. Alright, let's put our solution to the test using this tree input. 3 9 20 null null 15 7. This array represents a binary tree in level order form. 3 is the root. 9 is the left child, 20 is the right child. The nulls mean that 9 doesn't have any children. And finally, 15 and 7 are the children of 20. In this kind of problem, we're checking whether the tree is height balanced, meaning the left and right subtrees of every node differ in height by at most 1. For node 3, the left subtree rooted at 9 has a height of 1. The right subtree rooted at 20 has a height of 2, because of 15 and 7. The difference is only 1, still within the allowed range. Every other subtree is also balanced. Output: true. And that's exactly what our function returns, true. This matches the expected result, which confirms that our implementation correctly detects a balanced binary tree. So, our implementation is correct. The algorithm efficiently checks tree heights and balance conditions, ensuring every subtree meets the criteria, accurate and reliable. We begin by defining the solution class, the standard structure where LeetCode expects our method to live. This defines our main function, isBalanced, which will determine whether the binary tree is height balanced. Inside the main function, we define a helper called height. This function computes the height of a subtree, and detects imbalance along the way. This clever structure allows us to check balance in ON time by doing everything in a single DFS traversal. We start by handling the simplest case. If the node is empty, its height is 0. And we return 0 because an empty subtree has height 0. We recursively compute the height of the left subtree. If the left subtree is already unbalanced, it returns -1. And if that happens, we bubble up the -1 immediately, skipping all further work. Next, we compute the height of the right subtree. Same idea. If the right subtree is unbalanced, we pass the -1 upward right away. Here we check the balance condition at the current node. If the height difference between left and right is more than 1, this node becomes unbalanced. So we mark the entire subtree as unbalanced by returning -1. If everything is balanced, we return the height of this subtree, 1, for the current node, plus the taller of the two children. Finally, we check the height of the whole tree. If the helper returns -1, the tree is unbalanced. Otherwise, it's perfectly balanced. And that's how this algorithm works. It first sets up a height-checking helper with early imbalance detection, then uses a single DFS pass to compute heights and verify balance at every node. Efficient, simple, and elegant. Let's test our function using this input. 1, 2, 2, 3, 3, null, null, 4, 4. These numbers represent a binary tree in level order form. The 1 is the root, the 2 2s are its children, and the deeper values like 3 and 4 show how far the branches extend downward. The null entries mean that no child exists at those positions. Quick logic check. Here's why the solution works. The algorithm checks whether the binary tree is height balanced, meaning no subtree differs in height by more than 1. In this input, the left subtree keeps extending deeper, 3 4. The right subtree also extends but not evenly. Eventually, one branch goes 2 levels deeper than its sibling. This imbalance causes the tree to fail the height balance condition. False, and that's exactly what our program outputs, false. This confirms that our code is working correctly and passes the test case. Our implementation is correct. The algorithm successfully detects that the given tree is not height balanced, efficient, accurate, and reliable. Ever been asked if a tree is height balanced? Balanced binary tree. This one's a real interview classic. It tests how well you understand recursion, efficiency, and when to stop unnecessary work. We needed to determine whether a binary tree is balanced, meaning, for every node, the heights of its left and right subtrees differ by no more than 1. The goal was to return a simple true or false. The brute force approach calls a separate height function for every node, which ends up being ON squared in the worst case. Instead, we optimized it by combining both the balance check and height calculation in a single post-order traversal. That keeps it linear, ON time, and space proportional to the tree's height. We used a helper function that visits each node once. For each subtree, it returns 2 things, whether that subtree is balanced, and its height. As soon as one side is unbalanced, we immediately stop and bubble that result up, avoiding extra computation. We ran the logic in LeetCode, and it worked smoothly. No errors, no redundant height checks. The recursive calls handled balance and height together just as planned. After testing across multiple trees, every case passed, from perfectly balanced trees to skewed, chain-like ones. The solution produced correct results and ran efficiently. The big takeaway? Smart recursion isn't about writing more code, it's about returning more insight from each call. Bundling balance and height together is what makes this approach clean, elegant, and interview-ready.
Honestly, I only did patterns. Then they got the offer. PatternMastery.com.
Ever wonder what a tree looks like from the hallway? Only the rightmost nodes peeking out? Binary tree right side view. PatternMastery 100 is a quick litmus test for your BFS/DFS instincts. Bong interviewers love it because one clean pass nails it in ON, and the explanation shows you can tame levels and visibility like a pro. Let's crush it with basics. We're given a binary tree. From the right side, at each depth we only see the rightmost node. Return a list of those node values from top to bottom. 2 clean patterns. BFS by level, Q. The last node we pop for a level is the one that's visible. DFS, right first, pre-order. The first node we hit at each depth is visible. Both are ON time, OW space, W equals tree width. We'll do BFS. It maps perfectly to one value per level. Plan with BFS. If root is none, return. Push root to a queue, while queue not empty. Record current size equals len queue. Iterate that many nodes. In queue children. The last node in this loop is the right side value for the level. Append it. Handle empty tree. Seed the BFS with root. For each level, walk exactly size nodes. The last one we visit is visible from the right. We've collected the rightmost node per depth. Return the view. Consider the tree in the image. Level order is 1, 2, 3, 4, 5, 6, 7. The rightmost per level is 1, 3, 6, 7. Let's sanity check a couple cases. Each node enters/leaves the queue once ON. Queue holds at most a level's width OW. Here's the final complete solution for binary tree right side view. We do a level order BFS and record the last node of each level, 1 pass, ON time, and crystal clear to explain. To deepen tree traversal instincts, try binary tree level order traversal, foundational BFS by levels, binary tree zigzag level order traversal, same BFS with alternating order, left side view, mirror of this problem, take the first node per level, vertical order traversal, group by column using BFS/coordinates, and average of levels in binary tree, aggregate values per level. These strengthen your command of queues, level boundaries, and what to capture at each depth. Now, let's break down the first Python solution for binary tree right side view, a clean and intuitive approach that shows us exactly which nodes are visible from the right side of the tree. First, we define the solution class. This is simply the container LeetCode uses to run our code. You can think of it as the outer wrapper that holds our algorithm. Next, we define the main function called right side view. This function receives the root of a binary tree, and its job is to return a list of node values that are visible when viewing the tree from the right side. Before doing any processing, we check whether the tree is empty. If there's no root node, that means the tree has no nodes, so there's nothing visible from the right side. In that case, we immediately return an empty list. Next, we create an empty list called res. This list will store the values of the nodes that are visible from the right side of the tree. Now we initialize a queue and place the root node inside it. This queue allows us to perform breadth-first search, which processes the tree level by level. Using BFS ensures every node is visited exactly once, giving the algorithm a time complexity of ON. This loop continues running as long as there are nodes in the queue waiting to be processed. Each iteration of this loop represents processing one level of the tree. Here we capture the number of nodes currently in the queue. That number represents the total nodes in the current level. Now we iterate through all nodes at the current level. One by one, we remove a node from the front of the queue. This gives us the next node to process, similar to taking the next person from the front of a line. This condition checks whether we're currently processing the last node in this level. And that's important because the last node in a level is the one visible from the right side. When we reach that last node, we add its value to our results list. Next, we check if the current node has a left child. If it does, we add that child to the queue so it can be processed in the next level. We also check if the node has a right child. If it does, we add that node to the queue as well. Once all levels of the tree have been processed, the res list will contain exactly the nodes visible from the right side. So we simply return that list. And that's the full idea behind this solution. We scan the tree level by level using BFS, and for each level we capture the last node, which represents the rightmost visible node. It's a simple, efficient approach with ON time complexity and ON space complexity. Test case check. Let's walk through it. Input root equals 1, 2, 3, null, 5, null, 4. Let's test our function using this tree input. 1, 2, 3, null, 5, null, 4. This array represents a binary tree in level order form. 1 is the root, 2 is the left child, and 3 is the right child. 2 has a right child 5, left is null. 3 has a right child 4, left is null. We're looking for the right side view, the nodes you would see if you stood on the right side of the tree and looked inward. Quick logic check. From the right side. At level 1, you see 1. At level 2, between 2 and 3, the visible one is 3. At level 3, between 5 and 4, the visible one is 4. So the rightmost values per level are 1, 3, 4. Output 1, 3, 4, and that's exactly what our program returns. 1, 3, 4. It matches the expected output perfectly, which shows the logic is spot on. So, our implementation is correct. The algorithm cleanly captures the rightmost node at each level, producing an accurate right-side view of the tree. We begin by defining the solution class, the standard LeetCode structure where our method will be stored. This defines our main function, right-side view, which will return the list of nodes visible when viewing the tree from the right side. We create an empty list called res. This will hold the rightmost node from each level. Inside our function, we define a helper called DFS. This performs a depth-first search, and because we run in right-first order, it naturally captures the right-side nodes first. This strategy gives us an efficient ON time complexity since each node is visited once. If the current node doesn't exist, we simply return, there's nothing to explore here. This stops the DFS for that path. This line checks whether we've reached a new level of the tree. If the result list has fewer items than the current depth, it means we haven't added a node for this level yet. So we append the current node's value. And since we visit the right subtree first, this guarantees the rightmost node gets recorded. Next, we explore the right subtree. This is the key. By going right first, we ensure the first node we see at each level is the rightmost one. Then we explore the left subtree. These nodes will only be added to the result if no right-side node was found for that level. We start the DFS from the root node at depth 0. Finally, we return the list of right-side nodes we collected. And that's how this algorithm works. It first prepares a list to store visible nodes, then performs a right-first DFS so that each level captures the correct rightmost node. Efficient, simple, and elegant. Test case check. Let's walk through it. Let's test our function using this input. 1, 2, 3, 4, null, 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 5. These numbers represent a binary tree in level order format. 1 is the root, 2 and 3 are its children, and deeper nodes like 4 and 5 show how the left branch extends downward. The null values indicate missing children in the tree structure. Quick logic check. Here's why the solution works. The algorithm is computing the right side view of the tree, the set of nodes you would see if you looked at the tree from the right side. For example, level 1, you see 1. Level 2, on the right, you see 3. Level 3, only 4 appears on this level from the right. Level 4, the node 5 sits alone on the deepest left extension, and from the right view, you still see it because no other node blocks it. So the rightmost nodes at each level form 1, 3, 4, 5. And that's exactly what our program outputs. 1, 3, 4, 5. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully extracts the right side view of the tree. Efficient, accurate, and reliable. Let's wrap it up. The binary tree right side view problem is one of those interview favorites that tests your mastery of BFS, DFS, and tree visibility logic. It's a clean challenge that reveals how well you understand level order traversal, and whether you can capture exactly what's visible from the right side in just one efficient pass. We're given a binary tree and asked to return the values of the nodes that are visible from the right side, one per level, from top to bottom. There are two clean approaches. You can use BFS, where the last node you see in each level is the visible one, or DFS, where the first node you visit at each depth, going right first, becomes the answer. Both take ON time, but BFS naturally fits the idea of one value per level. We built a BFS loop using a queue. For every level, we processed all its nodes, tracked their children, and recorded the last node of that level as the one visible from the right. That gives us one clear value per depth, no duplicates, no confusion. We ran this in LeetCode, and it worked exactly as planned, efficient, one clean pass through the tree, no runtime errors. The solution passed all test cases, confirming that it correctly captures the rightmost nodes while staying within ON time and OW space complexity. The key takeaway? When working with trees, clarity often comes from thinking in levels. Mastering BFS helps you not just see what's in the tree, but what's visible from every perspective.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
What happens when an interviewer wants to see if you can beat the sword and prey approach? KTH largest element in an array is a classic efficiency trap. It looks easy, but the real test is whether you can find the answer without sorting the entire array. Nail this and you prove you understand heaps, selection algorithms, and performance trade-offs. Let's attack kth largest element in an array with the basic problem-solving framework. Breakdown: given an integer array nums and an integer k, return the kth largest element in the array. Important: it's the kth largest by order, not the kth distinct. Example: input nums equals 321, 5, 6, 4, k equals 2. Output 5. Largest is 6. Second largest is 5. Real-world example. Think of a leaderboard system that needs to show the top k performers, or a monitoring dashboard that wants the kth highest CPU spike without sorting everything. Classic interview extension. How would you do this if numbers are streaming in continuously? Hint: min heap of size k. Assess what's tricky here? Naive approach: sort the array descending and pick index k1. Time: on log n. Works, but overkill. Better approaches: the interview expects one of these. Minute heap of size k. Most common plus interview friendly. Keep only the top k elements seen so far. The heap's smallest element represents the kth largest overall. Time: on log k. Space: OK. Quick select, selection algorithm partition like quicksort, but only recurse into the side that contains the answer. Average time: on worst case, on squared, unless randomized, median of medians. Why a heap works so cleanly. You don't need everything sorted, just the top k. A min heap of size k automatically discards smaller elements as you go. Edge cases: duplicates are allowed, and count. K equals 1 max element. K equals n min element. Negative numbers are fine. Structure heap: min heap size k. Plan: create a min heap for each number in nums. Push it into the heap. If heap size greater than k, pop the smallest. After processing all numbers, the heap top is the kth largest. Return heap top. Solution 1. Sort. Time complexity: on log n. We begin by defining a class named solution. This is just a container to hold our method. This defines the function find kth largest, which returns the kth largest number from the list nums. Here we sort the entire list in ascending order. After sorting, the smallest numbers are at the front and the largest numbers are at the end. Sorting takes on log n time, which dominates the overall complexity of this solution. Because the list is sorted, the kth largest element is simply found by counting from the end. Nums minus 1, largest. Nums minus 2, second largest. Nums k, ktag, largest. So we return that value directly. And that's how this algorithm works. It first sorts the entire list, then directly accesses the kth largest element from the end of the sorted array. Efficient, simple, and elegant. Test case check find kth largest element. Sorting. Let's test our function using this input. Nums equals 3, 2, 1, 5, 6, 4, and k equals 2. These numbers represent an unsorted list of values, and k tells us we want to find the second largest element in the array. Why the solution works. We first sort the array in ascending order. Once the array is sorted, the largest elements appear at the end. For this input, sorting gives us 1, 2, 3, 4, 5, 6 from the end of the array. The first largest element is 6. The second largest element is 5. So we simply return the element at index k. And that's exactly what our program outputs, 5. This matches the expected result and confirms that the sorting-based approach is working correctly. Wrap up. So, our implementation is correct. The algorithm successfully finds the kth largest element by sorting the array and selecting the appropriate position. Simple, accurate, and reliable. Solution 2. Min heap, size k. Time complexity, on log k. We begin by defining a class named solution. This simply keeps our method organized. This defines our function find kth largest, which will now find the kth largest element using a min heap instead of sorting the entire list. We create an empty list called heap. This list will behave like a min heap, meaning the smallest element is always at the top. We loop through every number in the input list. This loop runs n times, contributing to the on part of the time complexity. If the heap has fewer than k elements, we haven't filled our heap yet, so we can safely add the current number. We push the number into the heap. Each push operation takes O log k time because the heap size never grows beyond k. Once the heap already contains k elements, We compare the current number with the smallest number in the heap, which is always at heap 0. If the current number is larger, it deserves to be in the top k. We replace the smallest element in the heap with the current number. This keeps the heap size exactly k while ensuring it always holds the k largest elements seen so far. This operation also runs in O log k time. After processing all numbers, the smallest element in the heap is exactly the kth largest element overall. So we return heap 0. Final wrap-up. And that's how this algorithm works. It first maintains a min heap of size k, then ensures only the k largest elements remain inside it while scanning the list, leaving the kth largest element at the top. Efficient, simple, and elegant. Test case check. Find kth largest element, min heap of size k. Let's test our function using this input. Nums equals 3, 2, 3, 1, 2, 4, 5, 5, 6, and k equals 4. These numbers represent an unsorted list of values, and k equals 4 means we're looking for the fourth largest element in the array. Why the solution works? We maintain a min heap of size k. This heap always stores the k largest elements seen so far, with the smallest of those k elements sitting at the top. As we iterate through the array, we first fill the heap until it contains k elements. After that, for every new number, if it's larger than the smallest element in the heap, we replace that smallest value. If it's smaller, we ignore it because it can't be in the top k. For this input, after processing all numbers, the heap ends up holding the 4 largest values in the array. The smallest among those 4, which sits at the top of the min heap, is 4. And that's exactly what our program outputs, 4. This matches the expected result and confirms that the min heap is maintaining the correct top k elements. Wrap up. So, our implementation is correct. The algorithm successfully finds the kth largest element by efficiently maintaining a min heap of size k, efficient, accurate, and reliable. Alright, let's quickly recap kth largest element in an array. One of those problems that looks simple, but really tests whether you can avoid the sort and pray trap. Breakdown recap. Conceptually, the task is straightforward. Given an array and a number k, we want the kth largest element by position in the sorted order, not the kth distinct value. So duplicates still count, and we're only after that single ranked value. Assess recap. We compared the naive approach, sorting the whole array, which works but costs more time than needed. Then we focused on the more interview-friendly strategy, keeping only what matters instead of sorting everything. That's why the min heap of size k stands out. It's efficient, clean, and scales well when k is small compared to the array size. Structure recap. The plan was simple. Maintain a structure that always holds the top k largest elements so far. As we scan through the array, anything that doesn't belong in the top group gets discarded automatically. By the end, the smallest value inside that top k group is exactly the kth largest overall. Implement recap. After setting up that approach, we ran the solution on LeetCode successfully, and everything executed smoothly with no errors. Check recap. We also verified the logic by running the provided examples and LeetCode test cases, confirming the result matches expectations, and the submission passed all test cases. Closing insight. The big takeaway here: you don't always need full sorting to find a ranked value. When the problem only cares about the top k, managing a small top k structure is often the smartest, most efficient move.
You thought your job was safe until you got that email. Now you're back on LeetCode remembering you forgot everything about trees and graphs. Interviewer says, solve this in O of n. Your brain says, 404, solution not found. Don't be that person. Subscribe to PatternMastery.com and master the coding patterns FANG companies actually test.
Ever wonder how Spotify or YouTube instantly surfaces the most played songs or trending videos? Today, we're cracking top K frequent elements, one of the most practical Pattern Mastery 100 essentials and a must-know for anyone aiming for a data or back-end role at companies like Google, Amazon, or Netflix. Over 50% of candidates get tripped up by time complexity here, so let's make sure that's not you. We'll use the basic framework: breakdown, assess, structure, implement, and check, which helps us communicate and design a solution step by step, better than STAR for algorithm questions. Let's restate the problem. You're given an array of integers and a number k. Your goal? Return the k most frequent elements from the array. For example, given 1, 1, 1, 2, 2, 3, and k equals 2, the answer is 1, 2, because 1 appears 3 times, 2 appears twice. Watch for cases like multiple elements with the same frequency, or when k equals the length of the unique elements. Imagine you're designing a dashboard for an e-commerce site and need to display the top k most viewed products in real time. You've got millions of product IDs in your logs. How do you surface the most popular items quickly and efficiently? A naive approach would be to count frequencies, then sort, on log n, time. But we can do better. First, use a hash map to count frequencies, on time. Next, instead of sorting all elements, use a min heap, priority queue, to keep only the top k frequent elements. This way, finding the top k is on log k. Alternatively, use bucket sort, group elements by frequency in on time, then collect the most frequent until you have k. Here's our plan. Count the frequency of each element using a hash map. Option 1. Use a min heap to keep the top k frequent elements. Push frequency element into the heap, pop when size exceeds k. Option 2. Bucket sort. Create a list of buckets, where each index represents frequency, and fill them with numbers of that frequency. At the end, collect the top k elements from your heap or by iterating buckets in reverse order. Now let's implement the frequency map approach, counting occurrences and sorting by frequency to extract the top k elements. We're starting our solution class that will contain our method for finding the top k most frequent numbers. This function receives a list of numbers and a number k, and we want to return the k most frequent elements. We begin with an empty dictionary that will count how many times each number appears. Think of it as a scoreboard. We loop through every number in the list. For each number, we increase its count. If it's not in the dictionary yet, we start it at 0. This builds our frequency table. We sort the dictionary items by their frequency values, from highest to lowest. This is where the on log n, time complexity comes from, sorting. Our result list starts empty. We'll fill it with the most frequent numbers. We loop exactly k times to pick the top k items. We add the number, not its frequency, to the result. Each sorted underscore items I is a pair like num, count, so we take the first element. We return our list of the k most frequent elements. Simple and clean. And that's how this algorithm works. It first builds a frequency table to count each number, then sorts those counts to pull out the top k elements. Efficient, straightforward, and elegant. Let's test our frequency map and sorting solution with this input array. These numbers represent the values we're analyzing, and we want to find the top 2 most frequent elements. First, we build a frequency map. 1 appears 3 times. 2 appears 2 times. 3 appears 1 time. So our frequency counts look like 1 3, 2 2, 3 1. Next, we sort the elements by frequency in descending order. 1, 3 times, 2, 2 times, 3, 1 time. Since k equals 2, we take the top 2 most frequent elements, 1, 2, and that's exactly what our program returns. So, our implementation is correct. The frequency map plus sorting cleanly identifies the top k frequent elements and matches the expected result. Now let's implement the min heap method, maintaining a heap of size k so we only keep the most frequent elements efficiently. This brings in Python's heapy key library, which gives us an efficient min heap, perfect for keeping track of the top k frequent elements without sorting everything. This brings in Python's heapy key library, which gives us an efficient min heap, perfect for keeping track of the top k frequent elements without sorting everything. This function receives the list of numbers and the number of top frequent elements we want. We start with an empty dictionary to count how often each number appears. We loop over every number in the input. We update the count for each number, either increasing an existing count or starting it at 0. This is our min heap. It will always store at most k elements, the current top k most frequent numbers. We iterate over each number and its frequency. If the heap isn't full yet, we still need to add elements. We push a pair, count, num, into the min heap. The heap always keeps the smallest frequency at the top. Once the heap has k items, we start being selective about what gets in. We compare the current number's frequency with the smallest frequency in the heap, which sits at position 0. If the current number is more frequent, it deserves to be in the top k. This efficiently removes the smallest element and inserts the new one. This operation is O log k, one of the key reasons this solution is so efficient. We unpack the numbers from the heap, ignoring the counts, and return them. Each number in this heap is one of the top k frequent elements. And that's how this algorithm works. It first counts every number, then keeps only the top k frequencies inside a small min heap. Efficient, memory-friendly, and elegant. Now let's test the min heap solution on a very simple case. We only have one number in the array, and we're asked for the top 1 most frequent element. First, we count frequencies. 1 appears 1 time. Then we use a min heap of size k. Push, frequency equals 1, value equals 1, into the heap. Since k equals 1, the heap will just contain this single element. At the end, the heap holds the top one most frequent value, which is simply 1. And that's exactly what our program outputs. So, our implementation is correct. The min-heap approach handles this trivial case perfectly, returning the only element as the top one frequent value. Spotlighting the most popular items fast is core to real-world systems, from trending videos to top products. Top k frequent elements is exactly that skill, turning raw counts into the k biggest winners efficiently. Let's do a recap. We're given an array and a number k, and we need the k most frequent elements. Conceptually, it's ranking by occurrence. Count how often each value appears, then return the top k. Ties are fine, and output order isn't important unless specified. We compared two strategies. The straightforward sort after counting works but costs on log n. To be smarter, we either keep only the best k using a min heap for on log k, or use bucket sort to group by frequency and collect from highest to lowest in on. Plan of attack. Build a frequency map in on. Choose a path. Minute heap. Push, frequency, element, pop, when size exceeds k. Bucket sort. Create buckets indexed by frequency, drop each number into its bucket, then scan from high to low until we have k. We followed that blueprint, first counting with a hash map, then either maintaining a size k min heap or filling frequency buckets. No extra sorting of the entire dataset, just the necessary work to surface the winners. We validated on examples like 1, 1, 1, 2, 3, with k equals 2, confirming the result, 1, 2. Variations with ties and edge cases like a single element array behaved as expected. The solution ran cleanly and passed the test cases. The takeaway: count first, then be selective. Use a min heap when k is small relative to n, or bucket sort when frequencies are bounded. Either way, you get scalable, interview-ready performance without unnecessary sorting.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
Here's a real-time data challenge that's everywhere in the tech world. Find median from data stream. It's a PatternMastery 100 classic and a favorite at Google, Amazon, and Facebook because it tests your knowledge of heaps, streaming algorithms, and dynamic data structures. Over 40% of candidates get stuck designing for both fast inserts and instant median queries. Let's make sure you're ready to impress. Let's conquer find median from data stream using the basic approach, a proven strategy for building robust, interview-ready solutions to complex streaming problems. Let's break it down. Design a data structure with two methods. Add an integer to the data stream. Return the median of all current elements. Input, sequence of numbers, one at a time. Output, the median after each query. Here's a real-world example. Suppose you're building a live dashboard for financial transactions, and you need to report the median transaction value in real time, no matter how many numbers arrive or what order. Interviewers might ask, how would you design a system to track the real-time median in a large, ongoing event log? Let's assess it. What's tricky? Median queries must be fast, O1 or O log n, and so must inserts. You need to handle an unlimited number of incoming numbers, so no sorting or rebuilding the list each time. Keeping the data split evenly for medians is the key. Think step by step. Use two heaps. Max heap, left side, stores the smaller half of the numbers. Minute heap, right side, stores the larger half. The max heap lets you instantly get the largest of the smaller half. The min heap gives the smallest of the larger half. Balance the heaps so that their sizes differ by at most one median. If both heaps have the same size, median is the average of the two tops. If one heap is bigger, median is its top. Let's go deeper. When adding a new number, if it's less than or equal to max heap's top, add to max heap, else, min heap. Balance, if any heap has more than one extra element, move its top to the other heap. This balancing act ensures that extracting the median is always O1 or O log n. Edge cases. First number, just add. Even or odd total numbers, median logic switches accordingly. Duplicates and negatives are handled naturally. Here's the structure. Initialize two heaps, max heap, invert values for Python's min heap, and min heap. On add num. If max heap empty or num is less than or equal to top of max heap, push into max heap. Else, push into min heap. Rebalance if heaps differ in size by greater than 1, on find median. If size is equal, median is average of tops. Else, Median is the top of the larger heap. Now let's implement the sorted list approach, inserting each new number in order so we can compute the median directly from the list. We start by importing the bisect module. This gives us a handy tool for inserting numbers into a list while keeping it sorted automatically. This class will store numbers as they come in and compute the median at any moment. Our constructor sets up the data structure. We keep one list, always sorted, to store all incoming numbers. Think of it like a growing, neatly organized shelf of values. This function handles the arrival of a new number in the stream. We use bisect.insort to insert the number into the correct position to keep the list sorted. No manual sorting, no reordering, Python handles it for us. This operation runs in ON because inserting requires shifting elements. This function calculates the current median from our sorted list. We grab the number of elements in the list. If the count is odd, the median is simply the middle element. We return that middle value, making sure it's a float. If the count is even, the median is the average of the two middle numbers. We compute that average and return it. And that's how this algorithm works. It first maintains a sorted list using binary insertion, then reads the median directly from the middle of the list. Simple, intuitive, and effective for moderate data sizes. Let's check. These operations describe the following sequence. Median finder create a new data structure. Add num1 add num2 find median add num3 find median again. With the sorted list plus bisect approach, every time we insert a number, we place it in the correct sorted position. Let's track the internal list step by step. Start. After add num1 insert 1 list becomes 1 after add num2 insert 2 in sorted order. 1, 2 find median current numbers. 1, 2, even count equals 2 median equals average of middle two values. Middle values, 1 and 2, 1 plus 2. 2 equals 1.5. So the median is 1.500000. After add num3 insert 3 into sorted position. 1, 2, 3 find median current numbers. 1, 2, 3, odd count equals 3 median is the middle value 2. So the median is 2.000000. Putting it all together, the outputs are null, 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 1.50000, null, 2.00000. And that's exactly what our implementation returns. So, our solution is correct. Keeping the list sorted and using bisect to insert ensures we always compute the median accurately from the current ordered data. Now let's implement the two heaps method, balancing a max heap and min heap to support fast insertions and constant time median retrieval. We import Python's heapkey module, which gives us a min heap. We'll use a neat trick to turn one of these into a max heap. This class will maintain a running median using two different heaps. We set up both heaps inside the constructor. This heap represents the lower half of all numbers. We'll store values as negatives here so it behaves like a max heap. This method adds one new number into our two heap system. We first push the new number into small, but as a negative value, turning the min heap into a max heap. We then pop the largest value from small and move it into large. This ensures the two heaps stay ordered correctly. All values in small should be less than or equal to all values in large. If large ends up with more elements than small, the two sides become unbalanced. We always want small to be the same size or one element larger. So we move the smallest element from large back into small to restore the balance. This method returns the current median from the two heaps. If small has one extra element, that extra element is the median, because it's the largest value in the lower half. We return the top of the max heap, remembering to flip the sign back to positive. If both heaps are the same size, the median is the average of the max of the lower half and the min of the upper half. This gives us an O1 median lookup. And that's how this algorithm works. It first inserts each number into a balanced pair of heaps, then reads the median straight from the heap tops. Blazing fast for streaming data. Efficient, balanced, and elegant. Now we check. Now we'll run the exact same sequence, but using the two heaps approach. A max heap for the lower half of the numbers. A min heap for the upper half. We keep them balanced so that either both heaps have the same size, or the max heap has exactly one more element than the min heap. Let's walk through the operations. Start. Max heap, low, equals, minute heap, high, equals, add num1. We insert 1 into the max heap, lower half, heaps. Low equals, 1 high equals, add num2 compare 2 with top of max heap, 1. 2 belongs to the upper half, so it goes into the min heap, heaps. Low equals, 1 high equals, 2 find median both heaps have the same size, 1 and 1. Median is the average of max of lower half 1. Minute of upper half 2. Median equals 1 plus 2. 2 equals 1.51.500000. Add num3 compare 3 with top of max heap, 1, and min heap, 2. 3 goes into the min heap high equals 2, 3. Now sizes. Low equals 1, high equals 2 unbalanced. We rebalance by moving the smallest element from high, 2, into low. After rebalancing, low equals 2, 1. As a max heap top is 2 high equals 3 find median. Now the max heap, low, has one extra element. Median is the top of max heap 22.000000. So the outputs for each operation are again, null, null, null. 1.50000000, null, 2.00000, and this matches perfectly. So, our two heaps implementation is correct. It maintains a balanced split of the data stream and retrieves the median in constant time, even as new numbers are added. Real-time data never waits. Find median from datastream shows whether you can keep inserts fast and still answer median queries instantly. A perfect blend of heaps and smart balancing. Let's do a recap. We designed a structure with two operations, add a number and get the current median. Conceptually, it's about maintaining the middle of an ever-growing set without resorting everything each time. The trap is rebuilding or sorting on every insert. It's too slow. Instead, we split the data into two sides so we can grab the middle on demand. That gives us quick inserts and O1 median reads. Our plan uses two heaps, a max heap for the smaller half and a min heap for the larger half. Every new number goes to the appropriate side, then we rebalance so sizes differ by at most 1. If both heaps are equal in size, the median is the average of their tops. If not, it's the top of the larger heap. We followed that blueprint precisely, routing each incoming number to the correct heap, rebalancing when needed, and reading the median from heap tops. We ran it on LeetCode without any errors. We verified the logic through multiple runs, odd and even counts, negatives, duplicates, and mixed orders. The medians matched expectations, and all test cases passed. The takeaway: separate, balance, and peak. By keeping two heaps in lockstep, you get streaming inserts with immediate, reliable medians, exactly the performance profile real-time systems demand.
Breakdown. Assess. Structure. Implement. Check. 5 steps. Way less panic. PatternMastery.com.
Speed round. K closest points to origin is a Phong staple because it quietly tests your grasp of heaps, quick select, and distance math without square roots. Tons of candidates sort everything in O(n) log n, and leave performance on the table. We'll solve it cleanly. With a heap you can code fast and a quick select outline you can mention for extra credit. Input: an array of points, x, y, and an integer k. We must return any k points closest to 0, 0 by Euclidean distance. Important: the actual distance sqrt x squared plus y squared is monotonic with the squared distance, so we compare xx plus yy to avoid sqrt. 3 main approaches. Full sort by squared distance O(n) log n, easy but not optimal. Heap, min heap, push all O(n) log n. Or better, max heap of size k keeping only the k best O(n) log k, and tiny memory. Quick select, /partition, to find the kth boundary in average O(n), then slice first k. We'll implement the max heap size k for speed and consistency. I'll also show a compact quick select. Plan with heap k. Define dist2p equals p0, p0, plus p1, p1. Maintain a max heap of minus dist2, point, or store, dist2, point, and invert logic. In Python we simulate max heap by pushing dist2, I, or dist2, x, y. For each point, push into heap. If heap size exceeds k, pop the farthest, the one with the most negative key because we stored negatives. Return the k points from the heap. Now let's solve solution 1 for the k closest points to the origin problem. This method uses a very simple approach: sort the points by distance. I'll walk you through the concept first, then explain every line of the code in a clean, easy way. Time complexity is O(n) log n, where n is the number of points. Sorting dominates the time cost. The idea of this solution: every point has a distance from the origin, 0, 0. Instead of calculating the actual distance, which requires a square root, we compare squared distance because it preserves the ordering. We sort all points by their squared distance, then simply take the first k points, the closest ones. Why squared distance? Because square root and squared values increase in the same order, so comparing squared values is faster and avoids unnecessary math. Line-by-line explanation of the code.
Define a class called solution. Define a function k closest that takes a list of points and an integer k. Sort the points by their distance from the origin using x squared plus y squared. Return the first k points from the sorted list.
And that's how this algorithm works. It first sorts all the points by squared distance, then returns the first k entries. Efficient, simple, and elegant. Sorting is the main operation, giving us O(n) log n complexity. We use squared distance to avoid computing square roots. This method is ideal when you need all points sorted by closeness, not just the kth distance threshold. It's very easy to implement compared to heap or quick select approaches. Now that we've implemented our solution to find the k closest points to the origin, let's check it with a real input. This helps us understand how the algorithm sorts the points by distance and selects the closest ones. We'll walk through the input, see how distances are compared, and verify that the output matches the expected result. Let's test the function using this input. The points represent coordinates on a 2D plane, and k equals 1, meaning we want the single closest point to the origin. Here's why the solution works. The algorithm calculates the squared distance of each point from the origin using x times x plus y times y. Then it sorts all points based on these distances. Finally, it returns the first k points from the sorted list. For this example, the point 1, 3 has a squared distance of 10. The point 2, 2 has a squared distance of 8. Since 8 is smaller than 10, the point 2, 2 is closer, and that is the one returned. And that is exactly what the program outputs, 2, 2. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully finds the k closest points to the origin. It correctly computes distances, sorts them, and returns the expected result. It works efficiently for this test case and scales well for larger inputs. This is solution 2. Finding the k closest points to the origin using a max heap. We maintain a heap of size k, always keeping the farthest point at the top so we can efficiently replace it when a closer point appears. Time complexity is O(n) log k, where n is the number of points. Heap operations are log k, and the heap never grows beyond size k. We import the heapecp module to use Python's built-in heap operations. We define a class solution to contain our function. The function k closest returns the k closest points to the origin from a list of points. Initialize an empty list to act as our max heap. For each point, calculate its squared distance to the origin. Squared distance avoids using square roots, which are slower. If the heap has fewer than k points, push the current point onto the heap. We use dist because Python's heapy is a min heap by default, so negating the distance simulates a max heap. If the current point is closer than the farthest in the heap, replace the farthest point with this one. Finally, extract the coordinates from the heap and return them as a list. The heap never grows larger than k, so all push and replace operations are O log k. Squared distances are sufficient for comparison. This approach is efficient for large n because we only maintain k elements in memory. And that's how solution 2 works. It first initializes a max heap of size k, iterates through each point keeping the closest ones, and finally returns the heap contents. Efficient, clear, and practical. Before checking the output, let's understand the problem. We are given points equals 3, 3, 5, -1, 2, 4. A list of 2D points k equals 2, the number of points closest to the origin we need to find. The goal is to return the k points closest to 0, 0 based on Euclidean distance. Let's test our function with this input. Each point represents coordinates in 2D space, and we want the 2 points nearest to the origin. Here is why the solution works. Compute squared distances for each point from the origin. 3, 3, 3 squared plus 3 squared equals 18, 5. -1 5 squared plus -1 squared equals 26 2, 4 minus 2 squared plus 4 squared equals 20. Use a max heap of size k to keep the closest points, push points with negative distances to simulate a max heap. If a new point is closer than the farthest in the heap, replace it step by step with this input. Add 3, 3 heap equals 18, 3, 3 add 5, -1 heap equals 26, 5. -1 and 18, 3, 3 add 2, 4 distance equals 20 which is less than 26 replace 5. -1 heap now contains 3, 3 and 2, 4 the two closest points, and that is what the program outputs, 2, 4, 3, 3. The order may differ but the points themselves are correct. This confirms the code works correctly for this test case. Our implementation is correct. It successfully finds the k closest points to the origin. It correctly calculates distances from the origin. It efficiently keeps the k closest points using a max heap. It works for any list of points in 2D space. Breakdown recap. We're given n nodes forming a connected, acyclic graph, a tree. Our goal is to find all possible root nodes that produce the minimum height when the tree is rooted there. In simple terms, we're looking for the tree's centers, the points that minimize the longest path to any leaf. Assess recap. The brute force approach would be to run BFS or DFS from every node to measure height, but that's too slow. Instead, we realize that the tree's centers can be found by trimming leaves layer by layer, just like peeling an onion. Each round, we remove the outermost leaves until only 1 or 2 nodes remain, which are the centers of the tree. Structure recap. We handled small cases first. If there are 2 or fewer nodes, we just return all of them. Then we built an adjacency list and tracked the degree of each node. Next, we added all current leaves to a queue, and while more than 2 nodes remained, we kept removing those leaves, updating their neighbors, and collecting new ones as they appeared. The final remaining nodes are our centers. Implement recap. After coding this peeling logic, we ran it on LeetCode, and the solution executed smoothly without any errors. Check recap. We verified it across multiple test cases, and each time, the output correctly identified the minimum height tree roots. Closing insight. The big lesson? Sometimes, finding the center of a problem means working from the outside in. By trimming layer by layer, we let the structure reveal its own core, efficiently, cleanly, and in linear time.
Rejected. 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 At some point, it is not bad luck. It is bad prep. PatternMastery.com.
Time travel debugging, but for keys. Time-based key value store is a PatternMastery 100 favorite because it blends hash maps with binary search. It's asked at Meta/Amazon to see if you can store version data and pull the value as of a timestamp, fast. Today we'll lock it down with basic and produce clean O-login. Lookups. We must design a class with set key, value, timestamp. Store the value for the key at timestamp. Get key, timestamp. Return the value for the key with the largest timestamp less than or equal to given timestamp, return if none. Input guarantee. For each key, timestamps in set are non-decreasing. That means we can keep a sorted list per key. Naively scanning backwards at get is on and too slow. Because per key timestamps are sorted, we can binary search the last timestamp not exceeding the query, O-log_n, time. We'll store dict key, list of, timestamp, value, or 2 parallel lists, append on set, and use bisect_right on get. Keep store. Dict str, list tuple int, str. Set, store key. Append timestamp, value. Get, binary search that list to find the rightmost pair with t less than or equal to query. If none, return. Now let's solve solution 1, the binary search with bisect approach. Time complexity. Set operation is O1. Get operation is O-log_n. The idea: each key stores a list of timestamp, value, pairs. Every time we set a value, we just append it, super fast, O1. For get timestamp, we need to find the latest timestamp that is less than or equal to the given timestamp. Instead of scanning the list, we use binary search, bisect_right, which finds this position efficiently in logarithmic time. Line-by-line explanation of the code. We import Python's built-in bisect module. This gives us fast binary search tools. Think of it like asking Python to help us quickly find where something belongs inside a sorted list. We start a new class called TimeMap. This class will hold all our timestamp data. This initializes the object every time we create a time map. We create a dictionary called store. Each key in this dictionary will map to a list of timestamp, value, pairs. Basically, key maps to a timeline of values. This method saves a value together with its timestamp. If this is the first time we've seen this key, we create a new empty list for it. We simply add the timestamp value pair to the end of the list. No sorting needed, timestamps are always increasing. This makes set O1. This method retrieves the value associated with the largest timestamp that is less than or equal to the given timestamp. If the key does not exist at all, we return an empty string. We grab the list of timestamp, value, pairs for this key. This is the heart of the algorithm. We ask Python where the pair, timestamp, something very large, would be inserted. By using CHR127, a very large ASCII character, we make sure our search finds the rightmost spot for this timestamp. Binary search makes this step O log n. If the result index I is 0, it means every timestamp we have is greater than the requested one, so there's no valid value to return. Otherwise, we return the value attached to the timestamp just before index I. This gives us the correct value for the latest timestamp less than or equal to the requested timestamp. And that's how this algorithm works. It first organizes timestamps in simple lists, then uses binary search to instantly find the closest valid timestamp. Efficient, simple, and elegant. Set is O1 because we only append. Get uses binary search, making it O log n. Using timestamp, CHR127, ensures we get the correct boundary using bisect_right. Each key maintains its own timeline. Now that we've implemented our timemap class, let's verify that it behaves correctly with a sequence of operations. This test will show how we can store key-value pairs at different timestamps and retrieve the most recent value for a given time. We'll walk through the input operations, see how values are recorded and retrieved, and confirm that the output matches the expected results. Let's test our time map using this input. We perform a sequence of operations. Initialize a time map. Set key foo to bar at timestamp 1. Retrieve the value of foo at timestamps 1 and 3. Set key foo to bar 2 at timestamp 4. Retrieve foo at timestamps 4 and 5. Here's why the solution works. The algorithm stores all values of each key as a list of timestamp value pairs. When get is called, it finds the largest timestamp less than or equal to the requested timestamp using a binary search. Step by step, after set foo, bar, 1, the list for foo is 1, bar. Get foo, 1, returns bar because timestamp 1 exists. Get foo, 3, returns bar because the latest timestamp less than or equal to 3 is 1. Set foo, bar 2, 4, adds the pair, 4, bar 2. Get foo, 4, returns bar 2, and get foo, 5, also returns bar 2 as the most recent value less than or equal to 5. And that is exactly what the program outputs. Null, null, bar, bar, null, bar 2, bar 2, bar 2. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully handles timestamped key value storage and retrieval, efficient, accurate, and reliable. Our implementation is correct. It accurately stores multiple values per key with timestamps. It retrieves the latest value less than or equal to the requested timestamp using binary search. It passes the given test case and is efficient for larger inputs. This is solution 2, implementing a time map using manual binary search to efficiently get values by timestamp. Instead of relying on Python's bisect, we perform a classic binary search to find the largest timestamp that is less than or equal to the target. Time complexity is O log n, per get operation, where n is the number of timestamps for a given key. Each set operation is O1 since we just append. Binary search lets us quickly find the correct value. We define a class timemap to hold our key value time data structure. Initialize an empty dictionary to store all key value pairs as lists of timestamp, value, pairs. For a given key, append the timestamp, value, pair. If the key is new, create an empty list first. To get a value at a given timestamp, check if the key exists. If not, return an empty string. Otherwise, get the list of stored pairs for that key. Set up left and right pointers for binary search, and initialize a variable to hold the result. While the search space isn't empty, compute the middle index. If the middle timestamp is less than or equal to the target, save its value and search the right half to find a later timestamp. Otherwise, search the left half. Return the value associated with the largest timestamp less than or equal to the target. If none exists, return an empty string. Binary search ensures O log n, per get. Set operations are O1. This works even if timestamps are non-consecutive. Manual binary search is helpful if you want more control than using bisect. And that's how Solution 2 works. It first sets up the dictionary of timestamped values, then uses binary search to efficiently get the most recent valid value. Simple, efficient, and precise.
This is the time map, storing values with timestamps. Set saves a value, get retrieves the latest value at or before a timestamp. Like Solution 1, we track boundaries, here, timestamps, to get the correct value efficiently. For key foo, timestamp 1 bar, timestamp 4 bar 2, get at 3 returns bar, the latest before 3. Output, null, null, bar, bar, null, bar 2, shows it works. Simple, accurate, and reliable.
Breakdown recap. We needed to design a class with two main operations: set, which stores a key value pair with a timestamp, and get, which retrieves the most recent value at or before a given timestamp. If there's no valid timestamp for that key, we simply return an empty string. Assess recap. A naive way would be to scan backward through all stored timestamps each time we call get, but that's too slow. Since timestamps for each key are always added in non-decreasing order, we realized we could use binary search to find the correct version efficiently. That gives us a clean O log n lookup instead of ON. Structure recap. We stored all data in a dictionary that maps each key to a list of pairs, each pair containing a timestamp and its corresponding value. When setting a value, we just append it to that list. When getting, we perform a binary search to locate the rightmost timestamp less than or equal to the query time and return its value. Implement recap. After implementing the class with set and get methods, we ran it on LeetCode, and it executed smoothly without any errors. Check recap. We tested multiple scenarios, overlapping timestamps, missing keys, and boundary cases, and all produced the correct outputs. The main takeaway? Time-based storage problems reward structure and search efficiency. By pairing hash maps with binary search, we built a clean, scalable solution that handles version lookups in logarithmic time.
Wake up. Work. Scroll jobs. Do random LeetCode. Feel behind. Repeat. Break the loop. PatternMastery.com.
You made it this far. That already puts you ahead of most people. But remember, this was never about finishing 100 problems. It was about seeing the patterns behind them, because in a real interview, you will not get the same question. You will get something unfamiliar, but built from something you've already seen. And when that moment comes, you won't rely on memory. You'll rely on recognition, on structure, on the system, basics, and you trained it all in Python. So keep training, keep breaking problems down, keep looking for patterns, because the goal was never just to solve problems. It was to think like someone who can solve any of them. And that's the difference between practicing and being ready.